Hi guys, in this module we will be discussing what is a graph data structure, why it is important to learn a graph data structure, and what are the various applications and how you can build some graph algorithms. Okay, so a graph is a data structure that is like a network. You can see it's a network containing five vertices, and also there are some edges that connect these two nodes. Okay, so it's a non-linear data structure. It's not like a list, it's not like a array, but it's a network like data structure. Now you might think, why do we need to create such a data structure? So this data structure is really important, and it lot of problems can appear in interviews related to graphs, but those problems are relatively easy as compared to problems that you might find in coding competitions like ICPC or hiring challenges or Google Kickstart. So it's a very important data structure from the uh, competition point of view, because if you talk about ICPC, at least one or two problems you will get on graphs definitely. Okay, so we will learn what is a graph data structure and how we can build a couple of graph algorithms that are quite common and popular, and we will also see how it is used in problem solving. But not just that, graph also has lot of real life applications. Okay, so a lot of real world problems can be solved using graphs. So this makes graphs a very important data structure to learn and master. So let us discuss about these applications one by one. So the first application is very common. It's about Google Maps. So if you think about the whole world as a network of landmarks or as a network of cities, you can represent each location by a vertex, and you will find there are edges that connect two cities or two vertices. That makes this problem, that makes this as a graph problem. Okay, so let me show you. If you want to right, so let's say if you want to go from Delhi to Mumbai or Delhi to Agra, you will have lot of cities in between them, and you will have lot of roads connecting between them. So we can call all those connections as edges. And edges can be flights also, because if you are taking a flight from Delhi to Mumbai or Delhi to Goa, then that represents there is a connection from Delhi to another node, Mumbai. So that's where graph comes into picture, and you might be interested in finding out, okay, what is the path that takes the minimum time, okay, what is the path that takes the minimum cost. So all those problems can be formulated as graph problems. Apart from it, you have social networks. Okay, so all social networking websites like LinkedIn, Quora, Instagram, they also build a graph of users. So all the people, they will form vertices of the graph, and all those who are connected, they will form edges of the graph. And you can use this kind of a graph to solve various problems. For example, you want to generate your LinkedIn newsfeed, so you generally see, okay, your connection has liked this post. So where does it come from? It comes from this graph data structure. Okay, so you can use it to find mutual friends also, like on Facebook. If you have two people who are connected, and if you also know uh, what are the neighbors of person X and person Y, you can also find out, okay, these are the mutual friends of these two persons. So like that. And you can also use graphs in designing circuits like PCB design. So maybe you have a lot of resistors spread across on a electronic board, and you want to connect them through a wire, and you want to minimize the total length of wire that goes on the circuit. So that can be used so that the packing on of the board can be done in an efficient manner, and you can use less metal. So again, this can be formulated as a graph problem. And you also have routers spread across the world. So when you access a website, let's say you're sitting in India and you are accessing a server from which you're getting data, and that data is coming through a network of routers spread across all of the world. So if you want to minimize the total time that website will load on your system, you need to optimize the flow of packets through this network of routers. So that is again kind of a shortest path problem that graphs around these routers can use. Okay, and also If you talk about delivery route problem, for example school vans or the Amazon delivery vans, they also um, they start from a warehouse, they go to different number of cities and they come back to the warehouse. So in this case it's not going from a source to destination, it's going from source to source, but covering all the orders that lie in between the cities. Okay, so that's where graphs can help you to solve such kind of problems. Apart from it, you can have problems in which you have to resolve some dependencies. For example, if you want to run your C++ code on a system, that is a task. Installing Sublime Text is a task. Installing GCC is a task. And installing an OS is a task. So you need to find out in which order I should do these tasks so that there are no conflicts. Obviously, there are certain dependencies. If you want to install Sublime Text, then you must have an operating system. If you want to install a G++ compiler, then you must have an OS. So you can see there would be some connections between these tasks, and also there would be fixed order. For example, first install the OS, then you install the Sublime Text, then you install uh, the compiler, and then you execute a C++ code. So you cannot do these tasks randomly. So we will see this is done using a algorithm called topological sorting. So then graphs are also used in deep learning. So if we talk about neural networks, then all neurons can be treated as vertices, and there can be connections between them. Those can be called as edges. So frameworks like TensorFlow, they also build competition graphs for optimizing different calculations. So there also graphs are used in artificial intelligence to simplify a lot of mathematical calculations and do a lot of work in the backend. Also, if you talk about a web page or a web document, that is also organized in the form of a tree. So it's not a graph exactly, but it's a tree. But we also know every tree is a graph. So if you see this tree structure, you will find there are nodes, and these nodes have certain elements, so certain divs, certain h1 tags, certain list elements. So when you work with JavaScript, you generally need to fetch some elements from this uh, DOM model. Okay, so you need to traverse this tree. So you may need to do some kind of a tree traversal to fetch different types of elements from this tree, and this is widely used in building web applications. Okay, and apart from it, several graph algorithms are also used in image processing, such as tasks like segmentation, and you can treat each pixel as a vertex, and connections between neighboring pixels, they can be treated as edges. Okay, and you can also build some tools for paint. For example, if you want to build a paint bucket tool, and if you want to fill some color in a region, then you drop a color at that particular point, and it will eventually spread out to all neighboring pixels until you found a boundary line. Okay, so here also you can use graphs to solve this kind of a problem. So there are a lot many applications, and we will be discussing some of these applications. We will be building some of the algorithms in the coming videos. So let's begin and start learning about graph data structure and how to solve problems using graphs. Hi everyone. In this lecture, we will see different ways to represent a graph data structure. Okay, so we want to now understand how do we store a graph inside a memory. So let us assume we have a very simple graph like this, in which we have four vertices and some edges. Okay, so you can see these are the connections that we have. Now we want to see if we want to store this graph inside the memory inside the computer, then what we can do. Okay, so the very first thing that comes in our mind is we can create a 2D array. Okay, like this we can say, and we can just fill what all nodes are connected with each other. So in this, if you see, there is a connection between 0 and 1. So you can say, okay, 0 and 1 are connected, and 0 and 2 are also connected, and 1 and 2 are connected, and 2 and 3 are connected. Okay, so 2 and 3. And also, if you see this particular edge, this connects 2 with 3 and also connects 3 with 2. So that means you will also make this kind of a connection. So in any graph, given any edge, so any edge can be a unidirectional edge or a directed edge. Okay, so we have this term called directed edge. For example, there is an edge from 0 to 1, but there is no edge from 1 to 0, so we do not put anything here, so this actually remains as false. Okay, so similarly we have an edge from 0 to 2. That means there is an edge from 0 to 2, and between 1 and 2 I'm not making any arrow. That means this is a undirected edge. So any undirected edge also means it's a bidirectional edge. Okay, so that means it connects 1 with 2 and also connects 2 with 1. So we can put 1 is connected with 2, and we can also put 2 is connected with 1. Similarly, 2 is connected with 3 and 3 is connected with 2. So we can make a adjacency matrix. So this representation of graph is called adjacency matrix, and this is the first way to represent a graph. Okay, another very simple way would be, we can just represent this graph by list of edges and vertices. Okay, so if I say, okay, what all vertices are there in a graph, so I can use a list data structure or an array. I can say, okay, there are vertices 0, 1, 2 and 3, and I can store list of edges. So I can say, okay, there is an edge between 0 and 1, so there is an edge between 0 and 1, there is an edge 0 to 2, there is an edge 1 to 2, and there is also an edge from 2 to 1, and there is an edge between 2 to 3, and we can say there is an edge between 3 to 2, something like this. So if we have this particular information, okay, if we just have these two data structures, that means we do have the entire graph. So this representation of graph is called edge list. So every representation has its own benefits. Okay, so this representation has its benefit that if you want to look between edge between two nodes, so if you want to check if there is an edge between 2 and 1, so you can just directly check. Let's say this matrix is M, so you can check M of 2 comma 1 is true or false. So this actually gives this you in order 1 time, but there are certain disadvantages as well. Okay, so what is the disadvantage of this representation? That if you want to store all the edges, then it will take n square memory. Okay, and in the worst case, it is possible that graph has only few edges, but you are still taking um, n square memory space to store all the edges. Second is, if you want to find neighbors of a node, this is a very common operation that we will see while working with graphs. That given a node, let's say you are given a node as 3, you want to find out what all nodes are the neighbors of 3. That means what all nodes are directly connected with 3. So you have to iterate over the entire row. So finding neighbors is going to take order of n time, assuming there are n number of nodes in the graph and let's say e number of edges. Okay, so let us also think about what is the maximum number of edges and what is the minimum number of edges a graph can have in terms of number of nodes. Okay, so maximum edges, you can say if each node is connected with every other node, then you can pick any edge in nc two ways. So that means you have order of n square edges if every node is connected with every other node. And minimum edges, you can say it can be 0, because a graph can be like this. In this graph there is no edge. But if we talk about a connected graph in which all nodes are connected, then for any number of nodes n, you need n minus 1 edges. Okay, for a connected graph. So for example, if you just keep one node, you do not need any edge, but for every other node you add in the graph, you actually need an edge to connect it. So For a connected graph, it will be n minus 1 edges, and this type of a graph is also a tree. Okay, so every tree is also a graph, and this type of a graph will not contain a cycle, and hence we can also call it as a tree. Okay, so we have seen two representations of graphs. Let's talk about some more representations. So another way of representing a graph would be in the form of a adjacency list. So this is a very popular method, and it is used in a lot of problems as well. So in adjacency list, we make a list of all the nodes, and we store what all neighbors are there for this given node. Okay, so 0 is connected with 1 and 2. So I can say, okay, 0 is connected with 1 and it is also connected with 2. 1 is connected with 2, and 2 is connected with 1 and 3, and 3 is connected with 2. So you can see this structure, this is actually a list. Okay, so what we can do is we can make a hash map in which you have node as the key, and in the value, okay, whatever is the name of the node, it can be an integer, it can be a string, and in the value you can have list of integers as the value. Okay, or you can have a list of whatever is the node type, that as the value. Okay, so this can be the value of that. Okay, so you can just put all these entries in this form as key value pairs in the hash map, and this will have an advantage that if you want to find neighbors of a given node, if you want to find neighbors of 0, you can directly iterate over the neighbors. Okay, so you can find neighbors in O of neighbors time. Okay, and another advantage is that it is memory efficient. It will not require n square memory. Okay, so in the worst case, if you have e number of edges, it will require order of e memory only. Okay, and this operation is quite fast. If you want to iterate over the neighbors, you can do it directly. So this is another way of storing a graph, and we will see it in lot of problems. One more way is, sometimes in some questions you are given a 2D matrix, and we call that as a implicit graph. For example, maybe you are given a 2D array of zeros and ones. Okay, let's say something like this. In some of the questions, you may be given something like this, and you are asked to calculate how many connected components are there in the graph. Okay, so let's assume that if there is an element 1, then all the elements that are in the left, right, top, down, and if they are 1, that means they form a connected component. So clearly here you do not actually need to convert this 2D array into some other data structure, because you can directly see, okay, given any node, I can just find out the neighbors of that particular node. Okay, so I know these nodes are connected with each other. Okay, so this kind of a graph will be called as a implicit graph. So you may see some problems in which you are given a 2D array, and you can just directly work on a 2D array to get the nodes and the vertices of the graph. Okay, so I hope you got an idea how do we store a graph. So most of the problems we will be using adjacency list, but in some problems we may also use some other representations like matrix, edge list, and a implicit graph. So thank you guys, I hope this lecture was clear to you. Hey guys, so now you have understood what a graph is. So it's time to implement our first graph data structure using a adjacency list. So let's begin. Okay, so let's say this is the graph that is given to us, and this is how the adjacency list representation of this graph would look like. And now there can be multiple ways to store this graph. So we may use a hash map that we will see in the next video, but just to make the implementation simpler, and since we have nodes which are numbered from 0 to n minus 1. Okay, so what I can say is I will put all this data inside a list, and I will create an array of lists. So I need a list L1, a list L2, L3, and L4. So firstly I need to know how many vertices I have in the graph, and accordingly I can create an array of lists. Okay, so I can create an array of lists of size v. So that means I have v number of arrays, and each array, the zeroth array will store what all neighbors are there for the zeroth node. First array will store what all neighbors the first node has. So first node has only two neighbors, that is 2 and 0. So they will go in the list of the first array. Okay, so what we will do is we can start by writing some code. So let me define a class called graph that will represent my data structure, and public I can make a graph constructor where I can accept okay how many nodes this graph has. So I can define a data member v, and I can say okay this arrow v equals to v. So this will basically set okay we have these many vertices in the graph, and maybe we can create a function called add edge. Okay, and since there is an edge between two nodes and each of those are integers, I can say okay int x and int y. So what I can do is if there is an edge from x to y, and I'm assuming it's a bidirectional edge, so what I can do is I can say okay I need to make a array of lists. Okay, so if you need to make a single list, then this can be written like this, list of integers as L. Okay, but if you need to make an array of lists, so we can say okay whatever is the size v, we can use it, but this v is not known to us during compile time, but it will be known to us at runtime. So what we can do is we can keep a pointer to an array of lists, and this we can initialize once we know the number of vertices. So I can say a list int star L, this is equal to new list int of v. So that means L is a pointer to an array in which each element of the array is a list. Okay, so if I talk about L of 0, then it means this whole list. If I talk about L of 1, it means this whole list. So L is a pointer, and it's a pointer to an array of lists. Okay, so if you just write it like this, it's equal to new list. So that means you're creating a list dynamically. And if you say okay no I want instead of one lists I want v lists, so this is actually an array of v linked lists. Okay, so this is, you can see this is the first linked list, second linked list, third linked list, and the fourth linked list. This is what we can do here. So I have initialized this inside the constructor, and if you need to add an edge, then it's also going to be simple. You can say if there is an edge between x and y, you can say L of x dot pushback y, and you can say L of y dot pushback x, and that's it. So that will simplify the work for you, and you are done. Okay, okay, so what we can do next is we can say let's create a graph with 4 vertices. So I call the constructor, and if I want to add edges, so I can call this function g.addEdge, and here I can say add an edge between 0 to 1, add an edge between 0 to 2, and also add an edge between 2 to 3. Okay, so since I have 4 edges, so one more edge that I need to add is between 1 to 2. Okay, so this will add all the 4 edges, and these are bidirectional edges. Okay, so here what we have done is list has a function called pushback. So I say L of let's say L of 0 dot pushback 2. So that basically does what it does is we have a linked list 0, and in that I push back an element 2. So if I say 0 is connected with 1, I say okay 0 is connected with 1, then L of 0 dot pushback 1. So in the 0th linked list I push 2 elements, 2 and 1. So that means 0 is connected with these 2 particular elements. So now let's also try to print it. So if you want to write a small function that will actually print the adjacency list, so in that you can iterate over all the elements. Okay, so you can say let's try to iterate over all the vertices. So you know we have v vertices. For int I equals to 0, I less than v, I plus plus, and for every vertex you need to iterate over that particular linked list. So I can say for int x, that is there in L of I. Okay, so either you can use this kind of a loop or you can use an iterator. So you can say auto neighbor or int neighbor. Let me write it like this only. Okay, so int neighbor that is there in L of I, cout neighbor. Okay, so this is one way, and here we can just print we are on this particular vertex, and that vertex is I, and followed by the neighbors of that particular vertex. And after every vertex I just print a handle here. Okay, so we have written the code to print all the adjacency lists. So what we do here, we go from the 0th linked list till the vth linked list, and for every linked list we say okay, we keep a variable neighbor that iterates over the ith linked list. So ith linked list contains all the neighbors of the node I, and that's how we get all the neighbors, and after every neighbor we press a handle here. So let's try to run this code. Okay, so let's see the output. Now you can see this is the output of the print function, and you can see 0 is connected with 1 and 2, that's true. 1 is connected with 0 and 2, that's true. 2 is connected with 0, 3 and 1, that's true, and 3 is connected with 2, that's true. So this is what adjacency list representation of a graph looks like. So that's all. We will see more details in the next video. Hi everyone, in this video we will have a look at how we can implement a weighted graph, and also in this graph you can see the names of the nodes are not integers but they are strings. Okay, so in the earlier example we had a edge between 0 to 1, so we could directly use L of 0 dot pushback 1, but in this case I cannot write L of a dot pushback b. Okay, so obviously we cannot use a list in this case. So what we need to do, if we want to maintain a adjacency list, we need to maintain a hash map. So we will have a followed by the neighbors. So in the neighbors we have b, we have c, and we have d, and also you can see we have a weighted graph. That means there is a weight assigned on every edge. So if you want to go from A to B, it will take 20 minutes, or it will take a distance of 20 kilometers, let's say. Okay, so what you need to store is, you need to store A, and A is connected with B, and the distance of B is 20 from A. A is connected with D, and the distance of A to D is 50, and you have A connected with C, and the distance is 10. So again you can see this is a list, and this is a list of pair, and in pair the first element is a string and the second element is a integer. Okay, and this value is a string. Okay, so what we can do, we can maintain a hash map where we will have a key of the type string, and the value will be of the type list of pair of string comma int, and we can put all of these values inside the hash map. So we also need to modify our function add edge, and here we also need to pass what type of edge it is. Is it a unidirectional edge, is it a bidirectional edge, and what is the weight on this edge. Okay, so that's what we need to define here. So let's also give something like this: A to B is a bidirectional edge, so we may keep a variable boolean that okay, this is a bidirectional edge, so I will connect A with B and I will also connect B with A, and the weight is 20. So something like this we should give. So keeping this in mind, let us design a graph. Okay, so we need to store everything in the form of a adjacency list, and this time this adjacency list will be a unordered map of the type string, and the value will be of the type list of pair of string and int, and let's call this map as L. Okay, and yes, so okay, so let's say someone says, okay, I want to add this particular edge in the graph. So let me say, yes, okay, so let me say we have this function void add edge, and this function gets a string source, or let's say x, and there is a node from x to y, and that is a bidirectional edge. So let's assume it's a bidirectional edge or not, and we will also get the weight. So let me just reduce the size. Okay, so what we can say is, in this unordered map L, I can say L of x. So L of x means map of x. That's basically the value, and that value is going to be a list. So we can directly use a pushback function here. So I can say L of pushback. What? I want to make a pair between y and weight. That's it. And I can check if it's a bidirectional edge. We also need to do other way around. So L of y dot pushback, and here we say make pair x comma weight. That's it. So this is actually the pushback function. So pretty easy. We didn't make a lot of changes, but it's very similar function, except instead of using an array of lists, we are simply using a hash map. So what is happening now, if you have say edge between x to y, we say okay, in the map corresponding to the key x, there is a list, and in that list you push a pair in which you have y comma weight. And if you see it's a bidirectional edge, that means x is connected to y and y is connected to s. So you also do it in the key for y. So L of y dot pushback x comma weight. Okay, so that you do for all the edges, and all the edges will be inserted in the graph. So let's try to do this thing. Okay, so we have given this information, all these edges are present. So the bidirectional parameter is true in all the edges except for the last edge, because that's a directed edge. That's edge from A to D. In that case, this statement will not execute. So D will be a neighbor of A, but A will not be a neighbor of D in this case. Okay, so let's write a print function that will actually help us to iterate over all the vertices in the map, and we can print neighbors of each vertex. So void print adjacency list, and it will not take any input. So here we need to iterate over all the keys in the map. So I can say for string city that is there in the map L. Okay, so this when you iterate over map, every time you iterate over the map, you basically get a key and a value pair. Okay, so you will get A and the neighbors. So what you should actually say is you have okay, so when you iterate over a map, you will get a key and a value pair. Okay, so what you will get is A and the list associated with A. So I can say for let me say pair of this thing. Okay, so what I will get is a pair of string and list of string. So these two entries will be clubbed into a pair, and I will get this whole thing when I iterate over this map. So let me just say auto p in L. For every pair in the map L, I want to get the city. So this part, this is the key. So I can say string city, that's equal to p dot first, and I can say I have a list of pairs. So that's basically list of pair of string int int, and let's call this as neighbors, and this is equal to p dot second. So what I can do is I can iterate over the neighbors and print all these elements. Okay, so for every pair, let me just say auto some a single neighbor that is there in neighbors, I can do cout neighbors dot first. So that means my destination city. Okay, so that is a string that's equal to neighbor dot second, and the distance, so int distance equal to neighbor dot first and neighbor dot second. Okay, I will explain you, don't worry. And here we can do cout destination and the distance. Okay, and we can put a comma here. That's it. And we can put a handle here, and we can also print the city here. We can say, okay, we are in this particular city, and these are the neighbors of that particular city. So we have written a function to print the adjacency list. So let me go through this function. So when I iterate over the map, so I say auto p in L, so this will give me all key value pairs one by one. So in the first chance I will get this, so A is also connected with D, and it's 50. So this whole thing is P. Okay, and I say city is P dot first, so city is A, and I say P dot second. So what is P dot second? This part of the pair. Okay, so this is P dot second, and this is nothing but the value corresponding to a given city. So that is nothing but list of pair of string and int. So this is what this data structure is, and we iterate over this all these neighbors. So auto neighbor in this list of neighbors, so this is called as neighbors, and this is what is a neighbor. And I say, okay, destination is neighbor dot first. Since this entity is a pair, so I print the destination, that is B, followed by neighbor dot second. I print how much distance it is from the distance from A. Okay, so that's neighbor dot second. I print out these and I go to the next value. Okay, so next value is C comma 10 and so on. So once I finished with this, I come in this loop, I pick B and do the same process for all other nodes. So this will actually help us to print adjacency list. Okay, so let's run the code, and here we have these in the output. So we can see A is connected with B and distance is 20, with C it's connected and the distance is 10, and with D the distance is 50. And in D you can see it's connected with B and it's connected with C, and you can see D is not connected with A directly because this edge is a directed edge. So this whole information represents this graph, and also you can see the nodes are not in specific order. That's because we are using an unordered map, and that is based upon the concept of hashing, and that means elements or the cities can come in any possible order. Okay, so that if you want these cities should be sorted lexicographically, you can also use a map data structure to do the same. So I hope this implementation is clear, and thank you for watching. Hi everyone, in this video we will talk about a graph traversal. So what is a graph traversal? So a graph traversal is a way of visiting all the nodes of the graph starting from a given node. Maybe I'm going to say, okay, this is the source node. You start from this point and visit all the nodes in the graph. So this is called as graph traversal. So it's nothing but it's a traversal that covers all the nodes of the graph. Okay, it's a way of visiting all the nodes of the graph, And there are two fundamental ways to do this. One is called BFS, or it's called as breadth first search, and another way is called as DFS, that's called as depth first search. So we will discuss about both of these ways one by one, but in this video we will focus on the breadth first search. That is a iterative way. Okay, so that's like a iterative way, and DFS is a recursive way. So let's focus on what is BFS. Okay, so BFS, as the name suggests, breadth first. That means you start from a given node and you will try to reach its neighbors. So what you will do, maybe you start from the source node and then you go to the neighbors of that particular node. Okay, you go to the neighbors of that particular node. So suppose we have 0. From 0 we can go to neighbors of 0 that are 1 and 3. So what we will do is, since we cannot go to both of these neighbors at the same time, we need to store these neighbors somewhere. So what we will do, we will take a data structure like queue. Okay, it's just like level order traversal that we have done in trees. It's like a level order traversal. So the element that goes first inside the queue will also come out first. So what we do, we have one node that we know about 0, and we do not know anything about all other nodes. So what we see, okay, we see from the adjacency list what are the neighbors of 0. We see, okay, the neighbors are 1 and 3. So what we do, we pop this out. So this comes out of the queue, and these neighbors are inserted in the queue. So we have 1 and we have 3 in the queue. So once you put any node in the queue, you just mark that node as visited, so that when you come back, you do not insert that node once again in the queue. Okay, so what you will do now is, you will say, okay, I will pop the next node, that is 1. Okay, and what you do next is, you put the neighbors of 1 in the queue. So neighbors of 1, if you see from the adjacency list, they are 0 and 2. Since 0 is already visited, so you skip this and you put 2 inside the queue. So 2 goes inside the queue. So currently your output is 0, and next you pop 1, so your output is 1. And what you do next is, you pop the next node from the queue, that is 3, and you put neighbors of 3 in the queue. Okay, so 3 goes off, and the neighbors of 3 are 2, 0 and 4. So 2 and 0 are already visited, so you just put 4 inside the queue. So your output is now 3. Similarly, you pop the next node, that is 2, and you see there are no neighbors of 2 that are not visited. So 2 is connected with 1 and 3, and both of them are already covered. So both of them are already marked as visited. So you skip them and you go to the next node, that is 4, and you put neighbors of 4 in the queue, that is 5. Okay, so 4 has neighbors 3 and 5. Since 3 is visited, so you just put 5 in the queue, so you get 4 in the output. And you go to next node, that is 5 in the queue, you pop it and you print it, and you put neighbors of 5 that are not visited. So 5 has only one neighbor, that is 4, and it is already visited. So when you put any node inside the queue, you also make it visited, so that we do not visit it again. So this is how you get all the nodes of the graph by using a graph traversal. So this way of traversing the graph is called breadth first search. So you can see you got the nodes at level 0, then you got the nodes at level 1, then you got the nodes at level 2, and finally you got a node which is at level 3. So if we see this we have 0, then we have 1 and 3, then we have 2 and 4, and finally we have 5. So this node is at a distance 0, this node is at a distance 1 or level 1, these nodes are at level 2, and these nodes are at level 3. So since we are getting these nodes level by level, or you can say it's like a level order traversal in a tree, we also call this as a breadth first search. Okay, so in the other traversal, that is DFS, we will see what is depth first search. In that, we basically go deep inside a branch and then we come back. Okay, So that is slightly different from BFS, and that we will discuss in the next video. Okay, so let's discuss the implementation of BFS now. Okay, so let's make a class graph, and this time I would be using a map to make the adjacency list. So I include the header file hash include map, and I want this graph to be of generic type. That means I will define a template class, template type name T, so that I can work with a graph of integers. I can also work with a graph of strings. So this is how we can make adjacency list. So I create a map, let's call it as L, and in this map you can see the key is of the type T. If I say T is an integer, so it will be of the type map of int comma list of int. Okay, so this is not a weighted graph, so that's why I just need to store which node is connected to what all nodes. So this is how I'm storing the key, and this is how I'm storing the value. Okay, so 2 is connected with 1 and 3, so I just put this thing into a list, and the value in the map is key. So this is how we are going to create this map. And next thing that we need to do is we need to write a function to add edges. So void add edge, let's say int x int y, and I'm assuming the edges are bidirectional. Then I can say L of u, L of x dot pushback y, and I can say L of y dot pushback u, pushback x, right? So this is our add edge function, and here we will write the BFS function, and here we will get the source node. Okay, so source is the starting node, so let's assume that this is the source node, and from this node we have to iterate our entire graph. Okay, so as we just discussed, we will need two data structures. One is a queue data structure, because that is needed to do the level order traversal. Another will be a visited array. Okay, so I can just make a map of the type T comma bool. Okay, let's say if there is a node n, then if it is visited, I just mark it as true. So we can make that. So let me make a map of the type T comma int, and let's call this as visited, and let's make a queue of the type T, and let's call it as queue. Okay, so what we will do in the very first step, we will add the node source node in the queue. So I add 0 in the queue, so I can say okay, queue dot push source node, and I also mark this node as visited, because once a node enters the queue, it will definitely come out. So we can just make sure it is marked as visited, and this will help us to prevent that node getting into queue again through some other node. Okay, so visited of source equals to true. So this step is really very important. So what we have to do next is, while some condition, we have to do something. Okay, so what we need to do, we need to remove one node from the queue. So I can say okay, the node I want to remove is given by queue dot front. So that will be of the type T. This node is there, and if we want to actually remove it, we have to call the pop function. Then we have to find neighbors of this queue, or neighbors of this node. So for that we can say for auto int neighbor that is there in the list of node. Okay, so L of node basically gives me the values of that node, and those values contains the adjacency list or the neighbors of that. Okay, so I can say if that neighbor is not visited, so I just check this. If this neighbor is not visited, what I do, I push that neighbor inside the queue. So I say queue dot push neighbor, and also I mark that neighbor as visited. So visited of neighbor equals to true. Okay, so that's it, and now we have to see what should go here. Okay, so this will be nothing but while the queue is not empty. Until we get all the nodes out of from the queue, our traversal is not complete. So that's it, and now we can make our main function and do the traversal. Okay. Okay, so let's see. I have written the main part and I have called the g.bfs function from node 0. So let us see what happens. So initially we have a queue in which we have the node 0 and this is marked as visited, and while the queue is not empty we pop out this node. So node takes the value as 0, this gets removed and we iterate over L of node. Okay, so if you see what are the neighbors of 0, you will get as 1 and 3. Okay, so first you will pick one and then you push neighbor into the queue and you mark this as visited. Okay, and after that what you can say is, you can say visited of neighbor equals to true, that we have marked. So this loop goes on. So what we do next, we go to the next neighbor, that is 3, and we say this is not visited, so we also add it into the queue. So this is also added in the queue. So now you pop out the next node, that is 1. So node takes the value 1 and then you say okay for neighbor that is in L of node. So now node contains 1, so L of node means it contains the value 2 and 0. So since 0 is already visited, you do skip this and you take out 2 and you push 2 in the queue. So this is marked as visited and you don't have any more neighbors for 1, so this loop is over and you come back here. So you pop out the next node, that is 3, and you see what all neighbors are not visited. So you see 4 is not visited. Okay, so 3 has neighbors 3, 0, 4, 0 and 2. So you pick 4 and you add 4 in the queue. Okay, and you also mark 4 as visited. After that you say okay we go to 0 but it's already visited, we skip this. We go to 2, it's already visited, we skip this. So we pop out 3 and we print. Next we pop out 2 and 2 has neighbors as 1 and 3 but both of them are already visited, so we skip this. We pop out this and next we go to 4 and 4 has a neighbor 5 which is not visited, so 5 goes into the queue, it comes out, and finally 5 will come out and queue will become empty and 5 will have one neighbor that is already visited. So you may get this of particular order 0, 1, 3, 2, 4 and 5. So let's run our code and see what we get. Okay, so let me just run /bfs. Okay, so one thing I just forgot is I should also add a cout statement here. Okay, so cout node that will print the node and I can build the code and we can just ignore this warning and let's run the code. Okay, so we get 0, 1, 3, 4, 5. That's also fine. It will the order will also depend upon in which order you have added these elements in the adjacency list. Okay, so if 1 has 3 as the neighbor or 0 has 3 as the first neighbor, so there may be slight change in the ordering, but this order is also fine. Okay, so this order basically depends upon the order in which you have inserted the elements in the adjacency list. But you can see we are able to traverse the graph and we are getting all the nodes 0, 1, 2, 3, 4, 5. So it's going to 0 to 1, 1 to 2 and 3, 4 and 5. So perfectly fine, and I hope you understood the concept of BFS. Hi everyone, in this lecture we will see how we can use BFS to form a single source shortest path algorithm. Okay, so what is the meaning of single source shortest path? So let us first see what is this. Okay, so single source shortest path means starting from a single source. Let's say any node can be a source. Let's assume that this 0th node is the source. You want to find out the shortest path or the distance to all other nodes in the graph. Okay, so I'm interested in learning what is the shortest path from 0 to some other node, that is, let's say, destination. Okay, so or you can just call this as a source node. So this destination can be all other nodes in the graph. So I may ask, okay, what is the shortest path from 0 to 5? So one path is, okay, from 0 you go to 1, and from 1 you go to 2, from 2 you go to 3, and from 3 you go to 4, and from 4 you go to 5. But a shortest path would give you something like this. You go from 0 to 3, and from 3 to 4, and from 4 to 5. So obviously this is the shortest path. So now if you see this carefully, we have discussed that BFS gives us the level order traversal. That means we are going to visit all these nodes level by level. And also, if you observe carefully, the distance calculated by the level order traversal is the shortest. Okay, so I'm making a statement: distance calculated by level order traversal is the shortest. Okay, this is actually the shortest distance if the graph is a unweighted graph. Okay, so here we have an unweighted graph. That means all edges have the same cost, or all edges have the unit cost. Okay, so this might not be the case if you have weights in the graph. For example, this edge is having a different weight than this edge. In that case, we use a different algorithm that's called a Dijkstra's algorithm. But in this case, since this all edges have the same weight, so what you can see this, if I just modify this graph little bit, or if I just change the way this graph looks like. So we have 1, we have this 2 which is connected here, and here we have 4, and here we have 5. So if you carefully see, so how does BFS proceed? So it starts from the root node and it tries to cover all the nodes that are in the next level. Okay, from 0 we go to 2 nodes that are 1 and 3. And if you see, if you just treat it like a fire that is spreading across these ropes, so you will find that 1 will discover 2, or 3 will discover 2. Okay, so at t equal to 1, or at level equal to 1, you will discover the nodes 1 and 3, and at t equal to 2, or the level equal to 2, you will discover the next node, that is 2. And since 2 is already discovered, so 3 may not discover this node, but in the same time 3 can discover another node, that is 4. So 3 can go to 4, and at this also we will reach and t equal to 2. Okay, so what happens is from 0 you go to 3, and from 3 you go to 4, and from 4 you can easily discover 5, and you can say t equal to 5. So this is what we have seen. Okay, so what actually happens is, if you talk about 5, who discovered 5? We know 4 discovered 5. And who discovered 4? We know 3 discovered 4. And if we know the shortest path to 3, we also know the shortest path to 4, and we also know the shortest path to 5. So what happens is, you are basically interested in finding out now what is the shortest path to 3. So one way is you can come via this path, and another way is you can come via this path. So obviously the path that is smaller will be discovered first in level order traversal. This we can say because this is a unweighted graph, and this will be true in this case. Okay, so what you need to do, if you need to find the shortest path to any other node, you need to when you are visiting any node. Okay, so the very first time when you are visiting any node, that path is going to be the shortest, because if you come via some other path maybe little later on to this particular node, it will obviously take more time. So if I do a BFS from this node to, let's say, discover this node, in the first step I will discover this, in the next step I will discover this, and similarly if this goes on parallelly, in the first step I will discover this, and in the second step I will discover this, in the third step I will discover this, and in the fourth step I will discover this. So obviously the very first time a node is discovered, that will be the shortest path to that particular node. So this is what I am trying to say, or I can say the level of that node is basically the distance of that node from the source. So this we can do for all the nodes. So we can run a BFS, and the level of that particular node will be the shortest distance. So what changes we need to make in this code is, we just need to update distance of a node. For example, if you go from a node X to node Y, and if you see this X has a distance D, then Y will have a distance of D plus 1. That's it. Okay, and if a node is already discovered, if a node, let's say there is some other node, and for this node the distance is already known, let's say this distance is d dash, then from y to this particular node, if there is an edge, you do not need to update this particular distance. So that distance is smallest when the node is discovered for the first time. So that's it. Okay, so let's try to make some changes in the code, and then we will try to print out the distances as well. Okay, so I will also dry run the code so that things become more clear to you. So we have 0, we have 1, we have 2, we have 3, and we have 4, and we have 5. So what now I'm going to do is, I'm going to say distance of source node from itself is going to be 0, and for all other nodes which are not discovered, I'm going to say this distance is going to be infinity. Okay, so what I will do here, I also need to maintain two things. One is whether that node is visited or not, and second, what is the distance of that particular node. So what I can do is, I can just maintain one hash map that basically stores that whether that node is visited or not. So I will make a map of t comma int. Okay, so earlier this could be a boolean value also, but I just made it an integer. So instead of storing true or false, I can actually store distance. Okay, so visited of source will be 0. In the beginning, the source node will have a distance of 0, and all other nodes will have infinity distance. Okay, so that is int max. So I can just iterate over all the nodes in the graph. So for auto, t node that is there in the adjacency list. Okay, so adjacency list will give me pair, that is the key and the values. So node pair that lies in the list L. So I can say okay, so my node will be, so let me say this will be auto. So node will be of the type t, and this node will be equal to node pair dot first. Okay, and I can say visited of node equals to int max, or let me just call this as distance array. So distance of that particular node is int max. That means that node is having infinite distance. Okay, so that's what we do. We basically in your adjacency list, okay, you have something of this form. You have 0 followed by a list, 1 followed by a list, and 2 followed by a list, and so on. So I say okay, node pair. So node pair contains these two things. Okay, so if you just want to get the name of the node, that is node pair dot first. So this is the first component. Okay, so similarly we iterate over all the nodes, and we say okay, distance of that particular node is infinity, and actually we should do this step here. Okay, except for the source node, all other nodes should have infinity, and then we override the distance of the source node as 0. Okay, and that source node is added to queue, and in this case, at this particular point, we can check if distance of neighbor is not equal to int max or is equal to int max. That means you are visiting that node for first time, so you push that node into the queue, and you also update the distance of that particular node. Okay, so distance of neighbor will be equal to distance of parent, the node that discovered this. So it's a child of node plus 1. That's it, and that's the only change we need to make in the algorithm. So let me dry run this code so that things are more clear to you, and this will actually help us to find the shortest distance to every node. So here I just remove the cout statement. I'm not going to print the traversal, but what I can do is I can print the distance to every node. Okay, so I can say okay, for auto node pair in L, I can say okay, my node is of the type T, that is node pair dot first, and the distance to that node is, let's say, int d, that is equal to distance of node, and I can just cout node is node, and this is at a distance d from the source. Okay, so that distance is going to be d. So that I do for all the nodes in the graph. Okay, so let's first try to run this code. Okay, so it says node 0 is at a distance 0, that's fine. Then we have node 1 that is at a distance 1, fine. We have node 2 at a distance 2, fine. Node 3 at a distance 1, fine. Node 4 at a distance 2, that is fine. And node 5 at a distance 3. So that means this is correct. Okay, so now let me give you a quick recap of what we have done in this problem. Okay, so we are doing the same BFS operation, but this time we are saying, okay, in the queue first I will add the source node, that is 0, and I say okay, 0 has a distance of 0. So then from 0 I know I can go to 1 and 3, so I put them in the queue. And I also know distance of 1 and 3 is initially infinity. Okay, so what I do, I mark this as visited and I set this as distance as 0. So this distance will not be int max again, and it won't be added back to the queue ever again. Okay, so I add 1 and 3, and at the same time I update distance of 1 as distance of parent. Okay, so distance of child is updated as distance of parent node, that is 0 node plus 1. So this distance becomes 1, and similarly this distance becomes 1. Okay, so you can say you from 0 you are able to traverse to 3, and you are also able to traverse to 1. So that's how. Okay, so you treat it like a fire that is spreading from 0 to the neighboring nodes. So you have reached 3 and you have reached 1, and both of these nodes took a distance of 1. Okay, so 3 has a distance 1, and you pop out 0 from the queue and you pick the next node. So next node is 1, and you pop out 1 and you try to reach the neighboring nodes. So from 1 you can only reach 2, and you say okay, distance of 2 is distance of parent plus 1, so this distance now becomes 2 instead of infinity, and 2 is now added to the queue. So 2 has a distance of 2. Okay, so now next node that you pop is going to be 3, so you remove 3 from the queue, and you see okay, from 3 you can go to 2, but 2 is already visited. 2 does not have a int max distance, so you do not go to 2. Now you pick the next neighbor of 3, that is 4, you go to 4, and you say okay, from 3 I am coming to 4, and this distance should be equal to, it should not be infinity, it should be distance of 3 plus 1, that's 2. Okay, so this distance is updated as 2, and 4 is added to the queue. Okay, next you pop 2, and from 2 you cannot go to any other nodes, you go to the next node now, and from 4 you can go to 5. Okay, and you say okay, distance of 5 is now not infinity but it is 3, that's what you do, and you add it to the queue and you pop 4 in the, okay, so 4 is already popped and 5 is added to the queue. So you know distance of 4 is 2 and distance of 5 is 3. So finally 5 is popped, and from 5 we cannot go to any other location. So this is how we get all the distances. Hi everyone, in this video we will discuss another problem, that is snakes and ladder problem. Okay, so in this problem you are given that there is a board which looks something like this, and in this board you are given there are, let's say, s number of snakes, and let's say there are L number of ladders. Okay, and you're also given the starting and the ending point of all the snakes. For example, this particular snake starts at 12 and it goes till 34. So this snake is from 12 to 34. This is snake 1, and let's say this there is a snake from 4 to 17. So there is another snake, and similarly you have different ladders. For example, there is a ladder from 2 to 15. So there is a ladder from 2 to 15, and there is a ladder from 18 to 29, and so on. Okay, so the rules of the game are very simple. It's just like the normal snakes and ladder game, but you are standing at this point, you are at 0, and you want to reach the destination, that is 36. So you want to know what is the minimum number of dice throws required to reach the final destination starting from the source. Okay, and we also need to print the shortest path that we can take to reach the destination. So a dice is just like a regular die, and you will have numbers from 1 to 6 on this die. Okay, so you can get anything between 1 to 6. So what you can do is you can actually control the movement of the die. Okay, so if you know the path, you can say, okay, I will throw a 6, I will throw a 5. So it's not a random die. It has a deterministic outcome. That means you can determine what number to throw, and accordingly you can choose a path, and you can pick it, and you can reach the destination using minimum number of moves as well. Okay, and there is no double turn on getting a 6. Okay, so there will be single turn every time. So what happens is, let's see. So first of all, does this problem look like a graph? Obviously yes. Okay, and if we talk about, okay, if this is a graph, then what vertices we have? So obviously every number in the this is every number is a node or a vertex. Okay, so we have vertices numbered from 0 to 36. So in all we have 37 vertices in the graph. Okay, and what about edges? So how many edges we have in the graph? So this is little tricky. So if you think very closely, you can see one is actually connected with two, because if you throw a one here, um, if you throw one here, you can end up at 2, but from 2 you can take a letter and you can jump to 15. So effectively 1 to 15 is a single edge. Okay, similarly from 1, if you throw 2, you can end up at 3. You can say, okay, there is an edge from 1 to 3, so 1 to 3 is an edge. Okay, similarly 1 to 4 is an edge. Okay, and similarly 1 to 5 is an edge, but 5 is connected with 7, so there is an edge from 1 to 7. So 5, at 5 we do not stop. Okay, and there is an edge from 1 to 6 as well if you throw a 5, and if you throw a 6 you end up at 7, so there is an edge from 1 to 7. Okay, and similarly you can see there is an edge from 2 to 3, there is an edge from 2 to 4, there is an edge from 2 to 7. So from every node I, so every node numbered I, you have an edge to I plus 1, you can have an edge to I plus 2, up to you can also have an edge to I plus 6. But what will happen is, if you reach this particular node, and that particular node can have something like a snake or a ladder. Okay, that's what you can have. So what you can do is, you can say, okay, I may get a jump. Okay, let's say you will get some jump. So that jump can be positive if there is a ladder, and that jump can be negative if there is a snake. For example, suppose you somehow reach, you are at 12, or let's say you are at 16, and you throw a 1, so you end up at 4. So that's what will happen. Okay, so what I can say, there is an edge from the node 16 to 16 plus 1 plus some jump. Okay, so that jump can be calculated by knowing if there is a snake that ends up at the location 17. So I can make a array, and let's say this is called a board array, and I can say board of 17 will give me a negative jump of minus 13. Okay, so that means if I end up at 17, I will get a jump of minus 13. So I will add this value, that is minus 13. So it will actually create an edge from 16 to 4. So you can see there will be an edge from 16 to 4. So similarly, I can say a board of 5 will be 2. Okay, sorry, board of 5 will be 2. That means if I end up at 5, I will get a jump of 2. So I can say if there is an edge from let's say 4 to 5, but I can say this will be actually 4 to 4 plus 1 plus the board value at 5. That means if I get any jump at 5 or not. Okay, so that is 2. So that means it will help me to make an edge between 4 to 7. So you can see this is a edge. Okay, now you may ask, if this is a weighted graph or it is an unweighted graph. Okay, so what do you think? Is it a weighted graph or an unweighted graph? So clearly it's an unweighted graph. Every edge has the same cost, and that cost is nothing but equal to one dice throw. If we want to go from one node to the neighboring node, we actually need one dice throw. The distance between those two nodes does not matter because the question says minimum number of dice throws. So if you want to go from 1 to 3 or if you go from 1 to 5, this will be only one edge. Okay, so now this problem is now reduced to a problem in which you are given an unweighted graph and you want to find out the shortest path from source to destination. Okay, so source is 0, destination is 36, and you know how to construct the graph that we can actually do. So we can say we will make a graph and we will add all edges to the graph. Okay, and after that we can run the shortest path algorithm using the BFS single source shortest path, and that will actually help us to find the shortest path from 0 to the destination. Okay, so let's try to build some code, and then but before that we need to build the graph. Okay, so firstly I'm building a board array. So that board array I have calculated from the input. So I have hard coded this board array, but you can just calculate the board array. So initially you can say all values are zeros. Then if you get the locations of snakes and if you get the locations of letters, then you can say, okay, if there is a snake, if there is a letter that starts at index 2 and it ends at an index 15, then board of 2 will be 15 minus 2, that is a jump of 13. Okay, so that means if you connect 1 with 2 and 2 has a letter to the index 15, so what you will do, you will say, okay, from 1 there is an edge to 1 plus 1 plus. Okay, so 1 is where you are standing, 1 is what you throw on die, plus if there is a letter then this value will be non-zero. Okay, so this value will be 13. So from 1 you can end up at, let's say, 15. Okay, that's what we are doing here. Okay, so from 1 you can actually end up at 15 in just one step. So there is an edge between 1 and 15. So then what I need to do, I need to add all edges to the graph. Okay, that's what I need to do. So we need to construct a graph. Let's say we have a graph G, and here, okay, so we are using a map, that's fine. So we can say for int I equals to 0, I less than 36, I plus plus. I can say for at every I can throw a dice between 1 to 6. Dice equal to 1, dice less than equal to 6, dice plus plus. Okay, so from ith node I can go to a jth node. So I can say int j equals to I plus dice plus something. Okay, so that will be board of the location where I have reached. So j will be equal to j plus equals to the jump that is given by board of j. Okay, so that's what I do, and I can check if this j is less than equal to 36, because in my current example I have only 36 nodes in the graph. So I can say g dot add edge from I to j. Now you may see that these edges are directed edges. Okay, so these are unweighted edges, but they are directed edges. That means if there is an edge from 1 to 5, there is not an edge from 5 to 1. So I will remove this statement here. Okay, so that we can just make a single edge from x to y. That's what we do. Okay, and we also need to modify our BFS function little bit so that we get the shortest path to the destination node. So we need to give source and we also need to give destination. So instead of printing shortest path to every node, I can just print the shortest path to the destination node. Okay, so here I can say to destination node, and I can say okay, let's return the distance of destination, and here we should accept the destination. That's it. That's a warning. Looks fine. Okay, so let's try to run this code. So warning we can ignore. I think that's what we need to do. Okay, so the single source shortest path algorithm will remain same, because that actually requires a graph, and in this problem we just needed to construct a graph. So we have this dot slash bfs underscore snakes. This file is okay. There is one error. Okay, so let me see what's the error. Template is declared here. Yes, so this graph is of integers. That's what we need to define. Okay, I have made small change. I am printing distance to all nodes, and I'm also returning the distance to destination. So I was just debugging this code, and let me show you what happens is, so if I see the output, I'm actually getting the shortest distance from 0 to all other nodes, and in some cases this distance is infinity, which means those nodes are not reachable. Okay, because 2 has a ladder, and if you throw a dice from 0 to 2, you end up at 5. You do not reach 2 in any way. So those nodes which are not reachable, or at those points where we cannot stand, those have a distance infinity, and we are actually getting distances till 35, but we want the distance to destination 36, which is coming out to be 0. So that is happening because we have not added any edge. Okay, we are not added any edge of this form where I is equal to 36. So we actually had done this thing. So we had done this thing. Okay, we have I less than equal to 36. So in this case, when I is equal to 36, we will have the value of j, which will be at least 37. So that means this function will not be called when the value of I and j I is 36. Okay, because j will have a value at least 37. So that means graph does not know that a node 36 exists. So this is a problem. So in order to fix that, you can call a function like this, g dot add edge, and you can say 36 comma 36. So this will actually tell the graph, okay, there is a node 36 in the graph, and we have to consider that. Okay, so let me build the code again, and let's try to run this. Okay, and yes, now you can see we are getting distance to the node 36, and this distance is 4. So that's what I just debugged, and I will now remove this, build the code again, and you will see the distance to the node 36 is 4. So that means 4 dice throws are enough to reach 36, and we can also verify from the graph. So what we can do is we can throw a die, and we can go from 0 to 15. That's the first throw, and from 15 we can go to 29. That's the second throw, because if you throw 3 here, you end up at 18, and from 18 you climb a ladder, and from here if you throw 1, you end up at 30, and from here if you throw 6, you can go to 36. So that's 1 2 3 and 4. Okay, so what we can do is we can also print the path. Okay, so it says find the shortest path as well. So what we can say is we can say, okay, if we are at 36, we can try to find the parent of 36, that is 30. From 30 we can find the parent, that is 29, and we can just backtrack and let's say it's 15, and this parent is 1 or 0. Okay, so 1 2 3 and 4. So we can just backtrack and try to print this particular path. Okay, so not necessarily backtracking is not the right word, but we can backtrace the path. Okay, so for that what we need to do, we can keep another array or another hash map that basically stores the parent of every node. Okay, so it will be of the type t comma t. If the node is t, the parent will be of the type t. Let's call this as parent, and we can say parent of source is source itself. Okay, here we should say parent of source is, let's say, source itself, and every time you are updating a node, you also update the parent of that node. Okay, so parent of neighbor is nothing but the node. And finally, when you have computed all the distances, you can path the you can find the path from destination to source. So you can say you have a temporary value that is equal to destination, and you can say while parent of temp is not equal to itself. That means while we have not reached the source node, or let's say while temp is not equal to source, that's also fine. Okay, what we can do, we can say cout destination followed by an arrow. Okay, or for let's say cout temp followed by an arrow, and we can update temp as temp equal to parent of temp. So from that node we go to parent of that particular node, and this keeps on going while we have not reached the source node, and finally we can just print out the source node and handle. So let me tell you what we are doing here is, let's say you are at 36, that is your destination. You say, okay, in the parent array of 36, it is stored that you came from 30. So temp goes from here to here. In the parent array of 30, it is stored it came from 29. So you go back here, you print it. Here it is stored you came from 15. So you go back here. And here it is known you came back from 0, that is the source node. And while temp is not equal to source, while temp is not equal to source, you keep on printing, and finally you also print the source. So ideally this should work, and let's try to build and run this code. So yes, you can say it's working from 0, 15, 29, 30 and 36, and you get the shortest length as 4. So that's all. I hope you understood the. Hi everyone, in this lecture we will talk about depth first search, or DFS as it is called. Okay, so it's another way to traverse the graph, and it's very simple. Okay, so what this method suggests is that you start from a node. Let's say we start from 0. It says you go to any neighboring node that is not visited. So let's say from 0 we can either go to 1 or we can go to 3. So let's assume we go to 3, and it says you repeat that process. So now you are at 3, you will still do the same steps. Go to any neighboring node that is not visited. Now you can go to 2 or you can go to 4. Let's assume we go to 4. Okay, and you again repeat the same step. So you, out of all the neighbors of 4, you pick any one node that is not visited and you try to visit that. So there is only one node, that is 5, and you go to 5, and you still again find a node that is not visited. Now you see all the neighbors of 5 are visited. So what you do, you come back. Okay, and at 4 you try to find a neighbor that is there and that's not visited, but still at this, in this graph we don't have any neighbor, but maybe if we had a neighbor n, we would have come to that neighbor and then we could have returned back. Okay, and from 4 you again return back. Now at 3 you again try to find a neighbor that is still not visited. So you find a neighbor 2, and at 2 you find a neighbor that is not visited. You go to 1 and you try to find a neighbor that is not visited. So 1 has a neighbor 0, but 0 is visited, and so you try to go back to 2, and from 2 you go back to 3, and from 3 you go back to 0 again. Okay, so this is how we have traversed this graph. So the output would be 0, 3, 4, 5, and then it will be 2 and it will be 1. So this is what a DFS traversal looks like. There can be multiple ways, there can be multiple paths you can get. So maybe if in the adjacency list, if 1 is the first neighbor of 0, okay, so 0 can have a neighbor as 3 or 1, but if 0 has a neighbor 1 and 3, then the first call would be made on 1, and when 1 can make a call on 2, 2 can make a call on 3, 3 can make a call on 4, and 4 can make a call on 5, and from here we can come back. Okay, so it's a recursive process. So you go to next node, and finally you end up in deep inside a branch. Okay, so you can see from 0 you ended up in at 5, and from 5 you are backtracking and you're coming back through the same path. Okay, so that's why it's called depth first search. Okay, so this is what DFS is, and let's see how we can implement a DFS function. Okay, so let's try to implement a DFS function. So what we need to do in this function is we again need to maintain a visited array. Okay, so since we are using a map, because we do not know what type of data we will get, so this data can be int, this can be string, this can be a custom node also. So I can just maintain a map of the type t comma bool, and let's call this as visited. And what we can do, we can mark all the nodes as not visited in the beginning. Okay, so that will help in two steps. Two things: one, all the nodes will be added to the map, and second, we can um, mark them as unvisited. Okay, so that's what we can do in this step. So let's iterate over all the nodes. For auto some pair p, that's there in the map L, so we can say node is p dot first, and we can say visited of that node equal to false. Okay, now this function is going to be a recursive function, but this initialization that we are doing should be done only one time. So what we can do is we can make a helper function. Let's call it as DFS helper, and this function gets the source from where we want to start the node, start the DFS call. So maybe we have the first node, let's call that as source, and we also should pass this visited array. Okay, so we can say we are getting a map of the type t comma bool, and it's visited, and since this map should remain same in all the function calls, we must pass it by reference. We should not make a copy of the map because it should be common for all function calls. So we have a function DFS, we have a function DFS helper. So DFS helper is the recursive function that will traverse the graph. Okay, that will traverse the graph. So what you need to do, so you're given, okay, you are standing at source node, so what you will do, you will just print out that particular node. So you can just see out source, that means you have visited that node, and what you need to do, you need to go to any neighbor of that node that is not visited. Okay, so instead of any, we should actually go to all neighbors of that node, but one by one. Okay, so let's iterate over neighbors of that particular node. So for t type neighbor, that's there in list of source, we can say if not visited neighbor. Okay, so then we will visit it. So how do we will visit it? We will use recursion. So we can call this function DFS helper, and here we can say, okay, go and visit the neighbor given the visited map. That's it, and that should do the work for us. Okay, so let us first try to run this code, and we have given the source node as 0, and we should also call the helper function. So I can say dfs helper of source and visited. Okay, so let me explain you the control flow once. So from the main we are making a call to this. So from the main we make a call to this function dfs. The goal of this function is just to create a visited array and mark all the nodes as false in the beginning. Also, okay, we forgot to add one step, that this node is visited, so visited of source should be equal to true. Very important step. So whenever you're coming to a node, you must mark it as visited. Okay, so let's see. From the main we call this function dfs, and from that dfs we make a call on dfs helper, and from here the recursive calling starts. 0 1 2 3 4 and 5. So let's see the output first, and then we can go through this once again. So dot slash dfs. Okay, build the code. That's fine. So it says 0 1 2 3 4 5. So 0 1 2 3 4 and 5. That's perfectly fine. So now let's see how this code works. Okay, so let's just have a look. Okay, so we maintain a visited array. Let's say this is a visited array, or it's a visited hash map. So initially nothing is visited. Then we start from 0. We say okay, 0 has a neighbor 1 that is not visited, so we see out 0 and we mark that as visited. So 0 is visited. So for all the neighbors of 0, we say okay, if we find a neighbor, so 0 has neighbor 1 and 3, we see if 1 is visited. No, it's not. Let's go and visit 1 by using this function. So we come to 1 and this starts a recursive call. So we see neighbor of 1, that's 2, that's not visited. So we come to 2 and we say okay, let's go and visit 2, and 2 sees okay, there is a neighbor 3 that's not visited, so let's go to 3 and visit it, and 3 says okay, there is a neighbor 4 that's not visited, so we go to 4. 4 sees okay, there is a neighbor 5 that's not visited, so we go to 5. And 5, at 5 you see okay, 5 has a neighbor 4 but it's already visited, so you just return from here. It does not do anything. And since the previous function call was 4 at 4, so from 5 we return to 4. At 4 we say okay, this for loop 4 had two neighbors. 4 had a neighbor 3 and 4 had neighbor 5. So 3 was already visited, 5 is now visited, so we just return back to the previous function call, that is 3. And 3 says okay, I have a neighbor 2, I have a neighbor 0, and I have a neighbor 4, but all of them are visited. So this for loop does not execute for 3 and we come back to 2, and same goes again, we come back to 1, and finally we end up at 0. So you can see there is a stack formation like this: 0 1 2 3 4 and 5. So we go deep inside a branch, and then one by one these frames are popped from the stack, and eventually we end up at this particular point. Okay, so this statement is executed when that node is visited for the first time, and when we are coming back, we do not print it again. Okay, so that part is basically here. So this is what depth first search is, and I hope this solution is clear. It's a very simple and a small solution, just a recursive function that we are making, and the visited array is needed because we just want to make sure that we do not get stuck in a cycle inside the graph. Okay, hi everyone, in this video we will discuss what is a connected component. Okay, so let us first discuss this term connected graph, and let me draw a graph. Okay, so let's say you have a graph like this: 0 1 2 and 3. Okay, and I can say this is a connected graph because uh, in a connected graph, if you start from one node, it is possible to traverse all other nodes of the graph by starting from any node. Okay, so you start from 2, you can definitely reach 3, you can reach 0, you can reach 4 as well, and you can reach 1 as well. So you can traverse all the nodes of the graph starting from any given node. So such a graph is called a connected graph. But it is possible that your graph might be split into multiple components and those components are connected. For example, this graph, this is a single graph and this has 7 nodes or 8 nodes, let's say. Yeah, 4, 5 and 3. Yes, so it has 5 plus 3, 8 nodes, but it is a single graph. Okay, for example, if you talk about a country like India, you can see different regions of India are connected through roads, but there are some islands which are not directly connected with roads, but they are part of India. Okay, let's say Andaman Islands, they are part of India, but they're not directly connected. So we can say, okay, India is split into two connected components. These islands are connected with each other and they are not connected directly with India. Okay, maybe you have to take a flight to reach these islands. So given a graph like this, we are interested in finding out how many components this graph has, how many connected components are present in the graph. That's what we want to do. So can you think of any algorithm that can achieve this? So okay, let me give you a hint. So think in terms of graph traversals. Okay, so what will happen if you let's say if you know one node, or if you know, okay, these are the nodes in the graph. Let's say you know there are nodes from v number of vertices in the graph, 0, 1, 2, 3, 4 and 5, 6, 7. So if you know, okay, there are let's say 7, 8 vertices in the graph, and you say, okay, I will start traversing my graph from a given node. Let's say you start traversing using BFS or DFS. So any traversal you can do, either you can do BFS or you can do DFS. So let us assume we are doing DFS, and maybe I go through these nodes. I go to 0 to 1 and I go to 2, I go to 3, and at 3 I see, okay, there is no node where I can go, so I come back to 0, and at 0 I see, okay, there is a node 4 where I go and I come back to 0. So what will happen is, during this traversal I can mark what nodes I had visited. Okay, so I visited 0, 1, 2, 3 and 4. Now what you can do, out of the nodes which are yet to be visited, you can pick one node, any one node, let's say 5 or 6 or 7. Let's say we pick 5, and you again start traversing the graph from that particular node. So it will visit 5, 6 and 7. So that means they are visited. Okay, so that means you need to make two DFS calls. So one DFS call you make 0 as the source node, and another DFS call you make 5 as the source node. Okay, and to identify what calls we need to make, we need to iterate over the array of all vertices or a list of all vertices, and we can check, okay, if there is a node that's not visited in the previous call, we can start a DFS call from that and that will visit the component in which it is present. Okay, and maybe if you have something like 8 here, and that 8 will be visited in the third call, and that can be done. Okay, so maybe you make another call as DFS of 8. So clearly you can come to know, okay, there are 3 components, and you also come to know what nodes are present in each component. Okay, so that's what forms a DFS forest. Okay, so each traversal of the component gives you a DFS tree. Okay, so why I'm calling this as a tree, because when you do DFS, you actually get a tree, you don't end up getting a cycle. Okay, so when you traverse the graph, this edge is not traversed, you cover these 3 and you cover this 3. So this is like a tree. So when you have multiple DFS trees constructed from a graph, you can also call this as a DFS forest. So what is a forest? A forest is nothing but a collection of trees. Okay, so forest is a collection of trees. So let's try to implement this algorithm to find connected components in case of a undirected graph. So we are assuming our graph is a undirected graph. Okay, so now I will make some changes here. So let's say this function is called DFS. Let's just say it's DFS, and we can take the source node or we can skip that. That's totally our choice. So maybe let's skip that. And here we do not give any source node because we want to print all the components of the graph. Okay, so here what we can do, we can iterate over all the vertices and initiate a DFS call if a vertex is not visited. Okay, initiate a DFS call. So I can say for int I equals to 0, but here I should know the vertices. Okay, so if you have integer vertices, you can put something like this and you can make a call. But what will happen is, if you do not know what all vertices are present in the graph, for that you need to use a loop like this. Okay, so I can say for auto pair that lies in the adjacency list. So I want to get the node that is given by p dot first, and I can say, okay, if the node is not visited, then initiate a DFS call from that node. So I can say DFS helper from that particular node, and I pass the visited array. So as a result of this, you will get explore the first component, and due to this loop you will get the next component, and so on. So you can just see out you are in the component, and yeah, here you can say count equals to 0. That's the component ID, and here you can say count, followed by you will get the nodes. Okay, so you will get the nodes that are there in the component, and you can say count plus plus. Okay, so let's try to make this graph. Okay, so let's say g dot add edge 0 to 1. Okay, so I have added all the edges, and now let's try to run our code and see the output. Okay, so you can see we are getting component. Okay, count is not incremented. Sorry, this count should be declared outside here. Okay, you can see component 0, it has 0 1 2 3 4, component 1 that has 5 6 7, and component 3 or component 2, you can say, that has only one node, that is 8. Okay, so I hope you got an idea how we can find connected components using DFS. So that's it. You can also use breadth first search because any traversal will work in this case. Okay. Hi everyone, so we will discuss this problem, journey to the moon from Spodge. So in this question you're given, UN is planning to send two people on the moon, and these two people should be from different countries, and in the input you're given list of pairs of astronaut IDs. Each pair is made up of astronauts that belong to the same country. For example, you are given 1 and 2, they belong to the same country. You are given 2 and 3, they also belong to the same country, and it is also given that the IDs are numbered from 0 to p or 0 to p minus 1. Okay, so you can see there is also an astronaut 0 which belongs to a different country. Okay, now if you want to find out number of ways in which you can choose two astronauts and they should be from two different countries. Okay, so determine how many pairs of astronauts from different countries they can choose from. Okay, so if I treat this as a one country and if I treat this as another country, I can make pairs like this: 0 comma 1, 0 comma 2, and 0 comma 3. Okay, so obviously we can make three pairs. Okay, so there are three pairs to choose from as given in this example. So let us see one more test case. So each line contains two integers n and p. So first is the number of astronauts. Okay, and second is the number of pairs. Okay, so p is the number of pairs. So astronauts are numbered from 0 to n minus 1. That means you have n astronauts, and p is the number of pairs. For example, you have 5 astronauts, 0 1 2 3 4, and there are 3 pairs. So you can take 3 pairs as input. Okay, so first pair says 0 and 1 are astronauts that belong to the same country, so that we know there is a relationship between 0 and 1, that they belong to the same country. Then we have 2 and 3, they also belong to the same country. Okay, so 2 and 3 are connected, and 0 and 4 belong to the same country. That means 0, 4 and 1 are actually connected. Now you can see, if we do a graph traversal to find out connected components using BFS or DFS, we will get two components, and during the traversal we can also find out the size of each component. Okay, so that can be easily done using DFS. You can make a function of the type int DFS, and here you give id of some node from which you want to traverse, and this can actually return you the size of that component. Okay, so let us assume we are able to build such a function that traverses a component in the graph, or that gives us the size of the tree in the graph. Okay, so this is we will let's say we start from traversing from 0, we go to 4, we say okay, size of 0 is 1, we go to 4, we come to know 4 is also 1, and 4 returns 1 to it, so we make the size as 2, and we make a call on 1 and it returns 1, so we make the size as 3. Okay, so this component returns you a size of 3, and similarly this component returns you a size of 2. Now how do you do it? Okay, how do you find out the number of pairs? So that is going to be pretty easy. So what you can do, if suppose you have country 1, country 2, country 3, country 4. Okay, so let's say it has 5, size of 5, it has size of 3, it has size of 2, it has size of 4. So what you can do, you can pick two countries first. Okay, you can pick any two countries, and then you can find out ways to calculate astronauts. Okay, for example, if you have k number of countries, okay, then you can say okay, if I pick C1 and C2, I have these many ways. If I pick C1 and C3, then I have these many ways. If I pick C1 and C4, then I have these many ways. So if you have k countries, you have kc2 options to pick two distant countries, and then you can find out how many ways are there to pick astronauts from those countries. Okay, but this is going to be little complex while implementing, and also kc2 is going to run in order of k square, and then you can find out the number of astronauts. Okay, but what we can do is we can actually simplify this. We can say, let us find out the total ways in which we can send any two astronauts. Okay, any two astronauts, irrespective of they are from the same country or from the different country. Okay, so total number of ways to send astronauts will be 5c2, and from that you subtract the ways in which both pairs of astronauts are from the same country. Okay, so that will basically give you the number of ways in which the astronauts are from two different countries, so both pairs are from same country. Okay, so if you have two countries in this example, so what is the number of ways in which both astronauts are from the same country? So if they're from country 1, so it will be 3c2 ways. Okay, so out of 3 you pick 2, so minus 3c2, and in this case it will be 2c2, so minus 2c2. Okay, so 5c2 is 10, 3c2 is 3, 2c1 is 1, so it turns out to be 6. Okay, so we will actually simplify this by using this. Okay, or if you want to try out using this option, so this will also give you correct answer. So you have two countries in this case, so if you choose one astronaut from country 1, so that is 3c1, and if you choose one astronaut from country 2, that will be multiplied by 2c1, so it will be also 6. But again, this one is going to be more efficient in terms of time complexity also. So the formula is going to be nothing but nc2, n is given in the question, minus summation over all country sizes ci c2. Okay, so this you can easily find using DFS or BFS. So you need to traverse each connected component in the graph and find out its size. So that size is s of I. Okay, the size of the ith country. So I hope you will be able to implement this question, and you would be able to submit it as well. So that's all for this video, and thanks a lot. Hi everyone, so now we will discuss very interesting problem from Spoj. It's called HOLI, or Holiday Accommodation and Sort. It's a problem from ACM ICPC regional contest, and let's go through the problem statement line by line. So it says people have many ways to save money on accommodation when they're on vacation. blah blah. One of these ways is exchanging houses with these people. Okay, so there are some people who want to exchange houses when they go on vacation. So there is a group of n people who want to travel around the world. They live in different cities, so they can travel to some other people's city. Okay, so people want to move from one city to another and use a temporary house, and they want to make a plan and choose a destination for each person. Okay, so there are two rules which need to be satisfied. All the people should go to one of the other people's city. That means no one is going to stay at home, and two of them never go to the same city. Okay, that means a single traveler will go to another city, and no other traveler will come to that city because they are not willing to share house. You can assume that a single city has a single house. They also want to maximize the sum of all people's travel distance. Okay, so they want to travel a lot, and they want that the total distance they travel by plane or through road is maximized. Okay, the travel distance of a person is the distance between the city in which he lives and city he travels to. Okay, for example, a person lives in Delhi and he travels to New York. So the distance between these two cities is the travel distance. Okay, given the highways information, it's your job to find out the best plan and maximum total travel distance of all people. So you have to maximize the total travel distance of all the people combined. Okay, now let us see the input. The first line of the input gives us one integer t, indicating the number of test cases. Each test case contains an integer n, representing the number of cities. Okay, so that means these many nodes are there, or these many nodes are there in the network. Okay, the following n minus 1 lines contains three integer x, y, z. Okay, so that means there is an highway between x and city y, and z denotes the length of that particular highway, and you can assume the highways are connected and bidirectional. So it's a graph problem in which you have direct bidirectional edges. Also, it's given all of the cities are connected, only then you can connect from one city to another. Okay, and it's also given there are n minus 1 edges. So this is a very important hint. So a graph in which a connected graph in which you have n nodes and you have n minus 1 edges is actually a tree. Okay, so this is actually a tree, and it's a weighted tree. Okay, so maybe this is y1, this is y2, this is z1, this is z2. So it's going to be a weighted tree. Okay, so that means no cycle is present in the graph. For each test case, we have to print the largest total distance traveled by all the people. That's what we have to print. Okay, so this is what it is given to us. So let us see. Let's see the first test case. Okay, also there is also something given: the travelers always choose the shortest path while traveling. So I will explain you what this statement means. Yes, so let's see one example here. So it is given that there are four cities. So let's number the cities as 1, 2, 3, and 4. From 1 to 2, there is a distance of 3 units. From 2 to 3, there is a distance of 2 units. And from 3 to 4, there is a distance of 2 unit. And what you need to do now, you need to maximize the total distance traveled by these four persons. Okay, so there are four persons, and we have to maximize the total distance. Okay, so let me just name these nodes as A, B, C, and D. Okay, and this is 3, 2, 2. So what one thing I can do is there can be lot of possibilities. Okay, so if I just swap A with B and C with D, so how much travel I will have? So if we swap these two, it will be 3 plus 3, 6. And if I swap C and D, it will be 2 plus 2, that is 4. So you can see in this case the total distance traveled is 10 unit, but this is not an optimal solution. So what you can do is you can actually exchange 1 with, let's say, 3, and you can exchange 2 with 4. In that case, what you can do is 1 and 3 will travel a total distance of 3 plus 2 5 plus 5 10. So if you exchange 1 with 3, so that will contribute a distance of 10, and if you exchange 4 with 2, that will contribute a total distance of 2 plus 2 4 plus 4, that's 8. Okay, so this is 10 plus 8, that is 18 units. And also you can see yourself, if you exchange 1 with 4 and you exchange 2 with 3, that will also contribute a total distance of 3 plus 2 plus 2, that is 14, and this will contribute a distance of 4, so it will be 18 units. Okay, so in the best case, the maximum distance we can get is 18 units, and we want to maximize the total distance under the condition that the travelers take the shortest path to reach their destination. Okay, so what does this line mean? So this line basically means if 4 has to travel to 2, it will take the shortest path to reach 2, that is this path, and it will not do something like this, that it first goes to 1 and then it comes back to 2. Okay, so it will not take a path like this. So it will take the shortest path to reach 2. That's another clarification that I have to give from the question. Okay, so now you have understood the sample input output. Now let us discuss how we can proceed with the solution. Okay, so let's discuss, let's make a sample tree. Maybe we have a tree like this, which is actually a graph. Okay, maybe this is the set of nodes, and let's talk about what we can do. Okay, so what we can actually do now. So one way is you can generate all possible combinations of persons visiting in all other nodes. Okay, for example, if the persons are like this 1 2 3 4, you can generate n factorial possibilities, and for every possibility you can try to compute what is the distance traveled by each person, and you can uh, sum up that particular distance for all the persons. Okay, so this complexity would be very bad. It will turn out to be an exponential complexity, since n is a large number. I think it's of the order 10 per 5 or 6. Then this type of an approach will definitely fail. Okay, so another approach is we are actually not interested in finding out where a particular person X will be located after the final migration happens. So what we are interested in finding is what is the maximum distance that will be traveled by all the persons. Okay, so we can kind of include a greedy thinking here. In order to maximize the total distance, we can say, okay, we will try to maximize the distance that is traveled through every edge. Okay, so maximize the distance through every possible edge. Okay, so through every edge, so that's what we need to do. So if we are able to maximize the distance through every edge, we will be able to solve this particular problem. Now you may say, okay, let's see how we can maximize the distance through every edge. So let us try to break this graph about this edge from, let's say, x to y. Let's say there is an edge from x to y, and I'm interested in finding out how many people will actually travel through this edge. Okay, so for that we need to know the number of people in this part of the graph. So that's 1 2 3 4 5 6, and I also need to know the number of people in this part of the graph, and maybe let's say this is 7 and this is 8. Okay, so let's try to find out what is the number of people in this part of the graph. So that is 1 2 3 4 5 6 7. Okay, so we have 7 people in this graph. Maybe let's add one more. Let's add one more, and let's say this person is 8. So we have 1 2 3 4 5 6 7 and 8. Now this right hand side graph has 8 people, and the left hand side component of the graph has 6 people. So what do you think? How many people can travel in the worst case or in the best case through this edge? Okay, so let's say we have 6 people here, we have 8 people here. Now obviously, uh, in order to maximize the total travel through this edge, what I can do is I can pick any 6 persons from the right hand side part and send them across to the other part. Okay, and I can pick 6 persons, that is all of the persons in this part of the graph, and send them to this part. So that is how this utilization of edge will be maximum. Okay, so that means the total persons that can travel is minimum of 6 comma 8 into 2, because the movement is going to happen across both sides. So this edge will be used 12 times. Okay, and what will be the contribution of this edge to the total distance traveled? It will be 12 times the weight of the edge. Okay, let's say that weight edge is z, so it will be 12 times of z. So this is the contribution of this edge in this uh, movement. Okay, so you cannot use this edge more than these many times, and by doing such a phenomenon on every edge, we can ensure that we are able to find out the total maximum distance by summing this up through every edge. Okay, now you may ask, okay, how do we compute this now? Okay, so for that, one possible idea is you break the graph at every edge. Okay, you will get two components of the graph. Okay, you will get two components of the graph, and for those two components you can find out what is the number of nodes in the left part, let's say n of x, and what is the number of nodes in the right part, let's say n of y. So you use a traversal such as BFS or DFS to find out the number of members in the number of nodes in that particular part of the graph. Okay, so from this can be done in linear time, and from that you can find out minimum of nx and ny, and you can say, okay, 2 into the weight of that particular edge. Okay, so that will kind of give you an idea, and you will get a sub problem which you can solve recursively, and so on. So but this again will be a very complex method, because if you break this graph about this particular edge, okay, then you have e number of edges, and if you do BFS and DFS every time, that will take linear time, that will take order of v plus time, so you will end up getting this quadratic complexity. Okay, so that may also not pass. So we have to come up with something better. Okay, so we have to, now we will make another attempt in which we will try to do it in just linear time. So the idea will remain same. Okay, so idea will be that we will try to break the graph about every edge, and let me just take the sample test case that we have. Okay, and we will assume, let's say this is A, this is B, this is C, and this is D. This is 1, this, I think this was 3, this was 2, and this is also 2. So what I can do is I can actually do it in just a single DFS traversal. Okay, so what I can do is I can say, okay, let me give you another diagram as well. Okay, now suppose, let's say this is your graph, suppose. Okay, so what do? You start doing, let's say, DFS from this particular node. Okay, and you make a call on this particular node. Okay, so that is a small component of the graph, and you ask this component, what is your size, how many nodes you have in this component. Okay, so this component says, okay, it starts a DFS from this node, it says my count is 1, it makes a call on its child, this says my count is 1, so it returns this count to the parent. So this parent count becomes 1 plus 1 2, and parent makes another call to this node, it says, okay, my count is also 1, so parent says, okay, my count is 3. So this is how we know this component size is 3, and now this size 3 is returned to this parent node. Okay, now we are interested in finding out what is the total number of nodes in this part of the graph. Okay, so for that, what we can say is, we know in total we have n number of nodes. So if one of the child says, okay, there are 3 nodes, the other part of the graph will have n minus 3 nodes. And how many times this edge will be used? That will be minimum of 3 comma n minus 3. Okay, so this is how you can find out, okay, what is the number of nodes, number of people that will cross this edge. So that will be into 2, and total cost will be into weight. Okay, so when you do DFS, you will do one thing: you will always return the size of the subgraph or size of the component from which you are returning back. Okay, so for example, let's try to make a DFS call from A. Okay, and DFS will say, okay, at this point my count is 1 and I want to count how many nodes I have in my entire graph. So A makes a call on B and B starts another DFS call. So B says, okay, I initialize my count with 1 and I will make a call on C, on my children, on my neighbors. And C says, okay, let me say my count is 1 and I will make call on any children I have. So C makes a call on D. So D says, okay, my count is 1 and I will make a call on any children I have. So since D has no children, so it return back to C and it says, okay, my count is 1. So C comes to know that this D has, there is one component in the graph. So this count becomes 2. Now what happens at this place is, when C is making a call on D, we are basically talking about utilization through this edge. Okay, so you can treat it like this: we are at A, B, C. Okay, and we have, let's say, broken the graph about this edge, and C made a call on D and D returned. So let's say D is a component and D returns a 1. So C comes to know that on the right hand side of this edge, on the left hand side of this edge, the graph has one node only, and in this particular left hand side graph there would be n minus 1, that is 4 minus 1, 3 nodes. So how many people will cross this edge in the worst case? That will be minimum of 1 and 3. Okay, so we know that finally there is one person who will occupy node D. So that person can be one of these, A, B and C. We do not know. So whatever it is, so we will say that will be multiplied by 2 into the weight of edge, that is 2. So that means the total contribution of this edge will be 4. Okay, so that's fine. Now we come come back to C. Okay, and C will return some information to its parent. So this information is the count of the number of nodes in the graph of C. Now we are at this particular edge. Okay, so we have already traversed this edge, this part of the graph, and C is now going to return to its parent. So now B will come to know, okay, C is saying I have two components in my I have 2 nodes in my graph. So B knows, okay, there are 4 minus 2, that there are 2 nodes in the graph. Okay, so that means how many people will travel through this edge from B to C. Okay, so it will be minimum of 2 comma 2, and that makes sense. So that means 2 people will travel. So that means in the combinations we have seen, both A and B should come to this part of the graph and C and D should move to the topmost part of the graph. So total movement will be minimum of 2 comma 2 into 2 into the weight of the edge. So it is 2 into 2 into 2, that is 8 units. Okay, so the first edge is contributing 4 units, the next edge is contributing 8 units. Now let us come back here. Okay, so B now knows count is 1 and also the count of children of B is 2. So now B knows there are 3 nodes present in the graph that starts from B. So let's say from A to B. Let's talk about this edge now. We have B, C and D. So now the graph is broken about this edge. Okay, we are actually not breaking it, but we are just counting it down. So when you make a call from A to B, okay, or when you return from B to A, let's say, so B tells A there are 3 components in my subgraph. Okay, and A will know, okay, so out of total 4 nodes, 3 are present in the other part. So in this part A, there is only 1 node. Okay, so it will be minimum of 1 comma 3. The number of people traversing through this edge will be minimum of 1 comma 3 into 2 into weight of the edge, that is 3. So this contribution will be 6 units. Okay, now if you add up the total contribution, that is 4 plus 8 plus 6. So this turns out to be 18 units, and this is the maximum contribution that is possible. So now you can see we actually have used pigeonhole principle at this particular point. So we are breaking the graph into two parts. The one part has X nodes, the other part has Y nodes. And in order to figure out how many people will travel through this edge, we actually used pigeonhole, because we said if X is smaller, then at most X pigeons will travel from Y part to X part, or if Y is smaller, we will say at most Y pigeons will travel from X part to Y part. And this is nothing but a example of pigeonhole principle. So I hope you got an idea how we can solve this problem using DFS, and the overall complexity of this will be order of V plus E, that is the complexity of DFS. Okay, and now we will see the implementation of same in the next video. So thanks a lot. See you guys. Hi everyone. Now let's implement the problem wholly from Spoj. So I am constructing a graph. Okay, so that will have the number of vertices, and it will have an adjacency list. So let's construct that, and let's construct a graph constructor that will get the number of vertices, and we can just put it like this, and we can say L equals to new list, and it is a list of pair intent V. So since this is a weighted graph, okay, it's a weighted tree, so I need two things. So suppose there is an edge from X to Y and with weight of Z. So I will say, okay, in the adjacency list of X put Y comma Z, and also in the adjacency list of Y put X comma Z. Okay, so where Z is the weight, and this is the source, and this is the destination. Okay, so this is how I am going to make a adjacency list, and we are making a array of lists with so there are V linked lists. Okay, so it's an array of V linked lists. Okay, so this is L of 0, this is L of 1, and similarly we have L of V minus 1. So we have these many linked lists in the graph. Now what we need to do, we need to define a function called add edge. So let's say there is an edge from U to V, and there is a cost associated. So what I can do, we can say L of U dot pushback V, and I can say L of V dot pushback U, since it is a bidirectional graph. So that's the add edge function. Now we need to write the main DFS function which will help us to do the work. Okay, so let's see. So I think int DFS is the function, and we will maintain a visited array so that we do not traverse any node again. So we can say bool star visited equals new bool v of 0, and we will also maintain a count array that will actually help us to store the count of every node. Okay, so that we are going to maintain. So new int of v of 0. Okay, so this kind of an initialization does not work in my Sublime, so I can just put a for loop and set all these values as 0. So for int I equals to 0, I less than v, I plus plus, and I can say visited of I equals to false, and count of I equals to 0. So initially count of every node is 0, or you can also put it as 1, that's totally your choice. And here I can say, okay, as I go through my DFS calls, I will maintain my answer. Okay, so answer denotes the total distance traveled. So we will make a helper function that will get the source node. Source can be any node, let's say it's the 0th node. Then we have the visited array, and then we have the count array, and then we have the answer. So I'm going to update answer by reference. Okay, so let's return answer here. Okay, and let's make a function called DFS helper. Okay, so int DFS helper and here we can get the node at which we are currently present, and we can get the visited array, and we can get the count array, and we can get the answer. Now you can see there are actually two things that you need to do while returning from a node. Okay, for example, from A you made a call on B made a call on C, and C made a call on D. Okay, so D returns something to C returns something to B, and we will return something to A. So that something is nothing but the count of nodes. Okay, so that is what this int data type tells me. So int basically denotes the count of the subgraph starting from that node from which we are returning back to the parent node. So at this particular point, when B returns to A, this count will be 3. Okay, and the total distance traveled and will be updated by reference, because we are already returning the count, so we cannot return the total distance either unless we make a pair of intent. Okay, so either we do that or we can just pass this variable by reference. Now let's see what we need to do. So as soon as you come to a node, what do? You mark that node as visited. So that's what you do in DFS. Mark the node as visited, and you can say visited of that particular node. This is equal to true, and also set the count of that particular node as 1. So count of that node is going to be 1. That's what you can do. And here you can say for auto, let's go to every neighbor of that particular node. Okay, so neighbor will be a pair. So neighbor pair that's there in L of node. We can first find out the name of the node. Okay, so int neighbor, that is going to be neighbor pair dot first. Okay, so there is small thing that I missed here, so it should be equal to make pair, and here I can say v comma cost. Okay, and it should be make pair, and I can say u comma cost. Okay, so that's how we can say the first element of this pair is the node, and the second element is the cost. So here we can check if that particular neighbor is not visited. If not visited neighbor, we will try to visit that particular neighbor. Okay, so that we can do recursively. So okay, let me just explain you what we are going to do here is. So let's say from A you find a neighbor B that is not visited, so you make a recursive call on this neighbor, and once that call is over, this recursive call will return me the count of that particular node. Okay, so the count of children and the count of this, so it will be 1 plus count of its children, okay, and grandchildren and so on. So it will be the total size of this particular graph, that is 3. So that 3 should be added to the size of A, because it is also possible that someone else might have called A and A had lot of branches. Then you need to sum up all of them into A. Okay, so you can see count of the parent, that is A, so that is count of node, should be incremented by a particular value. Okay, so that value is nothing but DFS helper. You make a call on one of its children, and that children returns whatever is the whatever count that children returns should be added to the count of parent. So here you can say it's V, this should be neighbor, and we should have visited, and we should have count, and we should have answer. So that will basically increment the count of A by this particular factor. Okay, so A made a call on B, and recursively DFS happened on this particular tree, and B returned, okay, my count is 3. You have to do one more thing. You have to increment the contribution of this edge to the answer, because you made a call on A, and once this call is over, you are coming back from B to A. Okay, so at this particular step, you have already visited the entire subtree of B recursively. So what you need to do is you need to increment your answer. Okay, so I can say answer will be incremented by twice of minimum of x and y. Okay, so let's compute the number of nodes in one part of the array nx, and let's compute the number of nodes in the other part of the array. So nx will be nothing but count of that neighbor. Okay, so in one part of the array it will be count of that particular neighbor, and the other part of the array it will be v minus nx. Okay, and here you can say nx and ny. Okay, so carefully see, it is the count of neighbor, it's not the count of node. Okay, so a has a neighbor b, and b, once the DFS call on b is complete, then we have count of b that is set as 3. Okay, so we will update it, and once all the calls are over, okay, so once all the neighbors have been visited of for b, we will update this count as 3. Okay, so now b returns 3 here, so that's the count of neighbor. Okay, so since this neighbor is already visited, so its count is already updated. So n of y is the other part, this part, so it is 4 minus 3, that is 1, multiplied by the weight of the edge. Okay, so a to b we have an edge, so whose weight is given here, so that weight is neighbor pair dot second. Okay, so you multiply this with the weight. Okay, and that's it, that will increment your answer. And finally, just before leaving the node a, okay, or the parent node, what do you need to do? You need to return the count of this particular parent to the parent of this node. Okay, so once you are leaving from a node, okay, once you are going back from a node, you return the count of that particular node. Okay, so that count is nothing but return count of the node. That's it. Okay, so this is the DFS helper function, and that's it. Okay, so you will see it will run in order of, okay, so it will run in order of n time. So now I have made the graph, and let's try to run our code. Okay, and you can see we are getting 18 as the answer for this particular graph. So if even some of the things are little unclear, I can just dry run it, and so that you feel more comfortable in the implementation. Okay, so what I do, I maintain a visited array that you already know. We have a visited array for 4 nodes, and we have a count array that is also there for all the 4 nodes, 0 1 2 3, and initially all the counts are 0, and we start the DFS from the 0th node, from this particular node, and we say okay, find a neighbor that's there. So 0 finds the neighbor 1, and from 1 we again initiate another recursive call. So at 1 we say okay, count of this node is actually 1, so we mark this node as visited, and we say okay, 0 has a count 1. So from there we go to a neighbor that's 1, and we say okay, this count is 1, and we mark this node 1 as visited, and we say okay, this count is 1. And from 1 we go to another node that's a neighbor of 1, that's 2, we say okay, this has a count of 1, and we mark this node as visited also. Okay, so this is the visited array and this is the count array. So from 2 we go to a node 3, and we say okay, 3 is visited and count of 3 is 1, and from 3 we can see this for loop will not go to any other node, so it will just return the count of node. So it says 3 returns a count of 1 to 2, but so now you are in this call, so you are in this function where 2 had made a call to 3. Okay, so 2 had made a call to 3, so the neighbor was 3 and the node was 2. So at this particular point, you know the count of neighbor, so count of 3 is 1, so n of x is 1, and n of y becomes 3. So in your answer you add the contribution of this edge. Okay, so this edge has a contribution of 2 into minimum of 1 and 3, that's 1, into the weight of the edge, so that is 2. So this contribution is 2 into 2, 4. Okay, so this gets added to your answer. So answer which was initially 0, now the answer is 0 plus 4. Okay, and also at this particular point you also update the count of node by this particular factor. So count of 2 is updated by 1 plus 1, so this count becomes 2. Now in 2 you cannot find a neighbor which is not visited, so the only option is you have to go back to 1. Okay, so you return something to 1, so that count is 2. And 1 now knows, okay, when you are making a call to its neighbor, now node is 1 and the neighbor is 2. Okay, and also 1 knows that you're returning some information here, so that information is count of this 2, that is equal to 2. So you increment the count of node 1 by a factor of 2, so this count becomes actually 3. And also you know the value of nx, so this nx is 2, and n of y, this is also 2. So you add this value to your answer, so this value is nothing but 2 into 2 into 2, so this value is 8. So your answer is incremented by 8. And finally you are back in this function call where 0 had made a call to 1, and 1 will return 3 to 0. Okay, so in this case your node is 0 and your neighbor is 1, and count of neighbor is 3, and the value of nx is 3, value of ny is 1, so it will be 2 into minimum of 1 and 3, that's 1 into the edge weight, so it is, this value is nothing but 6. Okay, so you add 6 to your answer and you return count of node. Okay, so to this function here you basically get the size of the entire tree. So this function actually returns a value 4, but we are returning answer from this function, so that answer is nothing but 18. So I hope this one is now clear and you will be able to apply DFS to more such graphs like these. Hi, so we are now going to discuss one very interesting application of DFS, that is the flood fill algorithm, right? So we are going to make this coloring algorithm work in C++. So it is a simple variant of BFS or DFS that can be used to label various connected components given in a graph. It is generally performed on implicit graphs. So implicit graphs are nothing but 2D matrices, and starting from a particular cell we can call this function on the neighboring cells, right? So you can see this is one image which is in the form of a 2D matrix, and if I drop some colors into it, or maybe if I call DFS at some particular point in it, let's say this is some pixel and I drop a red color here, so what will happen, this color will spread in all 4 directions because these pixels are the neighboring pixels of the current pixel, right? So the color can spread in 4 directions, it can also spread in 8 directions. So it's totally up to us how many neighbors we want to have, and it will keep on spreading until we hit this boundary, hit this boundary, and eventually all the apple region will become red. So we have to write some function which recursively calls itself, and it goes further and further until we reach a cell which is already different from the current cell. Suppose all these cells are white and somewhere we have a boundary, and boundary is, let's say, drawn like this, right? So until we reach a boundary we will keep our DFS call running. From the boundary I cannot go any further, so I will stop here, I will come back, I will move in a different direction, again I can move in a different direction, from here to this cell, and so on. So the only thing is we have to initiate a DFS call from this point and it will spread out to the entire region, right? So starting from any particular cell we can call DFS in 4 directions, up, down, left, right, or we can also call in 8 directions, right? So if this cell is ij, so this cell will be I comma I plus 1 comma j, this cell will be I comma j plus 1, I comma j minus 1, and this cell will be I minus 1 j. So I have to call my function on these positions, right? So these are the 4 calls which I have to make from the current cell, right? And somewhere if on this cell I get the boundary, I will come back. I will just backtrack. So let's see what the input is. So this is my flood fill algorithm which accepts an input matrix. This is the input matrix I'm going to give. The first line contains the size of matrix followed by the characters in the matrix, right? So you can see I have already taken the input, the number of rows and the number of columns. Then I am reading all the characters in the matrix. Now we are going to actually replace all these dots which are inside the boundary region with some character, some other character. Let's say I want to make them red, so I can replace them with R, right? So this function accepts the matrix. It also accepts the current cell where we are presently at, and this also accepts the character which we want to be replaced. So I want to replace all the dots in the boundary region because these dots form one connected component. All these dots are forming one connected component. This is another connected component, and all the outer region is the another connected component, right? So we are going to identify connected components by dropping some color into this region, and I want to make them to be replaced by some other character, let's say red, right? So I want to just make it red. So let's see how we can implement this algorithm, right? So it is a very simple and a easy algorithm. So the first condition is the base case, and then we have boundary condition, and then we will have the recursive call. So to make the recursive call easy, I have already made two simpler arrays, delta x and delta y. So these will define my positions. So instead of writing like this I plus 1 comma j, I can simply write I plus dx comma j plus dy. So I have stored all the 4 pairs of increments for the 4 directions, right? So this represents west, north, east and south, because if I am at ij and I want to go to west, so I have to write I minus 1 j. If I want to go to north, I have to write I comma j minus 1. So this pair 0 minus 1 represents the increment I have to make to I and j. So for the base case, I have to check if I am inside my matrix. So it is a R cross C matrix, and we have to make sure we do not cross the boundaries of the matrix. So if I is less than 0 or j is less than 0, or you can say I becomes greater than equal to R, or j becomes greater than equal to column, then we have to return. We do not need to cross the boundary. Then we have to check if we are this is basically boundary of the apple, right? Boundary of, this is the figure boundary, and this is for your matrix bounds. So if we are coming to a cell, let's say if matrix of ij is not equal to ch, so ch is the character to be replaced. So in our case, this character is a dot. So if we find out some other character than dot, then we do not need to paint that character. We just have to return back. So if this is not equal to the character to be replaced, then we will just return. So this is how we return. Now in the recursive call, I am going to use the for neighbor approach, but before that I'm going to paint my current cell with the color, whichever color I want to give. Right now, let's make the recursive call. So I have 4 directions. So for all the 4 directions, I can call flood fill, and matrix is as it is, I plus dx, ij plus dy, dx of k. Right, I'm trying for every position, and character remains the same, color remains the same. That's it. So this is done for the flood fill. Now let's call our method, but before that let's also print our matrix. So I have print matrix function which takes the input matrix and print it. Now let's call flood fill, and let's drop the color at some at this coordinate. So this cell is 8, 13. So this cell is 8, 13. So I will drop color here. So I will initiate my DFS call from here, and let's say the cell is 8, 13. Right. So I can call flood fill on my input matrix, and this cell is 8, 13, and the character I want to replace is dot, and the color I want to fill is red. And again I call print matrix and input. So I need to give the input as well. Oh, just a minute. So this file is apple.txt, and let's run our code now. The input is apple.txt. So you can see this was your input and this is your output after filling. So after filling, you can see all the characters which are inside the boundary region are filled with R. Right, so you can also try out this with something else. Let's say flood fill input, let's say starting from 0, 0, and I want to replace all the dots with some other sign, let's say exclamatory, and let's run it. So you can see all the boundary characters, all the characters which were in the background are filled with exclamatory sign. Now only these dots are left. So let's also print how this algorithm is working. So if you want to see the states, intermediate states, you can print your matrix here. You can write print matrix and input. You will be able to see how this algorithm is proceeding. So sorry, this is your matrix. So you can see the algorithm is going on, and at this point some of the cells have been filled, and this is going on. Then grid is getting filled more and more. Let's yeah. So now the whole grid has been filled. So you can see there were some characters left here, and after the DFS call these also got filled. So this is how DFS is filling all your positions. So I hope this algorithm is clear, and using some more uh, modifications by adding some graphics you can make it better, right? So I have used Ncurses to add graphics inside this algorithm. So you can see if I run my code, the input is apple.txt. Let's run our code. So this is the same algorithm, except the final output is now a colored one. So I've used some graphic libraries in C++ to give colors to my final matrix. So thank you for watching. I hope you learned how the flood fill algorithm works. Hi everyone. In this lecture we are going to discuss a very simple problem, and the problem is we are given a undirected graph and we need to find cycle in it. Okay, for example, this graph I'm going to draw, let's say 0 1, and 1 is connected with 2, 2 is connected with 3, and let's say 3 is connected with 4 and 4 is connected with 0. So it's something like this. Okay, so this edge is not there, but this edge is present. So we want to find if this graph contains a cycle or not. So one approach is we could have used BFS, but we can also do it using DFS. Okay, so just we need to do any traversal and we need to see if we are coming to a node, if there exists a node that we are visiting in the traversal and that node is already visited. Okay, so a graph contains a cycle if there is more than one way to visit a node. Okay, so if there is more than one way to visit any node, so that means that graph contains cycle in this case. Okay, so this is true for an undirected graph. So what we can do is we can say, okay, let's start BFS from any node. Let's say we start from 1, we go to 0, and from 0 we go to, let's say, 4, from 4 we go to 3, and from 3 we can go to 2. Okay, and from 2 we can see, okay, we have neighbors of 2 as 1 and 3. Okay, and if we now see, if I can see 1 is already visited and 3 is also visited, but what will happen in this case? So I can say from 2 I'm going to 1. So 1 is already visited, that means this graph contains a cycle. Okay, but it is also possible in the adjacency list if you had 3 followed by 1 and suppose this edge was not present. In that case 3 was already visited and 1 was 1 will not be there. Okay, so in that case you will have only one node, that is 3, and you can see 3 is already visited, but 3 is also the parent of 2. So we have to actually check that from any node, if you are iterating over the neighbors of that node, so that ith node should not be equal to parent of that particular node. Okay, so that is a check that you have to make, because if you see from 2 where you can go, suppose this edge was not present in the graph, this edge is not there, this edge is not there, so then this graph will look something like this: 1 0 4 3 and 2. Okay, so you start from 1, you go to 0, you go to 4, and from 4 you can see I can go to 3 and I can also go to 0, but you have to discard the case of 0 because 0 is a parent of 4. Okay, so you go to 3, from 3 you can again, you have a neighbor, 3 has a neighbor 4 and 3 has a neighbor 2. So 4 is visited, 2 is not visited, so we have to discard this case because 4 is a parent of 3. So we cannot say from 3 we are going to node which is visited and it contains the cycle. No, so we can go to 2, and from 2 we cannot go to any other place. But suppose this edge is present, so 2 will have in its adjacency list 3 and 1. So 3 is also visited, 1 is also visited, and since 1 is not a parent of 2, and we can visit 1 through 2, so that means it contains a cycle. So 2 will return a true. Similarly, the 3 will see, okay, I got true from my next node, I should also return true, and it should return true, and it should return true, and 1 will return true to the main. So that's how we can use DFS to detect a cycle in a undirected graph. So let us quickly write the code for it as well. So firstly we need to make a visited array, bool star visited equal to new bool of size v, and I can say everything is false in the beginning. So I can say, okay, let's mark every node as not visited, visited of I equals to false. Okay, so I am assuming there is a single component in the graph, but if there are multiple components, you can make a DFS cycle helper call on from every node, okay, for every component once. So here I am assuming, let's start this from 0. So cycle helper, the starting node is 0, the visited array is this, and one more thing is we need to send what is the parent of that particular node. Okay, so let's say int parent. So let's say parent of 0 is, let's say, 0 only, and but for all other nodes we will update the parent accordingly. Okay, or let's say this is equal to -1. Okay, so instead of passing a parent array, I'm just passing what is the parent of current node. For example, if you make a call from 1 to 0, you will say, okay, the next node is 0 and the parent is 1, because at 0 you need to check that in its adjacency list all those nodes which are present, for example 4 and 1 are there, so you just need to know, okay, this node is the parent. Okay, so that's why you just need a single variable instead of passing the entire parent array. That would be sufficient. So here we can say visited of that particular node equal to true, so you mark that node as true because you are visiting it. And for auto neighbor, that is there in list of I. Okay, so we have a adjacency list, so this is called as L. So in L of node, so for every neighbor that is there in the adjacency list of that particular node, now you can have two cases. So one is if the neighbor is not visited. Okay, so let's say if not visited of neighbor, then you have to go and recursively visit the neighbor. Go and recursively visit the neighbor. Okay, so we have to go and recursively visit the neighbor. Okay, so that means if the neighbor is not visited, let's go and visit that neighbor. Now it is possible that two cases may arise. Okay, so first is yes, if the neighbor is not visited, and in the second case, so the second case will be the neighbor is visited, but we have to check that neighbor is not equal to parent. Okay, so we have to write else if neighbor is not equal to parent of that particular node. Okay, so suppose you are going from, let's say, 4 to 3, and now from 3 you can either go to 4 or you can go to 2, because 4 and 2 both are neighbors of 3, but you have to make sure that you do not count 4 while considering a cycle. Okay, so this is the case when the neighbor is visited, but that neighbor should not be equal to parent. So for example, you are at 2 and you make a call on 1, so in that case 1 is already visited, but 1 is not the parent of 2, so that case you can say return true, which means this particularly contains a cycle. And here what we can say is recursively look for the cycle in the other part of the graph. So if the neighbor is not visited, it is fine, but it is possible that neighbor may lead to a node that leads to a cycle. Okay, so that's the recursive case. So here we can say bool cycle mila, this is equal to is cyclic cycle helper, and here you pass the node. Now that particular node is the neighbor, that's the current neighbor and visited, and the parent. So parent of neighbor is nothing but the node from which you are coming. So if this says cycle mila, that means if cycle mila is true, then you say return true. Okay, that's it. And finally you can say return false, that means the cycle is not present in the graph. That's it. So let's try to run this code. Okay, so we have to finally return this function from the contains cycle. So it returns cycle helper 0 visited and this. So let's build the code. That's fine. And let's see the output. So it says yes, undirected graph contains a cycle. So let's see this graph now. So it's yes, it contains a cycle, but if I just comment out this edge, so it should give me does not contain a cycle. So it says no, it does not contain a cycle. So that's perfectly fine. So let me give you a quick recap of what we have done if you want to see. So we have a graph like this: 0, 1, 2, 3 and 4, and 4 is connected with 0. So we start from the node 0 and we say okay, go to a neighbor. Let's say the neighbor is 1. We go here, we go to the neighbor. Okay, so at 1 we say 1 is not visited. Okay, so 0 has a neighbor, that's 1, it's not visited. So we say okay, ask 1 if this node can locate a cycle. So at when we come to 1 we see okay, 1 has a neighbor, that is 2, that's not visited. So we come to 2 and then we say okay, what all neighbors 2 has. So 2 has a neighbor, that is 3, and at 3 we say 3 has a neighbor, that is 4. Okay, and 4 sees okay, 4 has two neighbors, 0 and 3. So out of which 0 is visited and 0 is not the parent, so 4 returns a true here. Okay, now 3 comes to know that it finds a cycle. Okay, so 3 finds a cycle and it returns true. So at this point 3 returns a true here, and similarly 2 returns a here using this statement. Okay, and similarly 1 returns a true using this statement. And the 4, so 4 when calls to 0, it returns true basically from this statement that 4 is able to find a neighbor that is not equal to parent. Okay, and how the parent value is getting updated: from 0 when you come to 1, parent is 0, when you come to 2, parent is 1, from when you come to 3, parent is 2, and when you come to 4, parent is 3. So in adjacency list of 4 we come to know that okay, parent of 4 is 3. So we do not consider this as a case of a cycle, because parent will be visited and that does not contribute to a cycle in this case. Okay, so I hope this is clear.
Hello guys, let's see what is a bipartite graph, and let's write a code that will check whether a graph is bipartite graph or not. Okay, so bipartite graph is also called a two-color graph. Basically, what is actually a bipartite graph? Bipartite graph is a graph that can be divided into two sets, let's say set 1 and set 2, such that all the edges in the graph are from one node in set 1 to other node in set 2, right? That means there is no edge such that both the endpoints of that edge are in the same set. Okay, so set of x should not be equal to set of y, and I have to divide all the vertices into two sets such that there is no edge between the vertices of the same set, and all the edges are between the vertices of the different sets. Okay, now let us see an example. Okay, first of all, think about it. If, when a graph is a tree, then can a tree be divided into bipartite set? If yes, how? Think about it, pause the video and then continue forward. So guys, of course, when I take this 2, I can't take this 1 and this 6 and 7 in the same set na. So if let's say I have two sets, and if I'll take 1, I have to take 2 and 3 in the other set, right? And if I take 2, I have to take 6 and 7 in the other set, and if I take 3, and I have to take 4 and 5 in the other set, right? So basically, for a node of level, let's say level is x, then this is the level x minus 1 and this is the level x minus x plus 1, right? So x minus 1 and x plus 1 can come in the same level, right? So basically these are not connected somewhere, they're not connected by they're not directly connected, right? Because this is the grandparent and this is the child, right? So what I can do is, for a tree I can just divide my tree into alternate levels and give them the same set, right? I hope you got this. Why am I doing so? Because if I take a particular level, then the level above it and the level below it has to come in the other set only. There is no other possibility, right? There is no other possibility, no other option. Okay, right? So basically, for all the even levels will come in set 1 and all the odd levels will come in set 2. Okay, we are done with the tree. Now let's see when a graph is a cycle. Let's say a graph is a cycle. It's therefore it's not a tree anymore, right? So when can I divide this graph into into two sets? Let's see. If I take one in set 1, if I take 1 in set 1, then I have to take 4 and 2 in the other set. Why? Because adjacent can't be in the same set na. That's the main condition of the bipartite graph, right? Now if I have taken 4 in this set, I have to take 3 in the other set, right? So we can see that all the edges are like 1 to 4, 2 to 3, 3 to 4, and 1 to 2, right? So all the edges are between a node in vertex in set 1 and a node in set 2. No edges in the same set, right? So, yes, this graph is a bipartite graph. Okay, so basically I have done it 1 2 1 and 2. Okay, now let's see another condition. Let's make a graph of length 5, right? So we can see there is a cycle of length 5. Now guys, if I give this 1, I have to give this 2 and this 2. If I give this 2, I have to give this 1. If I give this 1 and I give this 2, basically you can see they are adjacent and they are both in the same set, right? So this is not possible. Why? Because if they are in the same set, 4 and 5 are in the same set, then there is an edge between 4 and 5 in the given graph. So guys, there is no possible option that I can divide this graph into two sets such that the condition holds, right? So what's the main condition about a bipartite graph? The main condition is that the graph should not have an cycle of odd length. Okay, so if a graph is in cycle of odd length, then it cannot be divided into a bipartite graph. It cannot be said as a bipartite graph, right? So basically what we get is the main condition is cycle of odd length. I'll explain it to you why. I'll give you an intuition. Okay, see, let's start from 1 and let's start a DFS. Okay, so 1 I go, then I go to 2, I go to 3, I go to 4, I go to 5, and there is an edge between 1 to 5, right? So if I'll start with 1 in the color 1, 2 in the color 2, 3 in the color 1, 4 in the color 2, because I have to give adjacent colors as different na. So let's give 5 a color 1. I can only give 5 a color 1, right? So guys, we can see that if 1 is given color 1 and 5 is also given color 1 and they are adjacent, so the graph cannot be divided into a bipartite graph, right? Why is this happening? Because they are of odd length. If there is a chain of odd length, there is a cycle of odd length, so the first vertex that I'm starting with and the last vertex that I will end with, they will have the same color. And if they have the same color and they are connected by an edge, then they cannot be divided into a bipartite graph. Okay, now moving on further. Now let us see, I'll code it down. I'll write a code to check whether graph is a bipartite graph or not. Okay, so what's the main condition? I just have to check if there is a cycle. then the cycle cannot be of odd length, right? So how can I check if there is a cycle and the cycle is of odd length in the graph? Again, it's the same thing that let's take this graph. When I'll form a DFS 1 2 1 2, I'll start coloring and I'll color 5 with 1 and I get a back edge. This is a back edge now, right? So if I get a back edge and if this edge is pointing to the same color vertex, that means I've detected an odd cycle, right? Why? Because I'm continuously coloring the graph as a different colors to the adjacent nodes, right? So if there's an odd cycle and there's a back edge, the back edge will tell me that there's an odd cycle. Okay, let's say if this was an even cycle, let's take a case for even cycle. Okay, see, I colored 1 as 1 2, this 1, this 2. Now we can see I got a back edge, but the colors are different. Why are they different? Because I have colored them adjacently and it's of even length, right? So when it will be an of odd length, these two vertices will have the same color. The vertices connected by the back edge in the graph. So what I need to do is I just need to check whether they are of the same color or not in the graph, and that will tell me if there is an odd length cycle or not. Okay, let me code it down. Let's make a graph. Okay, basically I constructed a graph. Now what I need to check is, let's run a DFS starting from node 1. Okay, there's just two things that I need to check. The first thing is that if it is already visited, then I'll get a back edge. Let me write the DFS int current. We are on the current. Okay, now, and also we have to pass out the parent, because if I found a back edge, then that edge should not point to the parent, right? Basically I have to take parent also, right? Now let's go for all the child in this graph, the current vertex. So if let's say visited of child equals to 0, then what we can do is we can start a DFS for the child node and make the current as the parent, right? And what else do we need here? If it was already visited, that means there is a back edge developed. So if there is a back edge, I just have to check whether the child is not pointing to the parent. That means it is not the edge that I have just come with. Okay, so this is the basic back edge concept. But if you're not clear with the back edge concept, you can see the video for articulation points and bridges. Okay, so let me write it here, back edge, right? Now guys, what we can do is either I can take a visited array and a color array, because I have to color those vertices into the different colors, right? Or what I can do is, in the same visited array, I'll take 3 states. Okay, there are 3 points. Either visited I is 0, either visited I is 1, or visited I is 2. 0 means it is not visited till now, it has not been discovered. Okay, 1 means it has been visited and colored in color 1, and 2 means it has been visited and colored in color 2, color 1 and color 2. Okay, so basically my one array will be saved, that will be a colored array. So let's start the DFS from 1 and make its color 1. Okay, color, let's again paint this color on the node. Visited current equals to color, right? So if visited of child is 0, it means it is not visited, otherwise it is visited and it has some color, right? So if child not equals to parent, and this means that I've got a back edge. And when will it mean that I have an odd cycle? When this back edge has both its ends as same color, right? So color of the current vertex equals to visited of the next vertex. So what does visited contain? The color of the next vertex, right? So if color equals to visited child, then there is a back edge and odd length cycle, right? So for this, what I need to do is let's take a boolean variable, bool odd cycle. Let's mark it 0, and what we can do is odd cycle equals to 1. Okay, that means there is a cycle of odd length detected. So basically I have detected a cycle of odd length. Now after completing this DFS, what I need to check is if odd cycle, if I found an odd cycle, that cout not bipartite, right, else cout bipartite. Clear, guys? So this is my simple code for this. So guys, if I'll perform a DFS, see, I have started coloring from 1, right? When I'll perform a DFS for a child node, I have to send a color here for the child node, right? So basically, if a current vertex has color 1, so I have to send the color as 2 for the child node. If the current has 2, then I have to send 1 as the color for the child node, right? Because they have to be a different colors. So guys, when I have 1 and I have to send 2, and when I have 2 I have to send 1, what I can do is I can say 3 minus x, right? So when x is 1 it will be 2, and when x is 2 it will be 1, right? Because 1 plus 2 is 3. So basically I can write it as like 3 minus color. If the current color is 1, then it will push on 2 and pass on 2. If the current color is 2, it will pass on 1, right? So let's try to run this code. Okay, there are no errors, so this code is perfectly working, right? So basically this is my graph. You can see in the input.txt file. Let's make this graph. The graph is 1 2 3 and 3 4 and 5, right? So here is a cycle of odd length, right? That's why the output is not bipartite. Okay, and now let's make another graph. Let's make a graph from the 4 vertices, and let's take 4 edges, 1 2 2 3 3 4 and 1 4. So guys, if there is any edge, any cycle of odd length, that will be detected, right? Because because there will be a time we'll find a back edge for that cycle, right? So let's try to run it. Bipartite graph. Okay, so this graph can be divided because it has a cycle, but it has a cycle of odd length. I hope this thing is clear to you. It's a very small code. There is just one DFS used and a color. Okay, don't confuse by color and visited. Okay, this visited contains color only. If it is 0, that means it is not visited till now. If it is 1, that means it has been visited, the node has been visited and put in set 1, it has a color 1, right? And if it is color 2, that means it has been visited and put in set 2. Okay, so guys, thanks for watching the video. Hello everyone, let us see how to find the shortest cycle in an undirected and unweighted graph. So let us begin by making a graph, and let's see how will this work. Okay, let's say this was the graph, and again let me make one more edge here, right? So let's take an example on this graph. So guys, how will I find the shortest cycle on this graph? What I can do is we can start a breadth first search from a node, and when I'll do a breadth first search, I'll keep on marking the distances to every other node, right? So basically let's say I'm starting a breadth first search from a node 1, and my all the nodes at distance 2 are on the level 2, right? And let's say all the nodes at distance 3 are on the level 3. Okay, I'm just writing the nodes according to their distances, right? So guys, if I encounter an edge, let's say I encounter this edge, this one, right? So basically what does this edge tells me? This edge tells me ki I have encountered a back edge, right? So basically, what will be the length of my cycle now if I encountered this edge? So we can see one distance here and two distance here, right? So 1 plus 2 plus this back edge, that is 1, right? So wherever a back edge will be found between any two nodes in while doing a breadth first search, there will be a cycle, right? So this much is clear, right? Now we can see that let's make on this graph, right? Back edge tells about a cycle. Now let's start a breadth first search from node 1 and let's keep distances of these nodes, okay? Okay, so basically I'll reach here. The distance to this node is 1, the distance to the node is 1, right? When I'll update this, I'll push 4 and let me make it in the other color. I'll push 4 in my queue and then 5 in my queue, right? And after that I'll visit this again, marking these distances. What I get is 2 and 2. Now guys, I've got a back edge that points to 3 and I've got a back edge that points to 5, right? So what is my total distance now? So total distance to this node is 2, right? From 1 I'm talking about, because I have started a BFS from 1, okay? I'm just trying to make you realize the algorithm and also the points where this will not work, okay? So firstly I've got this 2, length is 2, and then I've got this length as 2, length of 5, right? 4 and 5, and then plus 1. Why? Because of the back edge. Basically what I got is that there is a cycle of length 5, but is there a cycle of length 5? No, right? We can easily see that there is no cycle of length 5 in the given graph. Now guys, we can see another thing, that if I talk about this edge, this particular back edge, so this edge is pointing between a node 3 and 5. So distance till 3 was 1 and distance till 5 was 2, and the back edge was itself 1, right? So basically we got a cycle of length 4, right? Why? 2 this side, 1 this side, and 1 back edge, right? So whenever listen it nicely, that whenever there is a node and this node itself is in a cycle, right? So whenever I'm starting a breadth first search from a source, let's name it source, from a source, right? So if source is in a cycle, then my breadth first search will give me the correct answer about the cycle of that graph, okay? So we got, there are two cycles, right? Cycle number 1 and cycle number 2. So we got the right answer for cycle number 1, right? Why? Because we started a breadth first search from 1. Of course cycle number 2 will cannot be detected by starting a breadth first search from 1. Why? Because it's breaking here into two parts, right? So let me take one more example now. So till now what did we see? Ki if I'm starting a breadth first search from a node and that node is itself contained in a cycle, then I'll get the right answer, the correct cycle, right? Okay, so let's start a breadth first search from 2, okay? So basically at 2 I am at a distance 0, then at 1 I am at distance 1, at 4 I am at a distance 1, and at 5 I am at distance 1, and then at 3 I am at a distance 2, okay? So we can easily see that I have got a back edge here, and this back edge is pointing to between 4 and 5. The distance till 4 was 1 and the distance till 5 is 1, and there is a back edge that will also be included in the cycle, right? So basically what's the length of my cycle now? 3, right? Now you get it, na? Ki why do I get 3 here and why did I not get 3 earlier when I started a breadth first search from 1? So now talking about this second cycle, we can see that if I started a DFS from 2 and I'm currently talking about this back edge, so we got 2 distance till 3 plus 1 distance till 5 plus 1 3, right? So basically I've got a cycle of length 4 and it's the correct answer. Why? Because this node is contained in both this cycle also and this cycle also, right? That's why I've got both of my cycles as correct. Why? Because I started a DFS from a node in that cycle itself. Okay, so basically if I have to find the shortest cycle in a graph, what I'll do is I'll have to find all the cycles in the graph, or let's say length of all the cycles in the graph, right? So how will I find the length of all the cycles and that too correct? I'll start a breadth first search from every other node. Okay, I'll code this in this video only. I'll start a breadth first search from every node, right? I'll take every node as a source and start a breadth first search and continue my operation, and whenever I'll get a back edge, I'll just mark it in the answer, right? So I'll show you a shortest code to find the cycle in a graph, right? So let's write the code, right? Let's make this graph only okay, 1 2 3 4 5 edges, 5 nodes, and 1 2 3 4 5 6 edges, right? 1 2 1 3 2 4 2 5 4 5 and 5 3, right? This is my current graph. So let's input this graph now. Okay, so basically this algorithm, if you are thinking about it, this algorithm is of complexity n square. Why? Because for every other node I'm starting a breadth first search which will visit all the nodes, right? Because we never know na ki if that current vertex is in the shortest cycle. But think about a question when it is already given that current vertex is in the shortest cycle, then we can start just one breadth first search from that node, right? Start a breadth first search from that node and mark all the distances, and whenever a back edge is encountered, just take it as a minimum in the answer, right? So we have to start breadth first search from every other node, right? So let me input it first. Right, after this what I need to do is I need to start a breadth first search from every other node. It's one based indexing, right? So what I'll do is I'll just call a function called bfs, right? And in this bfs I'll pass I, that is the current vertex, the source vertex, and the length of the graph, right? And also let's pass answer. Okay, so in this answer variable it will be updated again and again. Initially let's take answer equals to n+1, that there is a cycle of length n+1, right? Which is quite not possible. So after writing the bfs that I'll write, so if answer is still equals to n+1, that means there was no cycle. Why? Because answer was never updated, right? Otherwise if it was updated, then I'll write it shortest cycle is of length answer. Okay, so let's write this breadth first search code. It's very simple code of a breadth first search. Let me write it as source. Okay, let's take it as n and answer. Okay, so I'm passing this answer by reference so that it can be updated again and again. Now what I need is I need a vector. Let's take let's name this vector as distance. It is one base index, so I'm taking it as n+1. Initially mark it with int max. Okay, now let's take a queue to run our DFS breadth first search, right? Push in the queue source, because we will start from source. Mark the distance of source as 0. Okay, and now let's just run a breadth first search, not queue.empty, until queue is not empty. What I'll do, I'll just let's name it current. Okay, current equals to queue.top. I'll take the current element from queue, actually it will be front because it's a queue, right? I'll just pop it current element, right? Now what I need to do is I need to search for all the means I just need to write down a breadth first search, right? We all know about how to write down a breadth first search algorithm. So what I'll do is for auto x in graph of current, right? I'm going in the adjacency list of current. Okay, so basically what is x? Let me write it as neighbor. Okay, so auto for all the neighbors I'll go, and what I need to do is if distance of this neighbor okay, if distance of this neighbor is equals to int max only, that means it has not been changed. So basically I'm trying to not use a visited array separately, right? Because if distance of this neighbor was still int max, that means it was never visited, right? Because int max is a number of 2 to the power 9, 2 into 10 to the power 9, right? So basically this means that neighbor is not visited, and it's a simple edge, not a back edge. Okay, otherwise if I've already visited it, that means distance has been updated. So I just need to check whether I'm not coming from the parent, right? Because we all know about this case, there's a what is a back edge? Back edge is an edge that is not pointing to the parent, right? For example, when I'll start a breadth first search, I hope this point is clear to you because it has already been explained in many videos. So when I'll start a breadth first search, when I'll go in the adjacency list of 1, this was not visited and this was not visited, both of them will be pushed in the queue, right? So queue contains 2 and 3 and their distances are updated. Now when I'll go in the adjacency list of 2, I need to check this edge is not a back edge. Why? Because I'm already coming from 1. So this edge can't be a back edge, right? We can consider this edge as a back edge. So basically for this what we can say is that if distance of I don't have to take parent with the current node, right? I'll explain you why, because there is another easy method to do it. Okay, so if distance of neighbor is greater than equal to distance of current, then this current edge that is pointing to the neighbor is not a parent. Why? Because if what is a parent, right? Because let's say if we have a source and we are coming to an vertex current, let's say I have a source and I am currently at vertex current, right? And I'm started a breadth first search. So what does a breadth first search do is it visits all the nodes at distance 1, then it visits all the nodes at distance 2, right? So basically the distance of parent will be less than the distance of current, right? So if I just write this key for a neighbor whose distance is greater than equal to distance of current, that means the edge is not pointing to its parent and I have to consider that edge, right? So let's consider that edge. If distance of neighbor is greater than equal to distance of current, right? So if distance of neighbor is greater than equal to distance of current, what I need to do is I have to take answer. I have to just take minimum in the answer again and again, because I have encountered a back edge, and if I have encountered a back edge, I have got a cycle. So how will I get this? So it is simple: distance of neighbor plus distance of current from the source plus 1. I am doing this plus 1 for the back edge, right? So basically back edge is encountered. So by this method we can encounter a back edge in the breadth first search. And in a depth first search, how do we do it? We just pass on a parent with it because we are calling recursion again and again, right? So I hope this thing is clear to you. Let's try to run this code and see for any errors. Okay, I've written whole graph here and I've just taken gr. Okay, so if I have to take minimum in the answer again and again. Let's try to print this value of answer. Okay, so the answer is 6 here, and I have, whenever I am passing this answer to the above node, what's happening is Okay, so basically, okay, I have just not done one thing here. Yeah, I've just not completed this if, right, I just went back to this package case and I just wrote the code and move forward. So I have to write this case. So if the distance of current neighbor is int max, that means it has not been visited till now. That means this is not a package, na? So distance of neighbor will be equal to distance of current plus 1, right? And I will just push this neighbor in the queue. Okay, right? So I got my answer now, that shortest cycle is of length 3. Earlier, why did I get it? Because I didn't completed it, I just skipped it, because I was trying to explain you the concept of finding back edge in the breadth first search. Okay, so basically I got a cycle of length 3, right? So it's a very small code and there isn't very much to do in it, but you can try to print different values when I am getting this cycle of length 3. Okay, so guys, thank you for watching the video.
Hi everyone, in this lecture we are going to discuss what is topological sorting. Okay, so let's see a motivational real world problem. So suppose you are given dependencies between tasks of the form x to y. For example, if you want to learn machine learning, you must know Python, or if you want to build a face recognition project, then you need a data set, you need a deep learning algorithm, or you need a machine learning algorithm, something of this kind. Okay, so let us assume that you are given a dependency graph of this form, where if you want to do data processing or you want to learn PyTorch, then you have Python as a dependency. Okay, if you want to learn ML, you need to know data pre-processing and you need to know Python. So there are two dependencies for ML basics. So given this kind of a graph and your final goal is to, let's say, build a face recognition project, what steps will you follow? Okay, one by one. So you need to output a linear ordering of the steps. So one possible ordering can be Python, because you can start with Python because it does not have any dependency, or you can start by getting a dataset, because dataset also does not have any dependency. Then in the next step you can, I think, learn data pre-processing, because that has only dependency Python that we have already resolved. So in the ordering we can put 1 and 2, and we also know 2 was dependent upon 1. In the next step we can either do PyTorch, or we can do ML basics, or we can do dataset. So let's just go with ML basics. So we can do the task 3, and it was dependent upon task 2, and it is dependent upon task 1, and we can pick fourth. So let's learn PyTorch, and you can see it's dependent only on 1. And then we can pick 5, and 5 is dependent upon 3 and 4. So we can say, okay, since we have completed 3 and 4, we can go to 5. And let's say 6 is not dependent upon anyone. And finally we can do 7. So 7 is dependent upon 5 and 6. Okay, so this kind of an ordering, where you have 1 2 3 4 5 6, this kind of an ordering is called topological sort of a graph. Okay, so, and you can see this is really helpful to resolve all dependencies in the graph, and you won't get any conflict when you start learning topics in this order. Okay, so can we do this for every graph? The answer is no. For example, if you are given a graph of this form, which is a cyclic graph, let's say A, B and C, and you can see this graph contains a cycle. There is no way to start from any node because of the cycle. So we cannot build such an algorithm for cyclic graphs. So we have special type of graphs which are called directed acyclic graphs. Let's say a graph like this: B is dependent upon A, and B is dependent upon C, and C is also dependent upon A. So this kind of a graph does not contain a cycle, and it's called a directed acyclic graph. So one possible ordering for this graph would be, you start with A, then you complete C, and then you do B, and this way all the dependencies will be resolved. So for examples like these, you can have multiple outputs. Okay, you can also start with 6, and then you do 1, then you do 3 4 5 6 5 and 7. Okay, so this is another possible output that you can have. So multiple outputs are possible. Our goal is to print one such output. So let's discuss how we can build an algorithm to solve such kind of a problem. Okay, so now let me take a very simple example, and we will see how we can do topological sorting using DFS. Okay, so let's say I have a graph like this, 1 2, and here I have 3, and here I have 4. So clearly for this graph, one possible order could be, you can do 1 2, and you can do 3 4, or you can do 1 3 2 4. This is also fine. Okay, so let's see how we can build an algorithm for such kind of an graph. So what I will do, I will start from this particular node. Okay, and I will try to visit its neighbors. So I'm just going to apply simple DFS, and but in this DFS I'm going to maintain a list in which I will push data of the nodes that I have already visited, and I'm coming back from that particular node. Okay, so we start from 1, we do not print 1, we go to another node, that is 2. Let's say 2 is the neighbor, and from 2 we make a recursive call on one of its neighbors, so we go to 4. Okay, so at 4 we cannot go any further, so what we do, we push 4 in the queue. So let's say 4 is added in the list. Okay, so this is a list, and the operation that I'm doing is add front. You can also do push back, but this add front is really very useful. You will understand why. So what will happen now is, from 4 you cannot go to any other node. That means your work is done. So you push 4 in this list, and then you come back to the previous node, that is 2. At 2 you see, okay, I have already covered all the neighbors of 2, so it's time to go back to 1. So before you are leaving from any node, what do, you add that node into the list at the head of that list. Okay, so you insert 2, so you come back at 1, and at 1 you see, okay, there is a neighbor that is not visited, so you go to 3. Okay, and from that you come back and you add 3 in the queue. Okay, and at 1 you see, okay, I have visited all the neighbors, so you go back in the main and you add 1 to the list. So you get this ordering 1 3 2 4. Okay, so this is how you went, and then you went to 3, and then you went to 1. So you can see DFS is actually giving us the ordering that is required to do topological sorting of the graph. So it's very simple, and the reason why this works, so let's see. Suppose you have a slightly complex graph in which, let's say, you have a node X, and from this node X you're going to nodes A, B, C, and so on. Okay, and that means A, B, C are dependent upon X. So what do, you come to X, you try to visit all the neighbors of X one by one. So you go to A, you add A to the list. You try to visit B, you add B to the list. You try to visit C, you add C to the list. And finally you say, okay, I have visited all the neighbors of X, now I'm going back from X. So when you're going back from X, that is just before hitting the return statement, one step before that, what you will do, you will add X to the queue. So that will make sure that all the dependencies have been resolved correctly, because C was dependent upon X, B was dependent upon X, and A was dependent upon X. And since you are putting this in the queue at the front, this will make sure that you will complete the task X first before moving to tasks C, B, and A. Okay, now you may ask, what if A is also connected to some other node Y, and X is connected to some other node Z, and let's say Z is connected to Y? What will happen in such a case? So in such a case, let's say you start from Z. Okay, in such a case, let's say you start from Z and you first go to X and you cover these nodes. So once you come back from X to Z, okay, once you come back from X to Z, so Z will see there is a neighbor Y that needs to be completed first. Okay, so what will happen, you will go to Y and you will push Y in the queue, and from Y you see, okay, I need to go to A, but A is already visited, so you just come back to Z and at Z you see all neighbors are visited, so you go back from Z to the main and Z is added to queue. So in this case you can see A had two dependencies, X and Y, and both of them are resolved. Okay, and Y was dependent upon Z, so this dependency is also resolved, and Z is dependent upon X, that is also resolved. Okay, so this is how topological sort works. Now let me quickly show you the implementation for the same. Okay, so what I will do, I have the same DFS helper function, and I have made one change here. In the add edge function, instead of putting bidirectional edge, we will just have a directed edge. So I just comment out this statement, and rest of the code I will write. So we have the DFS function in which we have a map of visited. We will also maintain a list of type T that will store the ordering that is needed. Okay, so in this list what we can do is we are calling the helper function. Okay, so it is also possible that you have a node 0 that connects to. So in such a case what you should do is you should try calling DFS from all possible nodes. So you make a first call from this node, maybe you make another call from this node, so that will make sure that you add 0 in the queue as well. Okay, so that's why we are iterating over all the nodes and we are calling the DFS helper function from every node, and that node will visit its component if it is not visited. Okay, so let's see. What I need to do is I need to send this list ordering to the DFS helper function. So here I should get this particular node. So let me remove this graph, and let's say we will get the list of nodes. Let's call this as ordering, and you should pass it by reference because you want to maintain a single list. Okay, so when you come to a node, you mark it as visited, and I just remove this statement cout source. And when you're going to the neighbors, you should also pass this ordering, and at this particular point before returning from this function, you should push back or push to the front of the ordering this particular node. So the function is called push front, and this node is pushed to the front. That's it. Okay, and here we are making a call. Okay, and here we have created a list in the DFS function, and finally you can either return the list or print the list. Okay, so I can say for auto node that is there in the list ordering, I can say cout ordering handle, sorry, cout node handle. So that will give me the order in which I should do these tasks. Okay, so we have one error. Okay, the error is here. So when we're using this function push front, so the name of the node is source, so we should push source here. Okay, so let's build the code, and that's fine, and now we can run the code. So you can see the list. We have Python, PyTorch, dataset, data preprocessing, MLDL, and face recognition. So this order is correct, and this is how the topological sort function is just nothing but a DFS function itself. Okay, so that's all for this video. Thank you. Hi everyone, in this lecture we will discuss how we can do topological sorting using BFS. So far we have seen that we can get an ordering using DFS, but we can also do it using BFS. Okay, so the very first thing that you need to do is you need to find out the first node that does not have any dependency. Okay, so I'm going to define a term called in degree. So if you have a node in which you have some incoming edges, okay, that means this node is has a in degree of 3. Okay, and let's say it has two outgoing edges, so it has an out degree of 2, but we are concerned for in degree, so let's try to write in degree for each and every node. So this has an in degree of 0, in degree of 0, this has an in degree of 1, this has an in degree of 2, this has an in degree of 1, and this has an in degree of 3. So those nodes which have an 0 in degree, that means we can directly start with those nodes because they are not dependent upon any other node. So you can take a queue, and in the queue you can add these two nodes. So you add 0 and you add 1. Okay, so what you will do is since now you have initialized your queue, you keep on removing these nodes one by one. So you remove 0, that means okay, 0 is available for processing because the task 0 does not depend upon any other tasks. So you pop 0, and you also reduce the in degree of neighbors of 0 by an amount of 1. So in degree of 2 will now become as 1 because 2 is now dependent only upon a single node, that is 1. So what you do during this process, if in degree of any neighbor becomes 0, then you also add it to queue. So as of now there was only one neighbor and this in degree is not 0, so we extract the next node from the queue, that is 1. So we print it and we say okay, the in degree of neighbors of 1 will be reduced by a factor of 1. So this in degree is now reduced to 0, and we add 2 in the queue, and we also reduce in degree of this neighbor, that is 4. So this in degree is also 0, so we add 4 to the queue. So we go to the next node, we extract it, so we remove 2. So as soon as we remove 2, we print it, and we also reduce the in degree of its neighbors by a factor of 1. So in degree of 3 becomes 0, and in degree of 5 will become 2 because 5 is now depending upon only 2 nodes, that is 3 and 4. Okay, so 3 is added to the queue, and next node you pop is 4. So you print 4 and you update the in degree of its neighbor, that is 5. So this in degree now becomes 1. Okay, and next you remove 3 from the queue and you update the in degree of its neighbor, that is 5, and this in degree becomes 0. So this is added into the queue. So finally you will extract this node 5 and you will get the topological ordering for this problem. So that's how we can do this. So let's try to write the code, and this time I'm going to write everything from scratch. Okay, so we need to create a class graph. Okay, and let us say we have a very simple graph, so we can just keep a list of we can keep an array of lists, okay, to construct this graph. So we have a graph constructor that accepts the number of vertices. I can say this arrow v equals to v, and here we get the number of vertices. Okay, and I can say okay, this L pointer is an pointer to an array of lists that has v number of elements. So we have v number of linked lists, one for each node, and we can write a function add edge. So let's say there is an edge from x to y. So since it is a directed graph, I can just say L of x dot pushback y. That's it. And now I can write a function called topological sort. So what I need to do is, first I need to create an array of in degree. Okay, so let's say int star in degree, this is equal to a new array, and this array will contain v number of nodes, and we can just initialize everything with 0. So for int I equals to 0, I less than equals to I less than v, I plus plus, I can say in degree of I equals to 0. So we can initialize with 0 in degree, and then we can update in degree by traversing edges. Okay, so if there is an edge from x to y, that means y has at least one dependency, so I can say in degree of y should be incremented. So let us iterate over all the edges for auto p that's there in the adjacency list L. Okay, so p dot first will give us x, and its neighbors will be given by p dot second. Okay, so I can say auto y in p dot second. So let me tell you what I am doing here. I'm just iterating over the adjacency list, so I can say in degree of y plus plus. Okay, so let me just give you an example here. So if you have edge from 0 to 2, and if you have an edge from 1 to 4, 1 to 2, so I say okay, this is p dot first, this is p dot second, I iterate over this. This is an edge from x to y, y1, y2, and so on. So I say okay, in degree of 4 will be incremented by 1, and if there is an edge from 4 to 5, 2 to 5, and 3 to 5, so in case in degree of 5 will become 1, 2, and 3. So final in degree of 5 will be 3. That's what we are doing here. So that gives us the in degrees. So after that we have to apply BFS, and in the first step we have to find nodes with 0 in degree. Okay, so you can iterate over the in degree array for int I equals to 0, I less than equal to v less than v I plus plus. I can say if in degree of a node I is equal to 0, I can push that node in the queue. Okay, so we can initialize a queue, so we can say queue of integers, it's called queue, and I can say okay, queue dot push I. So that node is now added in the queue. After that we can start removing elements from the queue. So I can say while the queue is not empty, I can pop out one element. Okay, so I can say int node equals to queue dot front and queue dot pop, and then I can iterate over the neighbors of the queue. Okay, so iterate over neighbors of that node and reduce their in degree by 1. So that means for auto neighbor that is there in adjacency list of this given node, so that is L of node. So you can say okay, in degree of that particular node is reduced by 1, and if this in degree of that neighbor becomes equal to 0, that means we can process that neighbor, so it must be added to queue. Okay, so that's it. That's what we have discussed in the algorithm, and now we will make the graph and test our code. One change that we should make here is since L is a array, so we cannot iterate it like this. So I can say int I equals to 0, I less than okay, so this part is actually I wrote according to the hash map, so it should be modified according to the list. So what we need to change this particular part. Okay, so we have now an adjacency list like this. Okay, and we have list like this. Okay, so this is an array of pointers, and what we can do is we can iterate from index 0 to v minus 1, and we can just, if you want to iterate over this list, we can say this is L of I. That's one change we need to make here. So for int I equals to 0, I less than v I plus plus, and x is not needed actually, so you just iterate over this thing auto y, that's there in L of I. So for all the elements in the ith linked list, in degree of y will be incremented by 1. Okay, so let's also add a cout statement here that will print the nodes, and let's build our code. That's fine, and let's try to run the code. Okay, so if I run topological sort, I get 0 1 4 2 3 5. So yes, so we can have 0 1 4 2 3 and 5. So this is a perfectly correct order, and maybe I missed a 3 here, so that's fine. Okay, so this is how you can perform topological sort, and I will give you a quick recap of what we have done in this code. Okay, so if you want to revise, you can watch this part. So initially I created an array that stores in degree of all the nodes, and it is initialized with 0. Then I iterate over this adjacency list. For example, if this element 2 is occurring 2 times in all the lists, then this 2 will have an in degree of 2. So I iterate over all the linked lists, and here we are iterating actually over the linked list. Okay, each linked list. So we say, okay, if there is an element y which is in the linked list, that means if an element is like this 5 6 7 8, so that means 6 7 8 have one dependency, that is 5. So I increment their in degree by a factor of 1. That's what we do, and we do it for all edges. And after that we have this we have this queue where we initialize this queue with elements with which have 0 in degree, like in case of 0 and 1. So I iterate over all the nodes and find nodes which have 0 in degree. I add them in the queue, and then I do simple BFS. While the queue is not empty, you pop out one node and you go to the neighbors of that node, you reduce their in degree by 1, and if this in degree becomes 0, let's say some node x, then you insert that node x in the queue and you remove this. Okay, so that's what we do. So I hope this is understood, and thank you. Hi everyone. In this lecture we will discuss a problem in which we are given a directed graph and we are interested in finding out if that graph contains cycle or not. So let's first look at this particular graph. So there is an edge from 0 to 1, there is an edge from 1 to 2. These are directed edges. There is an edge from 2 to 3, and let's say from 3 to 4 there is an edge. From 4 we have an edge to 5. There is an edge from 1 to 5, 5 to 6, and 4 to 2. Okay, this is the edge. Okay, so we are now interested in knowing whether this graph contains a cycle or not. So the difference is, earlier problem we discussed for an undirected graph, the same algorithm will not work for the directed graph, because if you carefully see in this graph, in the undirected case we just checked if there is a way to come back to a node again. But if this is a directed graph, you can see, let's say if this is the graph, so although there are two ways to visit this particular node, but it does not contain a cycle. Okay, so no cycle is present in this particular graph. But if we carefully look at this graph, you can see there is a way. If you go from 0 1 2 3 4, and from 4 you can come back to 2, so this part is actually creating a cycle in the graph. So that means you can come back to a node that is already visited, and also that node is visited in the path of visiting the current node. Okay, so let's try to do something using DFS. So what I do, let me tell you. Okay, so what I do is, let's say we start doing DFS from the node 0. So we visit this particular node, and let's also maintain what nodes we are visiting. Okay, so I'm going to maintain two things. One is my current stack. You will see this will be really helpful. So that stack will store the current path. Okay, what nodes I have visited in the current path, and another is my visited array that we generally need. Okay, so this is my visited array. So let's say when I go from 0 to 1, I mark 0 as visited, and I go to 1, I mark 1 as visited, and 2 3 4 5 6 7. Okay, so from 1 we have two options. We can go to 5, we can go to 6. Okay, let's also fill the stack. So what is the current path that we have? So we have 0 and 1 in the stack, and from 1 we can make a call to 5. So let's make 5 as visited. So we go here, and from 5 I can go to 6. Okay, so 6 is visited, and both 5 and 6 are part of the stack. Now what will happen? From 6 you will come back because there is no way to go anywhere else. So you come back to 5. Okay, so in this case 6 will remain visited, but 6 will be popped out of the stack because it's no longer the path, no longer in the current path. So we are now at 5. From 5 we cannot go to any other place, so we remove this from the stack, but we still mark this as visited. Okay, and from 5 we can return to 1. From 1, what we can do, we can go to some other node. Okay, so we can go to 2. So at 2, what we do, we make it as visited first, and we also add it to the stack. So now the stack will look something like this. You will have 0, you will have 1, and you will have 2. Okay, from 2 we can go to 3. Okay, so we mark 3 as visited, and we also add 3 in the stack. Now from let's go to next node, that is 4, and we add 4 in the call stack, and we also mark 4 as visited. Now we have visited all the nodes, but from 4 we can go to another node 5. So we can see we are going to 5. So 4 has an edge to 5 that we are yet to use, but 5 is already visited. So can I say visiting 5 will create a cycle? No. Why? Because 5 is not in the current path. Okay, so if you see carefully, what is the current path? So it's 0, 1, 2, 3, and 4. And if you just see this part, this is not a cycle. This is not a cycle, but there is also another edge, which is this edge. Okay, so it's taking to your node, to a node that is visited, but that node is also in the current path. Okay, so there is a node from 4 to 2. So this edge is called a back edge. Okay, and basically if a graph has a back edge, then we can say that graph contains a cycle. So what is a back edge? So it's an edge from a given node to a ancestor of that node in the same path. Okay, so currently we are having this path 0 to 1, 2, 3, and 4. From 4 there is a edge to an ancestor that is in the same path of 4. Okay, there is also an edge to 5, but 5 is not in the path of 4. So that's why we can say that is not a case of a cycle, but this is definitely a case of cycle. So our goal is now to detect and find a back edge in the graph. Okay, so that's why you can see we actually need to create two data structures. One is a stack array where we can check if that node was present in the stack, in the current call stack, and we need a visited array. Okay, so that's two things that we need to implement this solution. So we won't be using the stack data structure, but the implicit stack is maintained by recursion. But since we need to look up whether a particular node 2 or 0 or 1 is present in the stack, we can just make it like a array so that we can do a lookup in order 1 time. So we can directly check, okay, if stack of 2 is 1, that means this node is present in the array. Okay, or this node is present in the path. So we will implement stack as an array. Okay, so we will have indices like this 0, 1, 2, 3, 4, 5. If 2 is there in the stack, we can just make it as true. That's what I am going to do. Okay, so let's try to write a code for the same. Okay, so we will make two arrays. One is a visited array, that's a new bool, and it is of size v, and we will make a stack array. Okay, so it's not a stack data structure, it's just array. It's also of size v, and we can make a helper function. Let's say bool cycle helper, and this gets the node, and it also gets the two arrays, bool star visited and bool star stack. So now we have the addresses of two arrays, or you can say we have the two arrays. So first thing that we need to do when we visit a node. Okay, so firstly, when you visit a node, you say visited of that particular node equals to true. Okay, and also that node becomes becomes a part of the current path, so you can say stack of node is also true. But when you okay, so this is when you visit a node, and in the end of the code you will also have a case when you leave a node. Okay, so when you leave a node, when you're going back from, let's say, 5, what do you do? So that node still remains visited, but it is not a part of stack. So we say, okay, stack of that node equals to false, and here we can say return whatever true or false, whatever we want to return, we will see. So this part will come in the end of the function. So here what we need to do, here we need to check if that node contains a cycle or that node leads to a cycle. That's what we need to check at this particular point. So what I can do is, suppose we are standing at node 1, okay. So 0 asked 1, is there a cycle in the graph? So 1 will return true or false to 0, okay. So 1 will make a call on 2, one of its neighbors. 2 will make a call on 3, one of its neighbors. 4 will make a call on 3 will make a call on 4. 4 will make a call on 5. 5 will say no, I am not in the stack, so this cannot be a cycle, okay. So 4 will make a call on 2. So 2 will say, okay, I am in the stack and I am also visited, so that means there is a cycle, okay. So that's what we need to do here. So I can say for int neighbor that is there in the adjacency list of node. So I can say L of node, and here I can have two cases, okay. So one case is if you find a neighbor, suppose you are at 4 and you try to find the neighbors of 4. So there is a neighbor 2. So okay, so in that case what you can say, if that particular neighbor is in the call stack, okay. So you can see if stack of node is true, that means this is a case of back edge. So sorry, stack of neighbor, okay. So if stack of neighbor is true, you must return true that there is a cycle that is present. Otherwise, if you are at some other node, okay, so this is a case of 4, but let's say if you are at 3, so 3 is connected with 4, but 3 does not directly lead to a cycle, but 3 leads to 4, which leads to cycle, okay. So what you can say is, you can make a recursive call, you can make a recursive DFS call on the next node and ask if there is a cycle present from the next node, okay. So what we can say is, we can say if you are making a call on a neighbor, if visited of neighbor is false, that means that neighbor is not visited, and but that neighbor can lead to a cycle, okay. So you can make a recursive call here. So bool cycle mila is a variable name, and you can call this function cycle helper, okay. And here you can say, okay, I give the neighbor, I give visited, and I give the stack. So it is possible that the next node finds a cycle. So if cycle mila is true, okay, then you should also return true, okay. So we can make this case as a else if case. That's it. And finally at this particular point, we can say return false, no cycle is present, okay. So now carefully see what we are doing. So let's see. So this is what we are doing. So we are at a particular node, let's say we are at 0 or 1, okay. So we say, okay, if stack of neighbor is true, that means is 1 in the stack? No, it's not. So we go to this node, from 2 we go to 3, from 4. At 4 we can say, okay, 4 has a neighbor 2 which is already there in the stack, okay. So we say return true, that means 2 will return a true to 4. And how 3 will come to know that this is cycle is present at 4, okay. So when 3 makes a call to 4, so 4 says 3 asks, did you find a cycle? So cycle mila is true, because 4 returns to 3 that a cycle has been found, and 3 will return to true 2 that a cycle has been found, and 2 will return to 1, a cycle has been found, and 1 will return to 0, a cycle has been found, and 0 will return to main that a cycle has been found. So in order to send this backwards, we need to use this. So you can see if visited of neighbor is false. So let us see again, from 0 you go to 1, so it's now visited, 1 is visited, 2 is visited, and even 3 is visited, and now 3 has a neighbor 4 which is not visited. So if the 4 is not visited, so you make a call on 4 and you ask, okay, is there a cycle that you find at 4? So 4 will actually hit in this case. and this will return true. Okay, and this true will be propagated backwards and so on. So I hope you got an idea how this algorithm works. So it's little tricky but not very difficult. So I suggest you to dry run this and things will be more clear. And let me try to run this code. And here I can say return this function cycle helper. This accepts node, it accepts visited, and it also accepts stack. Okay, so we have, sorry, this node is 0. Okay, and you can also set all the values as 0 here. So for int I equals to 0, I less than v, I plus plus, you can say visited of I equals to stack of I equals to false in the beginning. Okay, so that's okay, and now we can run the code. So it says no, it does not contain a cycle because mm, okay, I found out the mistake. So this is by mistake written as not equal to, but it should be equal to. So if the neighbor is not visited, only then you will make a call and you will try to visit that node. So exactly as DFS. Okay, so let's build the code again and see the output. Okay, so it says yes, it contains a cycle. And suppose if I remove this particular back edge from 4 to 2 and I build the code again, and let's try to run it. So it says no, it does not contain a cycle. So that's perfectly fine, and I hope this is clear now. Hi everyone, so in this video we are going to discuss an algorithm that will help us to find strongly connected components in a given graph. Okay, so firstly we need to understand what is a strongly connected component. So we have already understand the concept of a connected component in a graph. So strongly connected component, or SCC in short, is a concept that is related with directed graphs. Okay, let me give you an example of a directed graph. Let's say we have a graph like this, and let me draw some more vertices in this graph. And now the question is, how do you find the strongly connected component in this graph? Okay, or what is a strongly connected component in a graph? Okay, so if you take a subset of a graph, okay, so that is going to be a component. Let us pick this component. Okay, let us pick this component of the graph, and if starting from any vertex, if you're able to reach all other vertices in that component, then that component will be called as a strongly connected component in a graph. Okay, for example, if you start from 0, then you can reach the node 1 and you can also reach the node 2. Or if you start from the node 2, you can reach the node 1 and you can also reach the node 0. And similarly, if you start from 1, you can reach the node 0 and you can reach the node 2. So we can say, okay, this part of the graph is a strongly connected component. So this is one component in the graph. Okay, so okay, let us see what more components can we have. Can we have this entire thing, 3, 5, 6 and 4? So the answer is no. Why? Because if you start from 4, you cannot reach the vertices 3, 5 and 6. Okay, so we cannot have 4 in the same component as 3, 5, 6. So another component that we can have in the graph is 3, 5 and 6, and you can see it forms a cycle. And if in a cycle, if you start from any node, then you can reach all other nodes in that component. Okay, so we can say this is another component in the graph, and let's call it as strongly connected component 2. And the third component will be this node itself. So this is the third component. Okay, so this given graph has 3 strongly connected components, and the components are 0, 1, 2, they form one component. 3, 5, 6, they form another component, and the node 4, that forms another particular component. Okay, so I hope you got an idea. So a strongly connected component is a component such that starting from any vertex in the component, you are able to reach all other vertices in that component. Okay, you can reach all vertices in the component. So that kind of a grouping will be called as a strongly connected component. Now we need to understand the algorithm. Okay, so there are two popular algorithms for finding SCCs, and in this course we would be discussing the Kosa-Raju's algorithm. So let us discuss the steps involved in this particular algorithm. Okay, so I won't say it's a very intuitive algorithm, but once we know the algorithm, we can actually dive deep into the intuition why these steps are actually helping us to find the strongly connected components. Okay, so first step is you need to kind of do a DFS on the graph. Okay, you need to do a DFS on the entire graph, and you need to get an ordering based upon finish time. Okay, so basically when you do DFS, uh, you try to visit as many vertices as you can starting from a given node, and once you are going back from a vertex, so that time is called as a finished time. So you need to get an ordering based upon finish time. Okay, so let me uh, tell you how you can get this ordering. So let us say you start from this particular node. Okay, you can start from any node, but let us assume you start from the node 3 or you start from node 0. Anything is possible. So you can have different orderings, that won't be an issue, right? So let us say we start our DFS call from the node 3, and from here where we can go to the node 5, and from 5 we can go to the node 6, and from 6 we cannot go anywhere. Okay, so we have to come back, and once you're returning back from a node, you push that node into a vector. Okay, so you have to create an ordering based upon the finish time. The node that is finished late will be pushed at the end of the vector. So from 6 you are going back, so you push 6 in your vector, then you go back to 5, and from 5 you cannot go anywhere else, so you come back. So what you do, you put 5 here. Okay, and in the next step, what do you do? From 3 you can see you can go to 4, so you go to 4, you put 4 in the vector, because from 4 you are going back, you came back to 3. Now from 3 you cannot go to any other, you cannot go to 0, because the edge is directed towards 3 and it's not towards 0. So what do, you pick any other node in the graph and again start doing DFS. Let's say you start doing DFS from the node 0, or you can start with the node 1 as well. So what will happen? From 0 you will go to 2, from 2 you will go to 1, and since from 1 you cannot go anywhere else, you will come back and you will push 1 in your vector, and from 2 you again come back, so you push 2 in your vector, and finally what do? You're going back from 0, so you push 0 in your vector. So this is what we get. Okay, so the node that is finished at the last is at the end of the vector. Okay, so some people also use stack, and here we are using a vector as a stack. Okay, so basically the node that is finished at the last is at the top of the stack. Okay, or you can also use a vector. So whatever data structure you want to use, both can be used. Okay, because we are simulating the same functionality through vector as well. So this is the first step. Now let us discuss the second step. Okay, so second step is you need to reverse the original graph. So the second step is reverse the graph. So reverse the graph means reverse all the edges of the graph that you have. So what we will do, we will create a copy of the graph in which all the edges are reversed. So let us see how we can create that copy. So as you can see, we have created the reverse graph in which all the edges of this original graph have been reversed. Okay, so this is the second step. Okay, so I'm done with this step. The third step is it's quite an interesting and important step. What you need to do, you need to pick vertices from the this particular ordering, and you need to start doing DFS. Okay, so it says pick the vertices from the ordering that you have created. So we will iterate over this vector from right to left, and every time we will pick a vertex, we will start doing DFS according to the vertices given by this particular order. Okay, so you again do DFS from right to left, okay, as given in the ordering list. Ordering, so the first vertex is 0. So if you do the DFS from the node 0, what you will get? So every time you initiate a DFS call from here, what it will do, it will go and visit 1, and it will go and visit 2, and from 2 you're coming back to again 0, and so you won't go back to 0, so you return from here and you return from here. So what you will get, you will get a component that starts from 0. Okay, so we get the first component, that is 0 1 2, by initiating a DFS call from the node 0, and as a result of this DFS call, the node 0 is visited, 2 is visited, and 1 is also visited. So you have visited these 3 nodes. So you come back here, you check, okay, 2 is visited, I do not need to make a DFS call. You come back here, you come to 1, 1 is visited, do not make a DFS call. You come back to 3, and again you see 3 is not visited. So what do? You make a DFS call from 3. Okay, now you start another DFS call from 3. So it will take you to the 6, then it will take you to the 5. From 5 you cannot go anywhere, you come back to 3, and that's it. So you get the second component this way. So the second component contains 3, 6, and 5. These are the nodes that are there in the second component. So as a result of this DFS call, 3, 5, and 6 are visited. So you come back to 4, and you see 4 is not visited. So you initiate a DFS call from 4, and this will visit only one node, that is component 3, and this node is 4. So 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 this is how you will get the connected components. Okay, so each DFS call will give you uh, the connected component. So this DFS call gives the connected component. Now the question is why this algorithm works. Okay, so now let us try to dive into the intuition. Okay, so for a more mathematical proof, you can refer the CLRS book, but let us try to dive into the intuition of this particular algorithm, why it works. Okay, let us see. So if I just club all these components 0 1 2 into a single component like this, let us say I have a component A which contains the nodes 0 1 and 2, and let me say I have a component this, let's call this component as B, which contains 3 6 5. Okay, and let us have another component 4, uh, another component C which has this node 4. So this is A, this is B, and this is the component C. And let us also draw the connections between these three components. Okay, so 3 is connected with 4, so we have this particular edge, okay, in the reverse graph, and also 3 is connected with 0, so we can say, okay, we have this particular edge, right? So we are not worried about connections between 0 1 and 2 because they are connected, and starting from any node, either from 0 1 2, you can reach all the nodes of this component. Okay, so we have just drawn the 3 connected components and the connections between them. So now I want to tell you the importance of this ordering. Okay, why this ordering is important. Okay, so suppose you do not start doing DFS from node 0, instead you start doing DFS from some other node. Okay, so what will happen? So this ordering says you should first do the DFS from the node 0. Okay, so what happens is, if you do the DFS from the node 0, you will never end up going into the other component. Okay, from if you start from the node 0, you will only explore all the nodes that are present in A, right? But if you start from some other node, let's say you start doing DFS from the node 4 in the reversed graph, then you will end up traversing the components 3, 6, 5, 0, 1, 2. So you will not get the right components. Okay, so basically that's the importance of ordering. Okay, so if you carefully look, so what we do, out of A, B and C, which is the first component that we need to traverse, obviously this is component A or the component C1, and that is decided by this particular ordering. Okay, so if you do DFS from node 0, you basically traverse 0, 1, 2 before traversing component B and C. Then what is the next component you need to traverse? Either B or C. But if you traverse C, you can also end up going into B, right? But suppose if you start from the component B, right? So if you just see from right to left here, 3 is coming before 4. So that means this will be always a case we would be traversing this component before this component. Okay, so the reason being is when we did the DFS based upon the finish time, so in that case we made sure that if 4 is reachable from 3, then in the ordering 3 will come after 4. Okay, so this is an important statement. So if X is reachable from Y, or let's say if Y is reachable from X, Y is reachable from X, for example in this case 4 is reachable from 3, then in the ordering that is based upon the finish time, we always ensure that X comes after Y. Okay, so you can see 4 is reachable from X. Okay, and X comes after Y, so 3 comes after 4, right? So this is, and since 3 is coming after 4, and in the reversed graph if you do the DFS from 3, you will always traverse this component before going to this component. Okay, and then you finally traverse the component 4, and you do not need to make a call from DFS 5 and DFS 6 because those nodes are already visited. So this is kind of an intuition that is behind this algorithm. Okay, so I hope you got a very high level over idea how to find strongly connected components in the given graph. In the next video we will see the implementation of this particular algorithm. Okay,
Hello everyone. Let's begin with the topic strongly connected component. Right. Basically, first of all, let us see what these individual terms means. Right. First of all, what is a component? Component is a part of a graph, and again, what is a connected component? In a connected component, there is a path between every two vertices. Right. Basically, if I make a graph like this, so this graph has three connected components, right? Why? Because there's a path between every two vertices, there's a path between every two vertices, and there's a path between every two vertices, right? Basically, this component has size of 1, so it is a connected component, right? Because from 6 we can visit 6. So what does a connected component means? If two vertices are in the same connected component, then there is a path between them, right? That means we can go from that one vertex in that component to the other vertex in the same component, right? Now guys, let's discuss about the term strongly. What does this term strongly means? Strongly means the term strongly is used only for directed graphs, right? Otherwise the rest definition is same. What is the definition? That what is a strongly connected graph? If I say a connected graph and a strongly connected graph, they both mean the same, but whenever the term strongly is used, this term changes its meaning in the form of a directed graph, right? So what is a connected graph? Connected graph can be any uh, bidirectional graph, right? Such that all the vertices are in the same component, right? So what is a strongly connected graph? Strongly connected graph is a directed graph. So strongly connected graph is a directed graph such that each of its vertices can be visited from the other vertex, right? Means there is a path between every two vertices. For example, this is a strongly connected graph, right? So whenever the term strongly is used, it will be used in the sense of directed graphs. I hope you got the meaning of strongly. Now guys, what is a strongly connected component? Again, it has the same meaning as a connected component but in a directed graph, right? So let's make a graph, right? So here we can see that we have two strongly connected components, right? So why are these strongly connected components? Because from 1 I can go to 2, and from 1 I can go to 3, and similarly from 2 I can go to 3, and 2 I can go to 1, right? And from 3 also the same logic applies. So we can visit each and every vertex from each and every other vertex in the in this component, right? So now guys, tell me, can I visit 4 from 1? Yes, there is a path. If I go to 1, if I go 1 to 2, 2 to 3, and 3 to 4, but as I said that there should be a path between every two vertices, right? So there is a path between 1 to 4, but is there a path between 4 to 1? No, right? So this that's why 4 is in a different strongly connected component than 1. Why? Because we can go from 1 to 4, but we can't go from 4 to 1. There is no path between these two vertices, 4 to 1, right? So I hope you got why this means that there are two connected components in this graph, right? Strongly connected components. Okay. And also you got it right. Why I can't take whole of this in a one connected component? Now let's change this graph a little. Let's say I have one edge over 5 to 1, right? Now guys, we can easily see that there is a path between every two vertices, right? From 4 I can go to 5, and then I can go to 1, and then I can go anywhere 2 or 3, right? So now guys, this graph has one connected component, and if it has a one connected component, that means it is a strongly connected graph, right? I hope you got this. What is the meaning of strongly connected component, strongly connected graph, connected components, right? Basically strongly is used in the terms of a directed graph, right? Now let's see an algorithm that detects all the strongly connected components in a directed graph. For the algorithm's name is Kosa-Raju's algorithm. So guys, for this algorithm, first of all, we should be aware of the term DFS tree that I have already explained in the articulation points and bridges graph video, right? And secondly, there is a term back edge that also I have already explained in that video. First of all, go through that video and then come study about the Kosa-Raju's algorithm, right? Right. So let's move with the algorithm. So first of all, what we'll do is, let's say I have a directed graph, right? So guys, if it simply means here, if there is a strongly connected component, that let's say 1 2 3 is a strongly connected component, that means it's a directed graph and they are in the strongly connected component. That means ki I can go from 3 to 1 also, 1 to 3, 1 to 2 also, and 2 to 3 also, right? Basically they are in a cycle, right? You can see this, you can easily understand this. Why? Because it's a directed graph. So if it's a directed graph and these vertices are in a cycle, so all the vertices in a cycle can be visited from each other, right? Because they are in a cycle, we can go over the cycle and come back to any other vertex. So somewhere the strongly connected components also tells about the cycle in a directed graph, right? Okay, now let us understand this algorithm. First of all, what we'll do is we have to understand one more thing. Let's say I have a source. Okay, I hope you know about what is a directed acyclic graph, right? Directed acyclic graph. So what is a directed acyclic graph? It's a graph that does not have a cycle, right? And on this graph we all know that we can perform topological order, right? We can have a topological sort on this directed acyclic graph. It means there is a directed graph that does not contain any cycle, right? So basically this can be an example of a directed acyclic graph because this does not has a cycle, right? Okay, so moving on forward, first of all what I'll do is I'll perform a DFS tree on this graph, on the given graph, right? So guys, tell me, if I have a directed acyclic graph, do I have any strongly connected components? Yes, I will have strongly connected components of size 1 only, right? I can't have any strongly connected component of size 2. Why? Because there cannot be two vertices x and y such that I can go from x to y and y to x. Because if I can go from x to y and I can also come back from y to x, that means there is a cycle. And if there is a cycle, then it is not a directed acyclic graph, right? So all my strongly connected components will be of size 1, right? That means I can go from one vertex to itself only, not any other vertex, and come back, right? Okay. So let's understand this algorithm, Kosaraju's algorithm for strongly connected components. First of all, what I'll do is I'll maintain a DFS tree. I'll do a DFS tree. So let's take a big example to understand more of a DFS tree and back edges. So guys, let's say this is the graph, and in this graph I'm performing a DFS tree. So let's say I started 1. Okay, I can start at any vertex, it doesn't matter. So let me start at 1. I'll go to 2, then I'll go to 3, right? And after this I cannot go to 1. Why? Because 1 is already visited, right? So basically DFS tree gives me a tree of a graph in which all the vertices are visited in a order, right? So this is a back edge. I will not visit this edge, the edge in the white, right? So after 3 I'll go to 4, from 4 I will go to 5, I'll go to 6, and again I'll get a back edge, right? And I won't go through this edge, right? So basically you saw that if I remove these white edges, let's remove these back edges, basically this will form a tree, right? Why? Because there will be no cycle, and this is happening because I cannot visit a same vertex twice, right? So if I cannot visit a same vertex twice, that means I cannot go through a cycle. And if a graph does not contain a cycle and it contains all the nodes, it is a tree, right? First of all, I'll perform a DFS tree on the graph, right? Now guys, there is a special ordering that we'll do here. Let me write it first. So let's name it order. Okay, what does this order means? This order means, okay, let's say we have a vector named order. Okay, let's say I have some x here in the vector somewhere before a y. Okay, there are two elements in this vector. There are many elements in the vector, but these two elements, what are they representing? That if x is before y, that means कि we can go from x to y. Okay, I'll give you an example, you understand it better. That means if x came before y in this order, in order vector, that means there is a path from y to x. Okay, so if there exists a path from y to x, then x will always come before order, right? If there does not exist a path from y to x, that means the graph can be in a different graph can have different connected components, right? So basically right now I'm considering a case for one connected component of the graph, right? That means I have not divided this graph into further components, because for every component I'll apply the same logic, right? Okay, so for I'm talking about a component. So let's say if I can go from y to x, then x will come before y in the order, right? So for how can I maintain this order? how can I maintain this order? Like, how can I fill up this order vector? I can fill up this order vector by first of all visiting the subtree of a particular node and then pushing it back, right? So from one, where I'll go? From one I went to two. Okay, let me write it here only. Let's say this is an order vector. So from 1 I am going to 2, and then I am going to 3, 4, 5, 6. So when I come back to 5, what I'll do is I'll push 6 in the vector. Okay. Now when I leave 5, I'll push 5 in the vector. Then I'll push 4, then I'll push 3, 2 and 1. When I leave a vertex, then I'll push that vertex in the vector. Why am I doing so? Because whenever I leave a vertex, before leaving a vertex, I have already visited all of its subtrees, right? If I have visited all of its subtrees, then I can ensure that all the nodes that I have visited in the subtrees that are already pushed in the vector, right? Why? Because before leaving 4 I went to 5, then I went to 6, I left 6, I pushed it in the vector, I left 5, I pushed it in the vector, then I left 4, I pushed it in the vector, right? So basically what I'll do is whenever I leave a vertex in the DFS, I'll push that vertex in the vector, right? Okay, let's take another example for you to be more clear. Then I'll explain you why are we doing this. Let's say this 1 2 4 2 3 4, right? So if I start a DFS from 2 from 1, what I'll go to 2, I'll leave 2, right? Then first of all I'll push 2 in my stack. Why? I left 2. Then I went to 3, I'll push 3. Then I went to 4, I'll push 4, and then I leave 1, right? Because I have visited all its subtrees. Then I'll push 1 in the order. So this will be my order vector for this graph. We can easily see that if there is a path from y to x, then y will always come after x in the order vector. Okay, let me write it for you to be more clear. You can also try for various graphs to fill this order vector. Okay, so let me write it here. If there is a path from y to x in DFS tree, then x appears before y in the order vector. It's very important to understand this thing first. Okay, so I hope you got this order vector of various graphs. Let me make another graph. Let's say I have this graph 1 2 3. Okay, let me show you one thing, that the order vector, they may be different, right? Why? Because I can also say na, for this graph only I can also say ki I can fill 4 3 2 1 in this way, right? Again the property will hold na, because I can go from 1 to 2, 1 to 3 and 3 to 4, right? The property should hold. There can be different varieties of this order vector, right? But order vector will contain all the elements in the end, because we will visit every element in the graph, right? So let me make this graph. Okay, eraser 4, and let's say I have this 5 3, and then I have this 5, right? So it won't matter, it doesn't matter ki from where I am starting my depth first search. I can start my depth first search from 4, right? Let's start a DFS from 4 instead of 1. Okay, so if I start a DFS from 4, where it will go? It will go to 3, and then it will go to 5, right? Basically it will go to 5, it will leave it, I'll fill 5 here. It will go to 3, it will leave it, I'll fill 3 here, and it will then leave 4, I'll fill 4 here, right? Now after starting a DFS from 2, I'll see that these are already visited, so these won't come in my tree, right? So after this I'll fill 2, and then finally there will be a DFS from 1, I'll fill it with 1, right? So guys, this thing already ensures it. If I fill a node after visiting all its subtrees, it will ensure one thing, that for all the vertices that I can visit from a particular node, they will come in front of the order vector, right? Why? Because first I am visiting them and then I am leaving them, right? So when I leave them, I'll fill them first, and after that I'll fill the current node. I hope you got this. We can easily see that there is a path from 1 to 5, so 5 comes before 1. There is a path from 2 to 3, so 3 comes before 2. There is a path from 1 to 2, so 2 comes before 1, right? So I'll perform a DFS tree, and in that DFS tree, what I'll do is I'll make an order vector. Okay, I will code it in the next video. Right now, let us understand the another concept. I hope the order vector concept is clear to you all. I've given many examples. Now, guys, we all know that this order vector contains elements. If I okay, if I start from back of this order vector, I can see that this from this I can visit many other nodes, right, that are on the left, right? So basically, what we'll do is we'll have a reverse graph. The algorithm says ki take a reverse graph. You'll get this. Take a reverse graph of the given graph, right? Now if I take a reverse graph, what will happen if I take a reverse graph? Let me make you an example. Okay, so this was the real graph, and let me okay, real, and let me reverse it. This is not an edge. Okay, I'm just reversing the graph. Reversing the graph means reversing all its edges, right? So guys, there's one thing that in a cycle, if I can go from vertex x to vertex y in a original graph, and if I can also go from vertex x to vertex y in the reverse graph, right? So if there is a cycle, this condition will always hold, na? If I'll reverse the graph, then also I can go from x to y. You can easily see I can go from 1 to 3, 1 to 2, and 2 to 3, right? And in the reverse graph also I can go from 1 to 3, right, and 1 to 2. Why is this happening? Because if I reverse a cycle, the property doesn't change, na? I can visit each and every other vertex in the cycle, right? So basically, what I'm trying to explain it to you here is, if I reverse a graph, and still I am able to visit some vertex from some vertex to another vertex y, then there is a cycle. That means x and y are in a cycle. I hope you got this, right? Okay, let's take another example. Let's say there is no cycle between these vertices. Okay, now I can go from let's make an order vector for this. Okay, that means ki first of all I'll fill if I start a DFS from 1, I'll fill 2. First of all I'll fill 4, right? Then I'll fill 3, I'll fill 2, and I'll fill 1, right? So I started a DFS from 1, so this was the vector I'll fill, right? Now guys, we can easily see that all those vertices from which I can go to another vertex, let's say x to y, x are on the right of y, right? So let me reverse this graph now. Okay, this is my reverse graph. Now guys, I will check key from 1 can I visit any vertex that I already visited, in my original graph, right? So from 1 in my original graph I can go to 2, I can go to 3, I can go to 4. But guys, in my reverse graph, can I go from 1 to any other vertex? We can easily see that I can't go from 1 to any other vertex, right? Because I can't leave 1, because there is no other edge. There is only one edge that is pointing towards 1 in my reverse graph, right? So from 1 I cannot go to any other vertex, so it will be only in its own connected component. Okay, so this is one connected component and it contains one strongly connected, right? Now from 2 I'll check if can I go again on the left hand side, can I go somewhere, because what are the nodes on the left side of this 2? These are all the nodes that can be visited in the original graph, right? So from 2 also I cannot go anywhere. 2 itself is in a strongly connected component. Again from 3 I cannot go to 4, right, in the reverse graph. Again 3 is itself in a strongly connected component, and 4 is itself in a strongly connected component, right? Now I'll take a final example for you to understand it, then I'll code this, right? The final example, let's take an example that I discussed above. initially. So basically the main part of this algorithm is that if I'm considering a vertex as a source and I can go to sink, right? If I can go from a source to a sink, and in the reverse graph also, that means if I make sink as the source, right, and source as this sink, means I reverse this graph, and still I can go from source to sink in the reverse graph, right? That means that both the source and the sink are in the cycle. If they are not in a cycle, then this is never possible, right? Because if I reverse a cycle, let's say I have a cycle, if I reverse this cycle, still I will be able to visit all the nodes that are in this cycle, right? So I hope you got the basic intuition behind this algorithm. What is it trying to explain it to you, right? Yeah, let's move forward. Let's move on with this algorithm, this example. Let me fill in an order vector. You can start from anywhere by filling this order, right? So let's start from 1. I'll go to 2, 3, 4, 5, 6. So basically 6, 5, 4, 3, 2, 1. This will be my order, right? I have made an extra one here. 6, 5, 4, 3, 2, 1. Right. Now guys, what I'll say ki, yeah, from 1 can I again go to any other vertex in the reverse graph? Let's make a reverse graph, okay? So from 1, let me make a reverse graph. It will give me 3, it will give me 2, and it will give me 1. This will give me, okay, reverse graph. This edge is reversed. 4, 5, 6, and 5, right? So this is a reverse graph. Now from 1 can I go to any vertex that is on the left of it? That means from 1 can I go to any other vertex? So from 1 I can check that in the reverse graph I can go to 3, and 3 was on the left of the order, right? What does this mean? From 1 I can go to 3 in the original graph, and from 1 I can go to 3 in the reverse graph. That means 1 and 3 should be in a cycle, right? So basically from 1 I can go to 3 in the reverse graph, and from 3 I can go to 1, I can go to 2 in the reverse graph. Yes, so both 3 and 2 were on the left of 1, right? So I'll take them in a single component. Now from 3 I cannot go anywhere, not to 4, not to 5, not to 6, because this edge is reversed, right? This is a strongly connected component of the graph. Now again what I'll do is I'll start a depth first search from 2. Now 2 was already visited, so I won't go in it. Again I'll start a depth of search from 3. 3 was already visited. Visited means that I visited them once. So when I was in the depth first search from 1, I visited 3 and I visited 2, right? So I made them in a separate component. Now I'll start a depth of search for 4 and it was not visited. So in the reverse graph I'll go to 6, I'll go to 5. Both 5 and 6 were not visited. So basically 4, 5, 6 will be in a strongly connected component. I hope you got the idea behind this algorithm, right? Now let's make a different case, a little different case, right? So let us say there was an edge between 5 and 1, right? So guys, in the reverse graph there will be edge between 1 and 5. So when I'll start a depth first search from 1 and I'll go in the reverse graph, let me start a DFS from 1 and go in the reverse graph, right? So I'll start from 1. I am currently here. I can go to 3, I can go to 2, right? So 1, 2 are 2 and 3 are in the same component. Still I can go to 5. 5 is in the same component. I can go to 4, 4 is in the same component. I can go to 6, 6 is in the same component. So all of them are in the same component. Why? Because all of them were not visited, and when I started a depth first search from 1, I can visit all these vertices. Means there was a path from 1 to all these vertices, right? So if there is a path from 1 to all these vertices in the reverse graph, and if there is a path from 1 to all these vertices in the original graph, that means all these vertices are in a cycle, right? So for the code, I'll code it in the next video. I hope you got this. Try making graphs and implementing this approach, okay? I'll code the algorithm and then I will discuss its complexity, right? Okay, see you in the next video. Hello everyone, let us code the Codeforces algorithm that I discussed in the previous video, right? So first of all, what I need to do is let us input a graph. Let's input a graph, make a graph, right? Okay, so this is a directed graph, and we also saw that we need a reverse graph for this, right? So let's take a reverse graph called GRR, right? And GR is the original graph. So in a reverse graph, what I'll push X in the adjacency list of Y, right? Because it's a reverse graph, right? So let me write a graph here, or let's take this example only. 1 to 2, 2 to 3, there are 6 vertices, and 1 2 3 4 5 6 7, there are 7 edges. So there's an edge between 1 to 2, 2 to 3, 3 to 1, right? 3 to 4, 4 to 5, 5 to 6, 6 to 7, right? So these were the edges in this given graph that I explained to you, right? After removing this vertex, okay, so this is my graph that I inputted: 4 to 5, 5 to 6, and 6 to 4, not 7, right? Now it's good. So basically I have inputted a graph right now. Now what I need to do is, first of all, I need to fill the order vector that I discussed with you. Let's take an vector called order, right? So what does order vector mean? Order vector means ki if there is a vertex that if there is a path from vertex x to y in the DFS tree, then y should come before x in the order, right? Y should come before x in the order, right? So how will I fill this? Let's take a visited array so that I don't get in a loop, right? Start a DFS from, okay, from any node I can start a DFS. Start from, so basically what I'll do is, if the vertex is not visited, DFS, start a DFS, right? DFS from I, right? Void DFS. Let's take a current and mark it visited, right? Now for auto x in graph of current, let's go in adjacency list of this graph. So if not visited x, DFS x, right? So this will perform a simple DFS and mark all the vertexes visited, right? So after this ends, see, why have I done this? Because I can start from any vertex, right? And there also may be different connected components of the graph, right? The graph may be in a different components, right? So after this, after I have visited all its subtrees, what I need to do is, I need to push back the current vertex in the order, right? So PB is actually pushback, right? So I have pushed the current vertex in the order. That was what I discussed with you, right? Now guys, after done with this, okay, after being done with this, what we need to do is, we have to start from the back side of the order, right? We have to start from the back side of the order. And if I have visited a current vertex, then I have to seek here in the reverse graph where I can go, right? So let's start from the back side of the order. For I equals to n, I greater than equal to 1, I minus, right? So let me fill this, okay. So what I need to do is, I need to perform another DFS on the reverse graph, right? So that I can see now what all vertices can I visit from the current vertex, right? So if not visited I, so first of all we have to mark the visited as 0. So let's set it as 0, right? Because I am using it again, okay, visited. So if I have not visited, not I, this time what I have is order of I, right? Because order of I contains a particular node, right? So if I have not visited order of I, what I'll do is, I'll start a depth first search. So when I'll start a depth first search, I have to start this depth first search on the reverse graph. So DFS reverse, let's name it reverse, okay. Start the DFS from order I, right? So basically let's do a depth first search in the reverse graph. Okay, let me mark it as visited current node, and again let me perform a depth first search. Let me copy this only. Auto X in reverse graph, right? So I performed a depth first reverse on the reverse graph, right? So if I have not visited it, I'll just start a reverse depth first search. Now guys, if I get into a DFS and all the nodes that I will visit, they will be marked in a same component, right? So let's make an array and component array. Okay, so it will tell me in which component are these nodes. Okay, so whenever I am going in a DFS, what I'll do is I'll increase the component by 1. Okay, so let's say int color equals to 1, right? So I'll give a color to this so that all of them will be marked in the same color. Same color means same component. Okay, and after coming out from this color, what I'll do is color plus plus, right? So whenever I'll go into a DFS, when I'll come in this if condition, then there will be another color for the another strongly connected component, right? So basically let's take a color here so that we can mark these nodes, right? And color, right? So mark component of current equals to color, right? Let's try to run this code now so that there are no errors. Let us check if there are any errors. Right, there are no errors. Now let's print it the component of every node. Okay, cout I and component of I. Okay, right. So what I saw here is that 1 2 3 are in the same component called 2, right? And 4 5 6 are in the same component called 3, right? So I have marked component as this color, and this color started from 2, right? Okay, so I hope you got this. How does I get a component for a particular value I, right? Okay, we can also do one thing, that for every node I can keep this track. If what I can do is that's, yeah, it's up to you how you'll do this. I have already marked 1 as 1 first component, 2 as 1, 3 as 1. That means they are all in the same component. Or what you can do is you can take a vector, and in that vector you can do it like this: component of 1 dot pushback 1. All those vertices in the first component are in this component 1 vector, right? So we can also write it this way: vector int in component, let's say there are n components, so component of in component color dot pushback color, right? So basically in component 0 represents all the components in the 0th component, and in component 1 represents all the connected vertices in the first connected component, right? This is all up to you. You can try this if you want, and there are other ways to save about it, but I hope you got the Kosa-Raju's algorithm of finding the strongly connected components of a graph, right? So guys, thank you for watching the video. Okay, one more thing, let us discuss the time complexity of this. Okay, so basically what I have done is I have ran a 2 depth first search, right? So in the first depth first search I am not visiting a node twice, every node is being visited once, so it's a order of n, right? In the depth first search reverse function, again the same thing is happening. If I have not visited it, then I'll go and visit it, right? So I will visit every node once only, so this is also of order of n. So the total complexity is O(n plus n), that is order of n only, right? So in order of n I can find the strongly connected components of a directed graph. by Kosa-Raju's algorithm as described here. Okay, thank you guys.
Hi everyone. So now we are going to see the implementation of Kosa-Raju algorithm for finding strongly connected components in a given directed graph. So I will start by writing the main function in which I will take the input for the graph. Okay, and I'm not going to make entire graph class. I will just create a vector to store the array of vectors to store the adjacency list. Okay, so vector int graph n. If there are n nodes, so I have a array of vectors, and each element in the array is a vector. Okay, so that will so that graph of 0 will give me, okay, these are the nodes that are connected with the node 0. Okay, maybe 1 2 3, something like this. Similarly, graph of 1, graph of 2, and graph of n minus 1. And another thing I'm going to do, at the same time when I'm taking input, I will also construct a reverse graph that will help me to uh, make my implementation easy in the algorithm. Otherwise, you can create a function that reverses the given graph and returns you a copy of it. Okay, so I am assuming I have n vertices numbered from 0 to n minus 1, and I have m edges. So for each edge, I'm going to take input the edges from x to y. So what I say, okay, graph of x dot push back y. So that means there is an edge from x to y, and at the same time in my reverse graph I'm going to push, there is an edge from y to x. So this completes the input part of my graph. And let us create a function void solve that is going to solve the problem of connected components for us. So here we are going to get the original graph and the reversed graph. I just call it as reverse graph, and I'm going to get the number of uh, vertices I have in the graph. Okay, so our first step is to do the DFS and create an ordering. So for that I need to create a visited array. Let us set this array as 0, and also I'm going to create a vector that will behave like a stack. Okay, so in the step 1 we need to do a simple DFS, and we need to sort the vertices according to DFS finish time. Okay, I will rather use the word store. Okay, so store the vertices in the vector according to DFS finish time. So what we will do, we will just iterate through all the vertices, and if a vertex is not visited, we will initiate a DFS call from that particular vertex, so that the entire component that can be traversed from that vertex is visited. Okay, so to the DFS function I give the graph, and I give the node I, and I give visited, and I also give the stack, because the result will be stored in the stack. So let us create a DFS function that will do the work for us. So void DFS, we get the graph, the visited array, and the stack. So we are going to pass the stack vector by reference, because this is going to be modified. Okay, so we should pass it by reference. So every time you come to a node, you mark it as visited, and then you find the neighbors of that node. So for auto neighbor, that is there in graph of the node I. So currently you are at node I, so neighbor, for neighbor you can just iterate on the adjacency list of that node, and you can see if that neighbor is not visited. Okay, then you make a DFS call there. So DFS of graph neighbor visited, and you give the stack. And when you're returning from a node, okay, so at this point your function call is complete. Function call is complete. That means you are going back. For example, if you came at a node 1, from here you could have gone to 2 3 4 5. Okay, so what will happen is, you go here, you come back, you go here, you come back, you go here, you come back, and from here you go back. So when you're going back from a node, you basically add that node in the stack. So stack dot push back that particular node, that is I. Okay. So this completes the DFS function that we need to use in the step 1. So this work is done, and here at this point we have the ordering that is actually stored in the stack vector. Okay, so step 2 is we need to reverse the graph. So that step we have already done while taking input, so it is also done. So let us go to step 3. So do DFS according to the vertices given in the stack. Okay, according to the ordering given in the stack. So we need to iterate on the stack from right to left. Okay, so what we can say is, so although you cannot iterate over the stack, but either you do the pop operation, but since we have used a vector, we can actually iterate on the stack. So starting from the last element till the first element or the 0th element, what I can do is I will again do a DFS. Okay, so this time we are again going to do DFS. So what we will do, we will reset this visited array as 0. So I'm going to say memset visited 0 and n. So remember, this algorithm is a 2-pass algorithm. That means we are traversing the graph 2 times. So next time when you're going to visit it, you again reset everything with 0. So every vertex is not visited now. Okay, so let us see what is the node at the last of the stack. So that is nothing but node equals to stack of x. So that is the index. If that node is not visited, what you do, you say, okay, there is a component starting from this node. There is a component starting from this node, and I will make a DFS call that will visit this entire component. So we can say, okay, make a DFS call, and this DFS function will be little different because we do not need to generate the ordering. So I will just copy this kind of a function and I will make some changes here. Okay, so let me call it as DFS2. I need to get a graph, that is fine. I need to get the vertex I visited, but I no longer need this particular stack. Okay, so I just remove this thing and I remove this thing, and let me call it as DFS2. So it's a simple DFS function which does not take the stack. So what we can do, we can say, okay, make a call on DFS2 function. What graph you need to give? You need to give the reverse graph in this case, and what node? That is node, and you need to give the visited array. That's it, and this will visit all the nodes of that connected component. Okay, so if I simply do something like this, char component name, let's say a, by default the first component is named as a. So what you can do is you can say, okay, we are outputting this component followed by component name, maybe put a arrow or something like this, and then you can say, okay, cout endl and component name plus plus. Okay, so that will give a name of b to the next component. That's it. So this is another DFS call. So this is step 3 of the algorithm. So I think we are done and we can try to run our code. So we can call the solve function and graph, reverse graph, and n. So graph, reverse graph, and n, number of vertices, that is n. Okay, build is done, and let's try to run this code. Now I need a graph, so let us construct our original graph. So we have this. Okay, so we said we have 3 components: component 1, component 2, and component 3. So let's see. So we have how many vertices? 7 vertices, 8 edges, from 2 to 1, 1 to 0, 0 to 2, 0 to 3, 3 to 5, 5 to 6, 6 to 3 and 3 to 4. Okay, we missed out one thing, right? So we just forgot to print the node here, right? So we should say cout I, build the code again, run the code again. Okay, so you can see we are able to get the three components. Component A is 0 1 2, this is A. Component B is 3 6 5, so this is B. And component C is 4, so this is C. So I hope this code is quite clear to you, and you would be able to find the connected components in a directed graph. Hi everyone. So in this lecture we will talk about a new type of a data structure that is called as disjoint union set, or DSU in short, and another name is union find data structure. Okay, so this data structure is quite important to study because one very common application of this data structure is in finding cycles in an undirected graph, and this application is also used in an algorithm called as Cruxell's algorithm that we will study in this course. Okay, so that's why it's really important that we study this data structure, and now let us try to see what this data structure is all about. So this data structure is basically deals with disjoint sets. Okay, so let me tell you what is a disjoint set, or what are disjoint sets. For example, let's say you have some collection of elements 1 2 3 4, and let's say 5 6 7. Okay, so I have divided these elements into two sets, S1 and S2. Maybe there is some more elements, let's say 8 and 9, and they are in the set S3. Now all of these three sets are disjoint sets. So disjoint basically means non-overlapping. Okay, so you can see there is no element that is common in all of these sets, so they are non-overlapping sets. So these are what disjoint set means. So this data structure basically supports two operations. One operation is called as union, and another operation is called as find. So basically find operation would work something like this. If I say okay, find the set in which the element 8 is present, so this operation would return set S3. Okay, if I say okay, find the set in which element 6 is present, so this will return me the set S2. So find function basically helps us to find the set in which a particular element is lying. And another very important function is the union function. So this is what the find function is, and let us see what is the meaning of union. So union basically means we want to merge two sets into one. Okay, so merge two sets into one. So maybe I can say okay, take the union of the set S2 and S3. So what will happen is these two sets will be gone and a new set will be created in which we will have all the elements from set S2 and from set S3. Another way could be we can say okay, union the sets containing the element 6 and the set containing the element 8. So this could be another way in which we do not give the name of the set, but we just identify okay, you are going to merge the sets in which element 6 is present and element 8 is present. So this will again lead to merger of set S2 and S3, and we will get a new set. Okay, so our goal is to design such a data structure that does to that performs these two functions in the minimum possible time complexity. Okay, so we will start with a little basic approach that will do it in linear time, and by adding some optimizations we will try to bring this complexity to O1. Okay, So we'll start with the basic union find data structure in this section that will does the work in ON time, but by adding some optimizations. So those optimizations are called as one optimization that we will do is called as path compression, and another optimization is called as union by rank. So we will learn about these two techniques. Okay, firstly we will do the basics, then we will learn about two optimization techniques that will reduce the time complexity of the find and the union operations to almost O1 time. So I hope you got an idea what we are going to do. We want to design a data structure such that we are able to implement the find operation. Find will take an element and it will return the set in which the element is present, and we want to implement the union operation that is going to merge two sets into one. I can also say, okay, merge S1 and S4. So this will give me a bigger set that will contain all the elements from 1 to 9. Okay, so something like this. So we are going to see why this is going to be important in the next video. Hi everyone, so now let us see how we can implement the DSU, disjoint set union data structure. And before that we are going to see how you can visualize it. Okay, let us try to do some operations and visualize them. So let us say we have four different sets, 1 2 3 and 4. Okay, and these are four disjoint sets containing one element each, and you can see each element corresponds to one set. Now suppose you get an operation on the form, you have to unite 1 and 2. Okay, and you also need to find out in which set this element belongs to. So initially 1 belongs to its own set, 2 belongs to its own set, 3 belongs to its own set, and 4 belongs to its own set. So what we can do, we can actually maintain an array. Okay, let's say 1 2 3 and 4, and we can initialize these values with -1. So if you see that if some node has a value, so let me call this as a parent array. If parent of some node is -1, that means that node is itself the set. That node itself is the parent of that particular set, something like this. So let's say if we want to unite 1 and 2, what we can do, that means we need to establish a connection between 1 and 2 and put them into a single set. Okay, so what we will do, we will say, okay, let us make 1 as a parent of 2. Okay, either you can do this or you can make 2 as a parent of 1, both are fine. So what we will do, in this array we will say, okay, 2 is now having a parent 1. So 2 is having a parent 1, that's fine. So let's say you get another query that says take a union of 3 and 4. So what you will do, you will establish a connection between them, and you can say, okay, 3 is now parent of 4. Now what is going to happen, 4 is now connected with 3 like this. Now you can see you have two sets, and now we need to identify these sets. Okay, so 4 is now having a parent 3. So can you identify the two sets from this array? So of course yes. So there is a set whose leader element. Okay, so what is the leader? So leader is the representative of the set, and I'm calling the root of the set as the leader of the set. Okay, so we need to find out the leader of the set, and that in this case is 1. And here also in this set, the representative or the leader of this particular set is going to be 3. So if you just iterate over this array, you see there are two places where you're having a value -1. That means that is one set and another set is at 3. So clearly we can see from the diagram also, there is a set that is starting from 1 and there is a set that is starting from 3, or the leader is 3. Okay, let us say you get another query in which you have to do a union of, let's say, 1 and 4. Okay, so how you can perform the union? So give it a thought, think for a minute, and come up with an answer. Okay, so let us discuss. So what I need to do, I need to do a union of 1 and 4. That means I need to establish this connection, and this will make sure that all the elements now lie in the same set. So for that we need to find out the set in which the element 1 belongs. So element 1 belongs to set 1. Okay, so let me say, okay, the parent of 1 or the set 1 is 1, and I need to find out the set in which the element 4 belongs. So this set is nothing but 3. So set id is same as the leader of that particular set. So set 2 is going to be 3. For this I found out two values: the first set in which the element 1 belongs, and the second set in which set 2 belongs. This is nothing but this is the set. This is given by the find function. Find the set in which element 1 belongs, and this is given by find the set in which element 4 belongs. So this find function gives you the value 3. What we can do, we can check if these two values are not same. If 1 is not same as 3, okay, or let's say if s1 is not equal to s2, what we can do, we can actually merge them by saying, okay, parent of s2 is equal to s1. So what we are doing here, parent of s2, so parent of s2, parent of 3 is going to be s1. So parent of 3 is going to be s1. So s1 is going to be 1. We are going to say, okay, parent of 3 is going to be s1. So this connection will get established, and here we can say parent of 3 is nothing but 1. So this is what you will get in the parent array. Okay, sorry, the arrow should be like this. Okay, this is how. So what we are trying to do is we are visualizing the union operation. Okay, so or the find operation in the form of a tree, and the actual work that we are doing is happening on the array. So we will visualize this whole operation in the form of a tree, but the implementation will be based upon a array. So we need to maintain a parent array that stores, okay, what is the parent of 4. So parent of 4 is 3. So let us look at what is the parent of 3. Parent of 3 is 1. Okay, so 4 is having a parent 3. You can see here. What is the parent of 3? 3 is having a parent of 1. And what is the parent of 1? That is -1. So that means both 4 and 3 belong to set 1. Okay, what is the parent of 2? That is 1. So that means 2 also belongs to set 1. So all of these elements belong to the same set. Now suppose you get another edge that says, okay, do a union of 2 comma 3. Okay, so if I just combine this particular edge, so you can see this becomes a cyclic graph. So how do we detect a cycle? Now let me come to the application. How do you detect whether the graph contains a cycle or not? So in order to detect the cycle, what you need to do, you need to find out what is the set in which 2 is present. So set 2 is, you can see 2 is having a parent 1, 1 is having a value -1. That means parent of 2, that is set 1, that is nothing but find 2. So that will give you 1. And another element is 3. So you can say, okay, 3 belongs to a set that is also 1. That is also 1. So that means both of these elements belong to the same set, and if you're going to add an edge that connects the two elements that are already in the same set, that means you're creating one more path. That means you're creating a cycle. So if both of these values are same, you're going to say cycle is present. Okay, and you can see if you connect all these edges, you will end up getting a cycle in the graph. Okay, so I hope you got an idea. How do we find a parent? So for finding the parent basically means the root or the leader of the set. Okay, so do not confuse, I'm using two terms. One is the root or the leader of the set. Okay, one is the parent. So parent could mean the immediate parent. For example, 4 is having a parent 3, but every time I talk about parent in general, it means super parent or the leader of the set. Okay, so what is the final parent of 4? That is 1. That is, I'm interested in finding out in which set 4 belongs. So that set is set 1. Okay, so let us see how we can write the code for the same. So firstly we will write the pseudocode and then we will go into the implementation in the next video. Hi everyone, so now we are going to discuss the pseudocode. Okay, so in the last video we said we had 4 nodes like this, and then we took the edges and we called the union operation over the edge. For example, we have the edge 1 comma 2, we say okay, combine them into a single set. Then we said okay, we can also visualize the same by making a tree like this. So 2 is having a parent 1, and we also made an array in which we said okay, we will have the elements like this 1 2 3 4. Initially everything is -1, then you start picking edges. You said 2 is having a parent 1, so you put this parent as 1. Then you combine 3 comma 4, so you can say 4 is having a parent 3, and it looks something like this. Then you say okay, combine 1 and 4, so you say 4 is having a parent 3 and 1 is having a parent 1. Okay, so that means root of the set. So how do we combine this? We say okay, parent of 4 should be equal to parent of 1, so that means this gets connected. So during this process 3 gets the parent as 1, and we said union 2 comma 3. So now you see what is the parent of 2, that is 1, what is the parent of 3, that is also 1, and both of them belong to the same set. So that basically leads us to this cycle. So 1 and 4 are connected. Okay, and we say okay, 2 is having a parent 1, 3 is having a parent 1, that means both are in the same set. That means if we just add this edge will give us a cycle in the graph. So we need to write two functions. One is the find function. Okay, so find function will return the super parent or the leader of the set. Okay, so let us say you get some element I here, let's say int I. So how do you find out the parent of some particular element? So let us see how you can do it recursively. Let us see the pseudocode. Okay, so it's going to be actually pretty easy. So you can see if parent of I is equal to -1. For that, for example, if you want to find the parent of 1, the parent of 1 is -1 in the array, so you will return the value I itself. So this will give you the same node as the parent of that node. Okay, otherwise you can make a recursive call return find, and here you give parent of I. So the parent array just stores the immediate parent. For example, if you want to find parent of 4, so you make a recursive call to the find function. You say okay, go and find the parent of 3. So in 3 you say okay, go and find parent of 1. So you make a call on 1. In 1 you say okay, go and find parent of 1. So that basically ends up at the same value that hits the base case. So eventually you get the parent of 4 as 1 using the find function. The final parent of 1 or the leader of the set, using the find function you get this as 1. So this is how you can actually implement the find function, and you can say in the worst case the find function can end up getting an order and complexity. For example, if I give you something of this form, let's say 1 is connected with 2, 2 is connected with 3, 3 is connected with 4. Suppose the graph is something like this, and you say okay, I want to find out the parent of 1. So in that case you say okay, 1 will take you to the 2, 2 will take you to the 3, 3 will take you to the 4. The parent of 1 is 4 in this case, and you can see this traversal can take order of n time. So in this case the find operation will take on time in the worst case. Okay, so this is something we will optimize in the coming videos, but now let us discuss the union function. How do we do a union between two sets? Let's say void union, and maybe I want to do a union between 1 and 4. Okay, so let us assume we have done the work till now and we want to do union of 1 and 4. So the sets that we have till now is like this after the first two steps. What we get, we get, okay, do a union between the elements a and b. So in this case, let's say a is 1 and b is 4. So what we need to do, we need to find out what is the set in which a is present. Okay, so a equals to, or let's say parent of a, or whatever you can say, set 1, set in which a is present. So that is set 1, that is find a. Set 2, the set in which b is present. You say, okay, find b. So set 1 and set 2 are the leaders of the set in which a and b are present, and if this is not equal, then that means you can merge them. If a is not equal to b, oh sorry, if s1 is not equal to s2, that's what I'm going to do. If s1 is not equal to s2, then I can say parent of s2. Okay, so in this case, s1 will be 1. Okay, so s1 will be 1 for this value of a and b, and s2 will be 3. Okay, so if you find out the parent of 4 from just this diagram, that parent or the super parent would be 3. So s2 will be 3. So I'm going to say parent of s2, that is parent of 3, is going to be s1. So that means 3 is now going to connected with 1, like this. Okay, so like this. So if s1 is not equal to s2, we can say parent of s2 equals to s1, or you can do the other way around, parent of s1 equals to s2, but follow only one notation. Okay, now you may ask, what is the time complexity of union function? So it is going to use the find function. Okay, and if find function takes on time, the union function can also take on time in the worst case. Okay, we are combining these two, and this is a O1 step, but here it can take time. This is the pseudocode for the union function. Now I will show you in the actual code how we can do it. Hi everyone, so now I will show you how you can solve this problem of cycle detection in a undirected graph using DSU. Okay, so let's see how we can do it. So firstly we need to make a graph, and this time I'm going to make a graph in the form of a list of edges. So I'm going to include the list header file, and let us define graph class. So we will have the number of vertices, we will have a list of pair of intent. Okay, so I'm not going to create an adjacency list, I'm just going to create a edge list. So for example, if your graph is like this, 1 2 3 and 4, so I'm going to store the edge 1 comma 2, 2 comma 3 and 3 comma 4. That's what I'm going to store. Okay, so this representation of the graph is called as edge list. So let us maintain this edge list. So we need to make a constructor that will get the vertices, and we need to make a function called add edge. So we have an edge from u to v, so we can say, okay, l dot push back, it's just going to make a pair of u comma v. That's it. That's the implementation of the graph. Now what we need to implement, we need to implement a function bool contains cycle, and to do that we will use the DSU logic. Okay, so we will use the DSU logic to check if graph contains cycle or not. For that, let me tell you what I'm going to do. Let us say you have a graph like this. So let's say this is your graph 1 2 3 and 4, and let us say you make four, you have 4 vertices. So in the beginning you make 4 disjoint sets, and let us say these are the edges 1 2 3 and 4. So you pick the first edge 1 and 2, you combine 1 and 2 in the same set. Then you pick this edge 3 and 4, you combine them into the same set. Then you pick this edge 2 and 3, you combine them into the same set. And then you pick this edge 1 and 4. So you see, okay, what is the set in which 1 is belonging to? So 1 is belonging to a set, let's say this is 1. And what is the set in which 4 is belonging to? Let's say 4 is also belonging to the set 1. So as soon as you get two nodes that belong to the same set, you can say a cycle is present. So this is something that we are going to do. So in the beginning, we are going to assume that each node is a set of its own. Okay, so there are v number of nodes. So in the beginning, you can say, okay, there are v number of sets that are present. So that is something we are going to do. So let us implement the DSU functions first, then we will use them in the contain cycle algorithm. So one, we need to implement the find function, another we need to implement the union function. We have discussed the pseudocode in the last video. So int find set, you will get the element I, and you will also get the parent array. Okay, and here you can check in the base case if parent of I equals -1. That means you have to return that particular node, you return I. Otherwise you return find set parent of I and parent array. Okay, so we have made a recursive function that finds the leader of the set. Okay, and let us discuss the union function. So let me just call this as void union. So union is a keyword in C++ or in C. I will just call this as union set. So I get X, I get Y, and I get the parent array. So firstly, let us say you want to do a union between X and Y. So maybe uh, this is some node X and this is some node, let's say Y. So you want to combine these two nodes in the single set. Okay, for that, what do you need to do? You need to find out the parent of X. Maybe let's say this is the node S1. You need to find out the parent of Y. Let's say this is the node S2, and you need to connect them. So if you connect them, all of these nodes will lie in the same set. So this is what we are going to do. So let us find the set 1 and let us find the set 2. So int S1, that is going to be given by find set function, find X. S2, find the set for the node Y. You give this X comma parent and Y comma parent. We actually use this parent array to recursively reach the parent and parent of parent until we reach the root node. If both of them are not equal, if S1 is not equal to S2, then we can merge them by saying parent of S1, okay, or parent of S2 equal to S1. So you can either do this way or that way. So you can even do this. So in my case, I'm doing parent of S1 equals to S. I'm connecting it like this. Okay, so you can see. So that's the union operation. Okay, that's it. Now we need to write this function contains cycle. So let's see how we can write this function. For that, we need to first maintain a parent array. Int star parent equals to new int v plus 1, and for int I equals to 0, let's say v, I less than v, I plus plus. In the beginning, I can say parent of every node is -1. That means each node is a set in itself. That's it. Otherwise, we can iterate over the edge list. So for auto edge that lies in the list L, what I can do, I can pick, there is an edge between two elements. Okay, so this edge, let's say edge list is like this 1 comma 2 2 comma 3 and so on. So if I say, okay, this is an edge, so edge dot first will give me the first node, edge dot second will give me the second node. So I can say int I equals to h dot first, int j equals to h dot second, s1, that is the parent of, or the super parent of I, s2 equals to find set of j. If both of them are not equal, then we will union them. Okay, we can say, okay, union set s1, s2 and parent. But if both of them are equal, that means both of them are lying in the same set. That means you found out a cycle. So you can say return true, and finally you can say return false. And here you can delete the parent array because that is dynamically created. That's it. This is your contains cycle function. So this statement should come here. Yeah. So I will just repeat what I have done here. For example, you have this graph, let's say. So this graph contains cycle, and let's say the edges are 1 2, 2 3, 3 4 and 4 1. So what do? You iterate over all the edges. You pick the first edge, that is 1 1 to 2. You say, okay, initially 1 2 3 4 are 4 different sets. You say, okay, find the parent of 1, find the parent of 2. 1 is having a parent 1, 2 is having a parent 2. So you union them. So it becomes something like this. Then you say, okay, go to the next edge. 2 is having a parent 2, 3 is having a parent 3. So both of them are different, so you union them. So you connect them. Then you go to the next node, 3 and 4. So 3 is having a parent 3, 4 is having a parent 4. So you connect them. So you make, say, parent of 4 is nothing but 3. Next you go to 4 comma 1. So 4 is having a parent 3, or let's say like this. You connect them like this. So you say 4 is having a parent 4, and 1 is also having a parent 4. So if you now find out the parent of 1, so 1 was having a parent 2, 2 was having a parent 3, 3 is having a parent 4. So eventually 1 is having a parent 4 and 4 is also having a parent 1. That means both of them belong to the same set. So s1 and s2 will be same, and you will end up getting this particular set. So you will return true. Else maybe you can say, okay, see out same parents, and you can print the value of s1 and s2. And maybe let us try to construct this graph and see the result. So int main, it's a graph G containing 4 vertices, G dot add edge 1 comma 2, G dot add edge 2 comma 3, G dot add edge 3 comma 4, G dot add edge 4 comma 1. See out G dot contains cycle handle. Build our code and let us run our code. So let's say tsu1. So it says same parents 0 and 0, and yeah, I should put a handle here. Okay, so there is one problem. The indexing should be done from 0 actually, not from 1 0 1 1 2 2 3 and 3 0. Okay, so this should be the correct indexing. So it says same parent 3 and 3. So you can see it's like this. So the actual graph that we would be building would look something like this, the tree visualization. Okay, so this is the tree visualization of the code. 0 is having a parent 1, 1 is having a parent 2, 2 is having a parent 3, and when you do finally 3 is having a parent 3 and 0 is also having a parent 3, so it says same parents 3 and 3, and 1 basically says that means a cycle is present. And if I just remove the last edge, if I remove this edge, so my output would be 0, so it will return false. This line should output 0, that means cycle is not present. And you can see the output is 0, that means cycle is not present. So I hope you guys got an idea how we can detect cycle using DSU. That's all for this video. Thank you. Hi everyone. So now in this video I will talk about two optimizations one by one. First is the path compression optimization that we will implement inside the find function. Okay. So let us try to understand what is the meaning of path compression optimization. Okay. So this will actually help us to reduce the time complexity of the find function. So now suppose for some given graph, when we construct this DSU tree from the parent array, let us assume the tree looks something like this. Okay, let me just draw this tree, and we will discuss what this optimization is going to do for us. Now suppose this is a tree for some given graph, okay, for some set of edges that we have scanned till now. And now suppose you get a query, you need to find out the set in which, let's say, the element 7 is present. So what happens? So you basically traverse this entire tree till the top, and you end up getting, okay, this is present in set 1. So what do? You traverse this entire path till the top, and then you find out, okay, this 7 is present in the set 1. Maybe sometime later you again get some edge, maybe 7 is connected with 13. You need to find out in which set 7 is present. Okay, because in a graph 7 can be connected with multiple nodes. Okay, every time you get an edge, you need to find out, okay, in which set 7 is present, in which set 13 is present, and so on. Okay, for very first time you make this query for the set 7, you traverse the path from the this node till the root node, or the ultimate parent of the set, that is 1. So what you can do during this traversal is you can actually compress this path. Okay, so we can actually compress this path using path compression. Okay, so if I just make this parent array, so you will see that 1 2 3 4 5 6 7 8, 7 is having a parent of 5, and 5 is having a parent of 3, 3 is having a parent of 2, 2 is having a parent of 1, and similarly other nodes have some parent. Okay, so what you can do when you're going from 7 to 5, from 5 to 3, 3 to 2, and 2 to 1, so you see, okay, we can do one thing. We can say, okay, 2 is directly connected with 1, that is perfectly fine, and 4 is directly connected with 2, so we will not change it. But we see there is 3 which is connected with 2, and 2 is connected with 1, so we can make 3 as the direct child of 1. So we can say, okay, we will do something like this. We will say 3 is now a direct child of 1, so this branch of 3 will remain as it is, because we didn't went into this branch. We are working with this branch only, and we said, okay, 5 is having a parent 3, 3 is having a parent 2, 2 is having a parent 1. So what we do, we compress the path of 5. We say, okay, 5 is also going to have a direct parent of 1, so 3 is having a parent 1, 5 is having a parent 1. Similarly, we will say 7 is going to have a parent of, so 7 is going to have a parent of. Okay, so this is what path compression is going to do. So it is basically, it's going to optimize it is going to reduce the path length that you will need to traverse the next time you call the find function for some given node whose path is already optimized. Now if you check, what is the parent of 7 next time. So it is just can be calculated in one step. So 7 is connected with 1, 5 is connected with 1, 3 is connected with 1, 2 is connected with 1. Maybe next time you run a query find 6. So what will happen again is uh, you will pick 6 and you will make the direct parent, uh, you will make it as a direct child of 1, maybe something like this. 1 is now connected with 6, 7, and 6 is connected with 8, and 1 is also connected with 3, 1 is connected with 2 and 4. So every time you get an query, you try to reduce the path from that node to the root node by making those nodes as direct children of the root node. So now let us see what changes we need to do to the find function so that it works in this particular manner. So let me show you the pseudocode. So in the pseudocode, you will write something like this: int find. Here you get the node I, and in the base case, you check if I equals -1. That means you are already at the root node. So you say return I. Otherwise, here we are going to make one change. So in the previous code, we said we are going to return find of parent of I. Okay, so we were just doing a return thing, but here what we are going to do, we are going to say parent of I will be now updated by this particular value. So you can see earlier in this case the parent of 7 was 5, and 5 was having a parent 3, 3 was having a parent 2, and 2 was having a parent 1. So what happens now? So in this case, 7 makes a call to 5, 5 makes a call to 3, 3 makes a call to 1. So when you come back, you say, okay, no, there won't be 2, there would be 1. 5 will say, okay, earlier the parent was 3, so parent of 5. Okay, so this is returned recursively from the base case. So you're doing two things. You're doing updation plus you're returning with the value. So 3 comes to know that my actual parent is 1, so you update this value as 1. Sorry, here. 5 comes to know that my actual parent is 1, so you update this value here. 7 comes to know that my actual parent is 1, or the final parent is 1, so you directly update the parent of 7 as 1. So you can see 7 is connected with 1, 5 is connected with 1, 3 is connected with 1, and 2 is also connected with. So this is what is called as path compression optimization. Okay. So let me show you in the code as well. So what you need to do here is, okay, this is the DSU code that we have written. I will just make a copy of this code and I will call this as dsu2.cpp. Okay, and in the find function, what you're going to do, you're going to say, okay, before returning, I will update the parent of I by the parent returned by the recursive call, because that is the final parent and that will be stored in the parent array. So earlier we were only doing a return statement, now we are also doing an updation. All the nodes that came in the path from bottom to top will now have the same parent. Okay, so, or if you want to break it down into two steps, you can just do it. So here we are doing updation plus return. So I'm just going to say this is the change that we have done for the path compression optimization. So in the next video, we will discuss one more optimization that is called as union by rank. Hi everyone. So now we will discuss about the second optimization that is called as union by rank. Okay. So remember in the union function, what we have done is, suppose you had two tree visualizations for a graph, okay, for a set of connected components. Let's say there is a component 1, 2, 3 and 4. Okay, and let's say there is a component 5 that is having these two nodes 5 and 6. And now say, let us assume that there is an edge between 1 and 5. So what we used to do is we connect the first component with the second one. Okay, so this is what we do. But doing this attaches the bigger component, may attach the bigger component with the smaller component. Okay, and if there are a lot of nodes, and then if you do a lookup for this particular node, you will actually have to traverse one edge extra every time. Okay, so what the idea is, union by rank says you store the rank of each set. Okay, rank of each set or rank of each node. So that basically means how many nodes are there in that particular set. So for example, if I say what is the rank of one, so one contains, let's say, 1 2 3 4 4 nodes. And what is rank of 5? So this contains 2 nodes. So rank of 5 is 2. So the idea is a union by rank basically says you have to attach the smaller tree with the bigger tree. Okay, so instead of doing uh, always the first tree will get connected to the second tree, what you will do, you will attach the smaller tree with the bigger tree. Ideally, in this case, what we will do is we will not change the parent of 1. Okay, we will not change the parent of 1, but we will just attach 5 and 6 with 1, like this. Okay, so this is what union by rank. So if you need to implement union by rank, what you need to do, for each node you need to maintain a rank value. Okay, so if you're merging two sets, so let us say this set was having a rank 4, this set was having a rank 2. So when you merge these two sets into a one, so this final set will have a rank of 6. Okay, so you can say you can maintain a rank array in which the node 1 is going to have a rank of something like this. Okay, and all other nodes can have rank as 0, or you can just put some value inside it. Okay, that will not matter much to us, because we are only interested in finding out the rank of the leader of that particular set. That value is really important for us. Otherwise you can keep the old values. For example, before merging the set, uh, 5 was having a rank 2. Okay, so maybe you can just keep this value as 2. You can, before merging 5 and 6, 6 was having a rank of 1, something like this. So either you can keep those values, or you can make those values as 0 later on. That's perfectly fine. The only thing that we are interested in finding out is what is the rank of the leader of the set, because when you're going to merge two sets, you should know which set is bigger and which set is smaller. That's the whole idea. Okay, so in order to calculate the rank, generally people can use size, or they can keep some kind of height as well. Okay, so but we will do the implementation using size, that is also fine. So that's what union by rank is. And after doing these two optimizations, okay, the overall complexity of DSU comes out to be approximately order of 1. Okay, so it's almost like a constant. Okay, we are not going to discuss the proof. You can refer internet for the proof. But if you add these two optimizations in your DSU, the complexity of the find and the union function gets reduced to almost order of 1 from order of. Okay, and even just by you, if even if you use path compression, then also it is order of log n on average. But if you add the second optimization as well, the complexity reduces further, and it becomes almost order of 1. So we will discuss the code for union by rank now. Okay, so I have opened up the previous code in which we have implemented the path compression optimization. Now I will update the code for union set. Okay, we will update this part, and little bit update we will have to do in the function contains cycle, because we need to initialize ranks for every node. Okay, so that's what we are going to do. So firstly we will make a ranks array. Okay, and for each node we are going to store a rank. So in the beginning there are v number of sets, and each node is a set in itself. We can say rank of every set is same, that is 1, because each set contains one node. 1 2 3 4 5 6. Each set has a parent -1 or the node itself, and the rank is 1. Okay, something like this we are doing here. That's it. And the other change, rest of the code for cycle detection will remain same. The other change that we need to do is we need to do it in the function union set. So to the union function we also need to find out, we also need to send the rank array. So here we will accept the rank array as well. Okay, and earlier what we were doing, we were saying okay, parent of s1 equals to s2. Now this statement will depend upon the size of the set. Okay, that's what we are trying to do. So I will make changes here. So we can say if set1 is not same as s2. So firstly we need to find out, okay, what is the super parent or the leader of the set x, and what is the super parent or the representative of the set containing node y. So those values are stored in s1 and s2. If they are not equal, then we can perform the merger. And what will be the new parent? That will depend upon rank. If rank of s1 is less than rank of s2, then s2 will be the parent. Okay, and I can say parent of s1 will be s2. And since you're attaching a smaller tree, let's say this is s1 and this is s2. S2 contains 4 nodes, s1 contains 3 nodes. So you will attach s1 as a child of s2. Okay, and as a result the rank of s2 will be increased by this factor. So you will add this to the rank of s2. So you can say rank of s2 plus equals to rank of s1. So rank is nothing but the size of the set. Otherwise you will do the other way around. You will say parent of s2 will be s1, and rank of s1 will be incremented by rank of. That's it. That's the complementary case, and this is called as union by rank. Okay, we just decided which tree will get attached to which tree. Okay, so this is what is union by rank, and I think rest of the code is same. Maybe I will just remove this line here, and finally I can run my code if there is no error. So this is dsu2, so I do not get any cycle. And if I add this edge, g dot add edge 3 comma 0, so that should give me the cycle. So you can see we are getting 1. That means cycle is present in this particular graph. So this is 0 1, 1 is connected with 2, 2 is connected with 3, and 3 is connected with 0. So this graph contains cycle. Okay, so I hope you got an idea of union by rank, and that's all for this video. Hi everyone, so in this video I'm going to dry run the union by rank and path compression algorithm on one example. So in this video we are given this graph. Okay, so I've just drawn this graph here. Okay, and this is the rank array, and this is the parent array. So I will tell you how you can check if the cycle is present in the graph or not. So we have added these edges in this particular order in the adjacency list. So let us start building our set data structure, the DSU data structure, and we will try to visualize it. Okay, so when we say okay, g dot add edge 0 comma 1, so in the beginning uh, we have to assume all the sets are independent. Okay, so we are picking the first edge 0 comma 1, so we basically connect 0 and 1. Okay, so now both have the rank 1, so in the beginning both have the rank 1. Okay, so what we can do is we will enter the else case. Let me show you. Okay, so in the union algorithm you will find out the parent of 0 is 0 and the parent of 1 is 1 if you just call this method find set. Okay, so it will return 0 for 0 and it will return 1 for 1, so both of them have a different parent. So in the union find algorithm you will see if rank of s1 is less than s2, so this is not the case, we will enter the else case. So we'll say parent of s2 equals to s1, so in that case 0 will become the parent of 1. So we will have something like this. We will have 0 that is now parent of 1. Next time we get another edge 1 comma 2. So what happens? Let us see. We find the parent of 1, that is 0. So parent of everything was minus 1 in the beginning, but parent of 1 is now 0. Parent of 0 is also 0. And 1 comma 2. So we need to find parent of 2. So 2 was having a value minus 1 here. That means 2 is parent of itself. Parent of 2 is 2. Parent of 1 is 0. So how do we unite them? When we unite 2 and 3, we say let us go here. Now because 2 is a smaller set, okay, and this is a bigger set, so 0 is now having a rank of 2 because we added one node here. Okay, and 2 is a smaller set, because of union by rank 2 will also get attached with 0 like this. Okay, so 2 will also get the parent as 0. Next time, so we have scanned this particular edge, no cycle till now. So this edge is scanned, this edge is scanned. Next time we go to 2 comma 3. So 2 comma 3. So 3 is having, so this value is actually minus 1. So where I have not written anything, that is minus 1. So 3 is now having parent this node at itself, and 2 is now having a parent 0. So what we do, we will attach 3 directly with the 0 like this. Okay, so if I just show you the code, what we are doing here. So we say parent of s2, so parent of s2, so it is 2 comma 3. So 3 is s2, parent of 3 equals to s1. So what is s1? S1 is nothing but it's the parent of 2. When you're connecting 2 and 3, so the parent of 2 will now become the parent of 3 because of the logic that we have written. So we have even scanned this edge now. So next we get 0 comma 4. So parent of 4 is 4 itself and parent of 0 is 0 itself. Okay, so this value should be actually minus 1 here. So parent of 0 is 0 itself. So and this value is also minus 1. Okay, so this value is also, this is minus 1 minus 1. So both of them are different. So parent of 4 is 4 and parent of 0 is 0. So if we want to merge them, so that would mean connect the smaller node with the bigger node. So 4 will also get connected directly under 0 like this. 4 will also have a parent 0 now. So we are done with this edge. Next we get the edge, this edge is connected. Okay, next we get the edge 5 comma 6. So we are talking about this particular edge. Okay, so in this case both have the rank 1. So 5 is having a rank 1, 6 is having a rank 1. Okay, so I forgot to update these ranks. So all the nodes that are connected under 0, they will add 1 to the rank of 0. So 0 is going to have a rank of 5 till this point. This number is going to be 5. Okay, so I pick this edge 5 comma 6. So this is another set. So what set we have? We have 4 0 1 2. This is one part of the graph, and we have 5 comma 6. Till now no cycle is present. Okay, so we say, okay, let us make 5 as a parent of 6 or something like this. So let us see what we have done. Then 0 and 1, so 0 and 1, so yes, so 5 will become parent of 6. So 6 will now have a parent as 5. So parent of 6 would be now 5, and rank of 5 would now become 2, like this. Okay, so this edge is done. Next we have 2 and 5. So 2 and 5 are connected. So what we will do, we will say, okay, 2 and 5 are connected, so we will make 5 as a direct child of 0. So we will basically attach 5 comma 6 here. Okay, so this is how you will see where the path compression thing will come in future. So now 6 is having a longer path to reach 6. So 5 comma 6, so you connect 5 with 6. So this is a smaller tree, this is a subtree. We are not going till 6. We started with 5 and we connected it with 0. Okay, so this is how this edge is done. Then you have 2 comma 5. Now 2 comma 5, sorry, 2 comma 5 is, I think it's done. 5 comma 6 is done, 2 comma 5 is also done. Now you have this edge 2 comma 6. Now you can see, if as soon as you pick this particular edge, okay, 2 comma 3, so this was also done, this edge. As soon as you pick this particular edge, you will end up getting a cycle. Why? Because if you find the parent of 2, that is going to be 0, and if you find the parent of 6, so when you make a call to find parent of 6, due to path compression, this node will move from this point to this point, and for the next time when you will find the parent of 6, you will get this parent in O1 time, and you can see parent of 6 is now also 0, parent of 5 is also 0, and parent of 2 is also 0. You see 2 is having a parent 0, 6 is having a parent 0, and you will end up getting that this graph contains a cycle. So let me just run this code. Okay, and you can see it contains a cycle. Okay, and if I just remove this edge, you will see we won't get a cycle. Yeah, so we got a segmentation fault, probably because I'm not given the correct number of nodes in the graph. So the number of nodes should be 7. So let me build the code and run. So now, okay, this graph contains a cycle, and if I just comment out this edge and run this code again, so this does not contain a cycle because this is the edge that is creating a cycle, and you can see this graph does not contain a cycle. And if you want, you can actually print the parent array as well. So I can say for int I equals to 0, I less than v, I plus plus, cout parent of I. Okay, and we can also print the rank array. So for int I equals to 0, I less than v, I plus plus, and I can say cout rank of I handle. And let us see the output for this graph. Yeah, so it's actually returning true from this point. So just let me just remove this edge as of now. So you can see this is the parent array. Okay, so you can see all the nodes have the parent as 0 except 6, which has a parent of 5. And since we removed the last node 2 comma 6, it cancelled our call, which could lead to path compression. Okay, so if we just make this call here, let me just uh, show you. If I uh, just skip this particular statement, so that will not return true, but that will show you the parent array. Okay, now you can see if we add this edge 2 comma 6, the parent of 6 is also updated as 0, and this also leads to path compression, and you can see the direct parent of 6 is actually 0. So that is the thing I was telling you. Okay, so what happened earlier was the graph was looking something like this: 0, we have parent 1, we have a child 4, we have a child 2, we have a child 3, we have 5, we have 6. So when you add this h2 comma 6, so when you make a call to the find function for 6, it removes this node from this point due to path compression, and it attaches here, and you can see 6 is having a parent 0 and 2 is also having a parent 0, and you get cycle detected and so on. Okay, so here I've removed the return true statement so that we come to the end of the code. And earlier, if before this step, 6 was having a parent that was 5, and you can see the rank of 0 is 7 in both the cases, and rest all elements have a rank of 1 or 2. Okay, so 5 was having a rank of 2 because two elements were connected here. Oh, so this rank is not important to us. You can even make it 0 after the merger. So it's only important when a particular node is the leader of the set. Once it is removed from the leader position of the set, the rank does not matter. Okay, so we will say return true, and that's the entire code. So I hope this thing is now clear. It was a bit tricky, I think, for the people who are going it for the first time. You will find it little tricky, but if you dry run it, if you go through it carefully 2 or 3 times, you will definitely get it. Okay, so that's all for this video. Thank you guys. Hi everyone, so in this video I'm going to discuss a problem from the challenges section. So this problem is from Hacker Blocks and also in the course. So in the graph challenges, the problem name is pairing. Although it's an easy problem, it can be solved using multiple ways, but I will discuss the approach using DSU method so that you can see how DSU can be used to solve some problems as well. So it says there are n number of cities numbered from 0 to n minus 1. For example, the value of n is 5. So there are 4 cities, let's say 0, 1. There are 5 cities numbered from 0 to 4. You have to choose 2 cities such that there is no path from first city to another city. Okay, that means these 2 cities should be in different components. You're given information in the form of m pairs such that there is a undirected road between city x and y. Okay, and we have to find out the number of ways in which cities can be chosen. So number of ways in which you can select 2 cities so that there is no path between x and y, or a and b, whatever you want to call. For example, in this case you are given 5 cities and 3 edges. So first edge is between 0 and 1, that's it. Next edge is between 2 and 3, so this is the edge, and third edge is between 0 and 4. Okay, so now clearly you can see there are 2 connected components. This is the first component and this is the another component. Okay, you can have more as well. So you need to find out the number of ways in which you can pick 2 cities, let's say x and y, such that there is no direct connection between x and y. Okay, so if you pick both the cities from the same connected component, so this condition will not get satisfied. So that means both the cities should belong to 2 different connected components. Okay, so in this case I have only 2 components, so I can pick the first city from the first connected component in 3 ways. and I can pick the second city from the second connected component in two ways, that is 2C1. So my answer would be 6 ways. But if maybe if you have one more connected component, then you also have to make pairs. Okay, so you pick you have three choices from here, you have two choices from here, you also have two choices from here, you have two choices from here. Okay, so in that case you will also add the ways to select the number of countries, number of components, and then picking one from each component. Okay, so something like this. An easier formulation would be if you can simply find out what is the size of each connected component. For example, this is the connected component, this has a size 3, this is another connected component, this has a size 2. So what one thing you can do is you can actually subtract from total ways those ways in which both the cities are coming from the same component. Okay, so for example, the total ways to select any two cities would be 5C2, that is 10. Okay, minus those ways in which you're selecting both the cities from the same component. Okay, so um, in how many ways you can select both the cities from the component 1, that is 3C2, that is 3, so 10 minus 3. In how many ways you can select both the cities from the second component, that is 2C2, that is 1. So this answer is also okay. So you can easily solve this using BFS or DFS. What do you need to do? You need to find out the size of each connected component. Okay, so let's say there are k number of components. So your final answer would be NC2 minus summation over all the k components, and let's say modest denotes the size of the component C2. Okay, so total ways minus those ways in which you are selecting both the cities from the same component would be your total answer. And this is something you can easily find out using the connected component logic. Okay, and even the value of k. So you can try the code on your own. Okay, so what I will do now is I will also discuss how you can actually use DSU as well to solve this particular problem. So let me give you an idea. You can see answer for this is 6. So let me give you an idea. Okay, so what you can do is we have studied about union by rank and path compression. So let us say whatever edges I get. So in the beginning I have 5 different sets. Let's say 0, 1, 2, 3 and 4. So maybe I get some connections. I say okay, connect 0 and 1. Then I get, let's say, connect 0 and 4. And let us assume that 0 is the representative of this set. Okay, so in this case rank of 0 would be 3, and let us say 2 and 3 are also connected, and let's say 2 is the representative of this particular set. So rank of 2 would be, so what you can do is we can iterate over all the nodes. We can say okay, for I equals to 0, I less than 4, I can go to every node and I can find out in how many ways this node can be connected with some other node. Okay, so if I talk about 1, the node 1, so can I connect node 1 with 0? No, I can't. Can I connect node 1 with 4? No, I can't. But one can connect with all other nodes that are not lying in the connected component in which 1 is present. Okay, so that means with 1 there are how many options? There are 2 options. One can either connect with 2 or one can form a pair with 3. So one has 2 options. Okay, so how do you find this answer? 2. The total number of nodes is 5. The number of nodes in the component in which 1 is present is nothing but 5 minus rank of super parent or the leader or the set in which 1 is present. That is going to be the rank or the set of that particular size. Okay, so let me just call 0 as super parent of 1. So super parent of 1. Okay, the rank of super parent of 1 is going to be 3. 5 minus 3 is also 2. So 1 is going to form 2 options. What about 0? 0 has super parent itself, so it is going to be 5 minus 3. 0 is also going to have 2 options, so let me also write those options: 1 comma 2, 1 comma 3, 0 comma 2, 0 comma 3. What about 4? 4 is also going to have total number of nodes in all the sets is 5, minus those nodes which are lying in the set that contains the node 4. So that means rank of super parent of 4, so that is 3, so that is also 2. 4 also has two options, 4 comma 2 and 4 comma 3. Let us do the same thing for 2 and 3. So if you go to 2, you know, okay, total number of nodes is 5 minus those nodes which are present in the same component. There are 2 nodes, this is going to be 3. So 2 has 3 options. 2 can pair with 0, 2 can pair with 1, 2 can pair with 4. And what about 3? So it is going to be 5 minus those nodes which are present in the same component as 3. So there are 2 nodes, so you are left with 3 options. So 3 also has 3 options. 3 can pair with 0, 3 can pair with 1, 3 can pair with 4. Now you can see some of the ways are getting repeated. So because 0 comma 2 and 2 comma 0 are considered twice, so these two are same. So what you can do is you can add up all of these options and you can divide your final answer by 2. So if you just sum it up, it becomes 12, and 12 by 2 becomes 6. Okay, so I hope you guys are getting the logic. The idea is to pick one node from one component and the other node from some other component. Even if you have multiple components, for example, if you have components like these, so one can club with all the nodes except the nodes in this particular component. So that's why I'm doing n minus uh, rank of whatever is the super parent or the ultimate parent of 1. Okay, so I can say find the set that contains. So this is how I can do it using DSU. So int pairing is the function name, so I initialize the parent, I initialize the rank matrix. I say okay, parent of I is -1, rank of I is 1. In the beginning all nodes are separate. Then I'm going to scan the edges. Okay, so here I've written the code to scan the edges, and here we have the DSU code using path compression and union by rank. So let me show you carefully how you can quickly write the code for this particular problem. Okay, so let us say int answer is 0. So in the edge list, so I've maintained the edge list here. I'm going to iterate over all the edges and I'm going to come add those edges in my DSU. So I can say for auto edge that lies in the list L, I would be edge dot first, J would be edge dot second. Okay, I will find out the set in which I is lying. I will find out the set in which J is lying, and I will unite them. So I can say okay, do the union of the sets S1, S2, parent and the rank array. Okay, so after this what we will have? We will have this structure ready. We know 0 is combined with 1 and 4 and 2 and 3 are separate. Okay, so we just added these edges. So now we have two sets. Okay, now we are going to iterate over all the nodes. So go to all the nodes. So let us say answer is 0 for int I equals to 0, I less than b, I plus plus. So to your answer, how many nodes can be combined with 0? So 0 can combine with 2 nodes. So answer would be b minus rank of super parent of 0. So that is going to be given by find set of 0, that is ith node. That's it. And finally you can say return answer by 2. So from here you can say return answer by 2 because you're combining, counting each answer 2 times. 0 is connected with 2, 2 is connected with 0, so that is being counted twice. And from here you can say delete the parent array and delete the rank array as well. Let's build the code. Okay, there is one error here. Int answer is 0. Yeah, so this does not need to be defined twice. That's it. Now let us try to run our code. So 5 vertices, 3 edges, 0 1 1 4 2 3. So you can see answer is 6, which is correct. And let me give you another case. 5 vertices, 3 edges, 0 1 1 2, and let's say 3 4. Okay, yeah, this one is actually same. So let us try to submit this code on coding blocks online. Okay. Okay, so we got a correct answer on all the test cases, and I hope you would be able to solve this problem. So I would recommend you try using BFS DFS as well to solve this question, and I just show you the application of DSU in this question.
Hello everyone. Now let us see a question, a beautiful question from Spodge based on the concept of disjoint set union. We'll see how we can use disjoint set union that has already been discussed in this question, right? So when you read the question, you won't get an idea like how to do it, where to do it, but just try to think about it, right? So this is the question. Read the question properly, and after that pause the video for a minute or like take your time, think about it, and then after that I'll explain it to you. Okay, yes. So now I'm beginning with the solution for this. First of all, what we have here, right? We have I hope you have read the question and gone through the examples and thought about it, right? So first of all, what we have is we have an array length n, right? So just let's make an array of length n. Okay, I think we should take the second example that will benefit us, like array of length 10 and there are 5 queries, right? Right, so 1 2 3 10. Now we have 5 queries, and in each query what we have is we have to color. We have an L, R and a color, right? L, R and C. So what we have to do over here is we have to color the array from L to R, that is from AL to AR. We have to mark its color equals to C, right? We are given a triplet in a query, and from L to R we have to mark its color C. Let me just go over an example this, and then we'll see the optimizations that can be done. First of all, we have 3 to 9 and color it 13, right? So just let's color it 13, right? 3 to 9 13. After that, guys, I have 1 to 4 9, and we know, as given in the question, if I'm coloring over a range again, then my older color will overlap, right? So the new color will come over the older color, right? It will overwrite. So from 1 to 4 I have to color 9. So just remove these two and let's make it 9, right? After this I have from 2 to 10, fill it with 14, right? So let's fill it with 14 from 2 to 10. originally there is 0, right? If a block is empty, it's 0 over there. So let's fill it with 14. Right. And after this we have 2 to 7 10, 6 to 9 44. 2 to 7 we have 10, just overwrite it. Right. And after that we have 6 to 9 44. Right. So from 6 to 9 we have 44. So this was a quick run over the example. This is my final array: 9 10 10 10 10 44 4 times and 14. Like, see the output, right? I hope you understood the question. Question says that from L to R, fill it with color C. So guys, if in each query, if I run a loop from let's say I equals to L till I less than equal to R and I plus plus, and in each query if I say, let's say color of I equals to C, right? So I can perform a for loop for each query, right? So how much time will this for loop take? It will take O of R minus L plus 1 time, that is the range, right? In the worst case, the range can be On, right? Let's say all the queries are from 1 to N, right? So if one query takes On and there are like M queries, M or Q, let's fix it Q, okay? So there are Q queries. So what will be total complexity into Q? That will be O of N into Q, right? So N into Q will range up to 10 to the power 10, and it won't work in 1 second. Basically it's N square, right? Because N and Q are approximately 2 into 10 to the power 5. So I was just trying to explain you why won't brute force work over here, because of the time limit, right? Now let us see another thing. Let me just write those queries over here, right? The queries are 39154. Here we'll have an observation, a good observation: 2 10 14 and 2 7 10. 10 14 and 2 7 10 and 6 9 44, right? So guys, we all know that if I have let's say I filled up a range with a color C, and then I have another range which comes after this, right? And I have to fill it with color D, then this part will overlap with color D, right? This part. What does this mean? That if I have a range and that range overlaps some other range, then the previous range is useless. I mean that this part is useless, right? And again, let's say if after even this there's another query and this gives me a range, this, like, let's say it was C1, it was C2, and it was C3. So basically we know now that now this part will be filled with color C3, right? Because it has overlapped it. And even more, this part will also be filled with color C3, right? So from here we can say that I don't need those ranges which have been overlapped by previous ranges, right? So guys, if I say that I'm coloring 1 to 10 with 5, and then I'm coloring 2 to 6 with 10, so guys, this 2 to 6 completely overlaps 1 to 5, 1 to 10, right? So in the range from 1 to 10, 2 to 6 will be filled with 10 and all else will be filled with 5. So basically the latest range, the range that comes, the query that comes after a particular query, right? The latest query, the after query, right? The query which has a greater index, that affects more than the previous queries, right? So guys, can I not do this? That I'll just save those queries, I'll save all these queries and I start going backwards, right? Because if I start going backwards, okay, pause the video now, think about it, then I'll just continue. So if I start going backward, guys, let's take this example: 6 to 9 44. So if I'll fill 6 to 9, let's say this is 6 and this is 9, and I filled with 44, then guys, after this, if I get 2 to 7, let's say this was 7 and this is 2, okay, 2 to 7, and I have to fill it with 10. So do I need this range 6 to 7? Do I need to fill 6 to 7 with 10? No. Why? Because I have already got uh, on 6 and 7 I have already got 44, right? So if I already got 44 on 6 to 7, then I don't have to fill 10 on it, because that range came afterwards, right? And this range came before, right? Because now I'm trying to go in the opposite order. So if a range, if I have already colored an index with a particular color, and then there are like two ranges which overlap it, like C1 and C2, so I won't take C2, I will only take C1, right? So now what is my question left? That for every index I have to find out the first overlapping range if I start moving backwards, right? The first overlapping query if I start moving backwards in the queries, because the last over, because if I go from the starting, the last overlapping query will give me the color, the final color, right? But do I need the last overlapping query? Yes. So what I'll do is I'll start going backwards, right? And after going backwards, I just need the first query that will overlap the current element, because if after that any other query overlaps it, right, then I don't need that query. I hope you got this. See, now I'll just fill it by going in a reverse order. Let's fill this array in like going in the reverse order. Okay, let me just make it. Still you won't get the idea like why is the question being discussed in the disjoint set union thing. You'll get it, don't worry. I'm just trying to build up a solution. We'll go step by step, right? So let's start moving upwards. From 6 to 9 it is filled with 44. So initially it was 0, let's fill it with 44, right? After this 2 to 7 is filled with 10. So if I started 2, I'll fill it with 10, right? And then 6 was already done, 7 was already done, I won't overlap because 44 came after 10, right? I've already filled it. Now moving from 2 to 10 with 14. So starting from 2, don't overlap, don't already filled, and then 10 is not filled, fill it with 14, right? I filled the 10 with 14. Now what I have is fill 1 to 5 with 4. So I'll just fill here 4, and then 2, 3, 4 and 5 are already done, right? Okay, it's 9, not 4. Yeah, 9. And 8 to 9, 13, 1 to 4 is 9. Okay, it is 1 to 4, 9. Don't get confused, it's 1 to 4, 9. I filled it with. So as we saw, now we have this query left 3 to 9, and this 3 to 9 will be completely filled, so we don't have to overlap anything, override anything, right? Because we are moving backwards in the queries. So this is the final answer, right guys? Because this query was not needed and there were various elements that were not needed, that were overwritten later, right? So I hope you got the first part of the solution, that we have to move in the opposite order of the queries, and the first query that overrides it should be the answer, right? That color should be the answer for the particular index, right? Now see, again the same algorithm, if I try to move from if I again try to like write it like this, key, let's move an I from L and I less than equal to R and I plus plus, means I'm iterating over L to R, and what I'll do is, if color of I equals to 0, that means it has not been colored, then set color I equals to how much? C, right? So guys, if I try to perform this operation, this is what I am doing it while moving backwards. I'm iterating over L to R, and for each iteration I'm checking whether it's colored or not, and if it's not colored, then I'll color it, right? So how many operations does it take, guys? Again, this loop is running in how much time? R minus L plus 1, right? So this loop is again running in R minus L plus 1 step, worst case on, and for all the queries it will be O of n into Q, which will be how much? O of n square, and this won't work, right? So guys, now we have to think of an optimization for this loop, right? So why is this loop performing badly over here? This loop is performing badly because this I, whenever I'm trying to go from L to R, this particular I value is also going on all the other values that have already been colored, right? So guys, if I could just optimize this for loop and I can just like, so I don't have to apply this condition, means if I can create a solution such that I don't have to apply this if condition. What I mean to say is that the I that I'm using over in this for loop, this index I, right? I'm saying that if this I already goes over those places which is from L to R only, right? That means color I equals to 0, right? So if that I only goes on the places from L to R such that color I is 0, then I'll be able to reduce my time complexity a lot, right? Okay, what I mean to say is this. Let me just give you an example, or let me just not erase it. Okay, so right, so let's go over again with this same example. It's a good example. Let me erase this. You'll get it, don't worry. I'm saying that for a particular range, let's say 6 to 9. If I start at 6, I'll go at 6 first, I'll go at 9, I'll go at 7, I'll go at 8, I'll go at 9, right? Now if I start at 2, right? So when I started 2, I'll fill it with 10 because it was not filled. 3, 10, 10, and guys, when I reach 7, I want that whenever I reach a point and that point is already filled, then in the next step, where should I go? I should directly jump to 10. Means if I come at 6 and the range from 6 to 9 was already filled, right? Because if it was already filled, do I need to iterate over 6 to 9? No, right? So I just want the position of the index that was not filled and which was on the right of 6. The first position which was on the right of 6 and it was not filled, right? So basically, let me write it over here. What do I need? I need the first position to the right of index which has color equals to 0, right? So I want this position, right? And in O1 I need this position, that if I come at 6 and it will directly point me to 10, right? So now when I came at 6, it pointed me to 10, but 10 was greater than 7, so I'll not fill 10, right? I hope you got this. Now see, coming up one above, coming on this query, it's from 2 to 10, 14. So when I came on 2, I want this 2 to point me directly to 10, because now 10 is the first index and that is not been colored, right? And this 10 is less than equal to this R, that means it is in the range, right guys? If it is in the range, I'll color that index with 14. I hope you got what I wanted, that if whenever I am on a current index, I just want in O of 1, right? In O of 1, if I get a index which was not filled and which is on the right of particular I value, then I'll just color that index, right? So how to do this? Think about it, pause the video. See, again, let's say let's move 1 to 4. So when I reach 1 will give me the rightmost index that is not filled as 1 only, right? Now guys, I'll come on 2, right? So 2 will give me the rightmost index that is not filled as 11, and we can see 11 was greater than 4. So if I have to fill 1 and 4 only and I have reached 11, then I won't fill 11 and I also won't go more right? So basically, I hope you got me, that what do I need? I only want to go on those places which were not filled, right? So I just want those places which were not filled. So how to find those places in O1? Like for any index, how will I find that this index, let's say for a particular I want this J, right? such that this j was on the right of I and it was the first index that was not filled. And I need this for every index. I want to update it for every index. How will I do it? Pause the video, think about it, think about disjoint set union, right? Okay, let me give you a second example first, second explanation for this queries. There's a beautiful approach by, I hope, I don't know if you know it or not. There's another approach by using segment tree with lazy propagation, right? Because segment tree with lazy propagation, what does it does? It updates in a range, right? So just for a fun fact, you can also do this question using segment tree with lazy propagation, and it's a very advanced data structure and it's a very powerful data structure too, right? But segment tree with lazy propagation takes too much time, right? So it would be better if we do it using disjoint set union only, but you can also try using segment tree with lazy propagation for those who know about it, right? Okay, now what do I need? For every index I want the rightmost index that is not colored till now, right? So not colored means 0. Okay, so don't get confused. Colored means that there is some value and not colored means it is 0, right? So let us see how will I find the rightmost index that is not colored, and we'll just make an example over here. Okay, let me just give you one more quick example. Let's say we had a range and this range was colored. Okay, and then let's say we had a range and this range was colored too, and then this range was colored too, right? Now I have the query that colors this range with some other color. Let's say this was C1, C2, C3, and this is C4, right? So if this is C4, what does this mean? That yeah, this range needs to be colored with C4, this range needs to be colored with C4, this range needs to be colored with C4, and this range needs to be colored with C4, right? Okay, so how will I color a range with C4? Again, what we'll do is, see, let's say this is L and this is R. Okay, so first of all I'll find the rightmost value from L which was not colored. It was the L only, right? So C4, C4, C4 and C4 I have colored till this position. Now I have reached this starting point. Let's say it is L1. I'll find the rightmost value which was not colored and it was on the right of L1. So it will return me this position. This is R1 and this L1 will give me R1 plus 1, right? If it gives me R1 plus 1, then I'll color R1 plus 1, I'll color R plus 1 too, so on till here, right? So this will be again colored in C4. Let me write it. What I'll do is I always take the rightmost value. Okay, tell me the rightmost value which was not colored. Again I'll reach here. Let me name it L2 and R2. Again guys, L2 will give me which position? It will directly give me this position, that is R2 plus 1. Again C4, 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 and then we'll reach here. This is L3. Again L3 will give me the position R3 plus 1, right? So basically what's happening over here is, whenever I am on a particular range, let's say whenever I am on middle of a range or starting of a range or anywhere in that range, from L to R, let's say I am over here or here or here even or here, anywhere on the range, any index, but it should lie within the range that is colored, right? So for any index, what do I need? That it gives me in O1, it gives me the index R1 plus 1, R plus 1, right? I hope you got this, that what do I want from every range? If I'm at any index in a range, I want the index R1 plus R plus 1 and I have to update it also, right? Basically what does update mean? Let's say this is L1 and R1 and this was a range, and then I had another range L2 plus R2, and I filled this range, that is from R1 plus 1 to R1 plus 1 to L2 minus 1, right? That basically this range is also filled now, right? So guys, now this whole comprises of a bigger range, right? So whenever I'll be somewhere in the middle of a range, here or here or here in the next query, then all of this range should give me which position? R2 plus 1, this position, right guys? So I hope now you are able to visualize that why will I use disjoint set union over here, because I'm combining ranges and I'm trying to find the rightmost value. Okay, so what we will do, coming on the solution now, what we'll do, we'll always try to have initially what we'll do is we'll fill parent of any index equals to index only, as we usually do in a disjoint set union question, right? After this guys, when I'll try to merge two ranges, let's say I'm merging these two ranges, okay, L1 to R1 and L2 and L2 to R2. Let's say I'm merging these two indexes in these two ranges. Then what do I want is, I want the rightmost value to be the parent of the current index, right? See, let me just try run over an example again, make it more clear. So what I'll do is this. Let me write a parent array also, then erase this. See, I hope you are getting this, ki why am I using disjoint set union over here. I'll also code it in the video. Right. So let me just make a parent array, and initially everyone is their own parent. 1 2 3 5 6 8 9 10. So just make them their own parent first, right? So again, let's come on the last query, 6 to 9 44. Now I'm on 6. I'll ask the rightmost value that is not filled, not colored. So from 6 what I get is 6 itself, right? So because parent of 6 is 6, what does parent mean? Parent will always point to a rightmost value, right? So what I'll do is I'll fill 44 over here, and I'll jump to let's say I equals to get parent of I, right? And before this what I'll do is I'll just perform one other operation. The operation will be that merge or unite, whatever you say, merge I and I plus 1. This is important. So if I'll merge I and I plus 1, let's merge I and I plus 1, right? So before this what I did was I filled resultant of 6, I made it equals to 6, right? So basically let me write I and C over here, right? I and C, right? So first of all I filled it with this, I merged these two, right? Why am I merging these two? Because let's say there was another range of a particular length on the right hand side, and that whole range will be merged, and then it will return me the rightmost value, right? So I have merged I and I plus 1. So while merging, what I'll do is I want the parent to be the rightmost possible, right? So if I have to merge two components x and y, so let's say I have a parent of x, and that is super parent, right? And I have a parent of y. So if I'm merging x and y, what do I want? I want parent of x to be maximum of parent of x and parent of y. Why? Because why maximum, guys? Because maximum will give me the rightmost value that can be the parent, right? So let me merge 6 and 7 now. Let me just run it again. Let me just merge 6 and 7, and I have merged 6 and 7. The parent of 7 is 7 and parent of 6 is 6. Merge them, it will give me 7 and 7, right? Now I am on 7, right? Because I have went to I equals to get parent I. Now I am on 7. Again I'll do the same operation because I is still less than equal to R, right? And R was 9. So I'll again do the same operation. I'll fill 44 over here, and I'll merge 7 and 8. Let's merge 7 and 8. If I merge 7 and 8, what I'll get? I'll get 6, 7 and 8 with 1, right guys? Because I'm merging these two components, because 6 and 7 were already merged. Now I'm merging 8 and 6 and 7. So whole component's parent becomes 8, right? So let's merge with 8. Now again we can see that I is still less than equal to R. What does this mean? I'm still in the range. Let's fill 44 over here. Let's merge 8 and 9. So let's merge 8 and 9. What I'll get is whole component's parent equals how much? 9. The rightmost value, the maximum among both of the parents, right? Parents of 8 was 8 and parent of 9 was 9, so I'll get the maximum of both the parents. After this, what I'll do is perform this operation and then merge I and I plus 1. Right? So let's merge I and I plus 1. Again, what I got is 10. Right? Basically, right now I'm continuously editing the parent again and again so as to make clear to you that they are in the same component. Okay, so I am at 10. I goes to get parent I and it's on 10, right? So guys, now 10 is not less than equal to r, right? 10 is greater than 9, so I will not fill it. So I hope you got this, that now whenever I'll have a second query from 6 to 9, right, or 10 even, right, and I want to find the rightmost place that has not been filled, it will return me 10 in O of 1 only, because we know that get parent of I works in constant time because we use path compression, right guys? So basically I am only jumping on all those values that are not colored. So I'll come on all the indexes at one time only, right? Now I'm talking about the time complexity of the code, right? So I'm for every range I'm just jumping on all those values that are not colored by using this operation. I equals to get parent I, and get parent is the rightmost value that is not filled, right? So if I'm jumping on all those values which are not colored, not filled, right, and I'm coming on those value once in my total code, right, because when I'll be in this or here or here or here, I'll come on that place exactly once, right, because that place will be parent exactly once. If it is colored, then it won't be parent anymore because I'm merging I and I plus 1, right? The parent will be something bigger than I, right? I hope you got me. So basically what will be the total complexity of all the queries, because I'm only jumping on all the non-colored nodes. So O of n, because there are n nodes only which are not colored, and I'm going through them only once, right? I'm not traveling over them twice. So O of n for all the queries, right? So O of n and into O of constant, right? So if you want to take O of constant, you can take it because of path compression, but we all know that O of constant into O of n is O of n only, right? So basically we have solved this question in O of n time only, right? I hope you got this, that why are we going in a reverse order and why am I using the disjoint set union algorithm in this, because we want the rightmost parent which is not colored. Okay, again if I merge 5 and 10, what I have 10 over here, right? So if I merge 5 and 6, then this place will also give me 10 because 5 has been colored, 6 has been colored, 7, 8, 9 all have been colored, right? So if I come to this range at any time, if I ask the parent, it will directly give me the position 10, right? Basically my for loop will not work as I plus plus, it will work as I equals to get parent I. Okay, so let's code this solution and let's submit it on Spotch, right? So let me just copy it. Okay, so let's start the code. First of all, what I need is you can also try to code this yourself first. It will be good if you tried yourself, right? Let's take in main, and I'm just pushing two files over here. Don't worry about these files again, because the file is to take input from the input.txt you can see on the right, and this is to write the output on output.txt. okay, don't get confused, and these are for fast input output. You can even use them in your codes, right? Okay, so let's take the queries, store the queries. Okay, int n, also let's take m with it or name it q. Okay, after this let's store the queries. How to store the queries? Let's store it in L and R and C. Okay, let's store the queries here. For int Li, Ri and Qi, Ci. So I've stored all the queries. from 0 to qi, right? And now what do I need it? I need a disjoint set union, dsu, let's name it g, and let me just write that quickly. Okay, structure dsu, writing the same structure that I used in the previous code. Initially, what all do we need? I want a parent, right? So the parent will be the rightmost value, right? So let's initialize it. How to initialize it? Parent dot resize till n, right? And after this, let's fill it with parent. So the iota function fills the values from 0 to all the values. From starting from an index 0, it will fill 0 at index 0, 1 at index 1, 2 at index 2, right? Or you can use a for loop to fill the parent initial, right? It doesn't matter. Okay, so I've initialized the parent vector. Now let me just write a function called get. This get function, what will this return? It will return me the parent, or let's say the super parent of x, right? The component x. So how to write it briefly? How to write the get function briefly, guys? If x equals to px, that is parent of x, right? If x is parent of x, I'm not using whole if and else again and again, okay? I'm just writing in a concise way. Then return x. Otherwise, return parent of x equals to get parent of x, right? So this was both if and else that I used in the previous code. Else equals to parent of x, return x. Otherwise, return parent of x equals to get parent of x. Okay, so let me just make another bracket so that don't get confused in this, right? Okay, after this, let me just write a function called unite, which will unite two components, let's say x and y. Right now I'm using a briefer code, right? In the previous video I used a big code to explain it to you in detail. Now we can use a small code, right? So x equals to get x, y equals to get y. That will give me the super parent, right? And if x not equals to y, what I'll do is I'll mark parent of x equals to, okay, what do I need, guys? Again, parent of x equals to how much? Maximum of parent of x comma parent of y. Okay, it's parent. Actually use p, that's why. Parent of y, right? Again, doing the same thing. The parent of y will also be equals to maximum of parent of x and parent of, right? So it doesn't matter, don't worry, write both, okay? And right, so we got this, that if x does not equal to y, I have made the parent of x equals to parent of maximum of parent of x and parent of y, right, guys? Okay, so let's take this structure dsug. If there are some little mistakes, we'll correct them later. G dot init, initialize it with n plus 1. Why n plus 1? I can also initialize with n plus 2, right? Because I have to unite I and I plus 1. So in the worst case, I have to unite n and n plus 1, right? And if I initialize with n plus 2, I can easily unite n plus 1 with n. Okay, so let me just build it so that we don't face any errors. Yeah, no errors. Great. Right, so I've taken the disjoint set union. Now let's start iterating over all the queries, and we'll go in reverse order as I told you, right? So we are starting over all the queries. Okay, now let's take a index. And what is this index? Let me just write it over here. This index is the rightmost non-colored index, right? So for li value, for this query we have li value, right? So how to find the rightmost not colored index? Simple, I'll just say g dot get li, right? So it will in the starting only it will point to the rightmost value that is not colored. Okay, now what do I need to do is, let's go index less than equal to r till index is less than equal to r. Let's perform the operations that I wrote, right? So let's take a resultant array. Okay, and initially let's fill this array with 0, right? So let me make it 2, don't worry. So if index is less than equal to r, let's perform these operations. Resultant of index equals to how much? Ci, the color of the current query. And after this, what I need to do is g, okay, I need to g dot unite. Let's unite index and index plus 1, right? And then what I'll do is I'll just simply jump over that index. So index equals to how much? G dot get index, right? So by using this line, it directly switches me to a place that is not colored. That's why it can be a parent. Okay, rightmost. So we are only jumping on those places which are not colored, and all the places will be colored once. Basically the complexity of the code will be O of n only, right? So I hope you are getting this, why I am uniting these two, right? Okay, so what I need to do after this is simple. Let's just try to print the values. Less than equal to n, cout resultant I. Let's see if it's working on. Okay, it's r I, right? Any other changes? Right, 2776, right? 2776, and let's just fill for this. And 10 10 10 14 14. Yeah, it's good, right? So let me just try to submit it on Spotch, have a better correctness. Plus 14, paste the code, let's submit it, right? So the code works in O of n only because we are ignoring the O of constant of getting the parent, right? So let us see. Okay, we just got a runtime error, IGSEJP. That error tells me for a small mistake. Where can I get a mistake? Maybe because I think this unite function should be void. I think maybe because this, it is giving me a wrong answer. Otherwise I cannot see any other mistake in this code, right? So let us submit again. Because we don't know about spoils, right? Maybe because a compiler gives a warning, right, for this if an integer function does not return something. Maybe because this we are getting it. Let us see. 15, right? Last time we got here, right? Okay, so you can see the code is accepted. Colorful array, 0.35 seconds. Guys, I hope you got this. How and why did I use disjoint set union in this question, right? So you will get various questions in which you'll use disjoint set union, right? So thank you guys. Hello everyone, let us see what is a minimum spanning tree. In this tutorial, we'll see Kruskal's algorithm to find minimum spanning tree. And secondly, we'll also see how to code it. Basically, prerequisite for the video is you must know about disjoint set union, which is already been provided. You should see that video first. Secondly, I'll use the same code that I've already used in the disjoint set union video tutorial. Also, there is another prerequisite video that is to find cycle using disjoint set union. There has been a tutorial uploaded for both of these topics. You must also see them. Let's begin with Kruskal's algorithm to find the minimum spanning tree. First of all, let us see what is a spanning tree. Now, what is a spanning tree? Spanning tree of a graph is a subset of edges that connects whole graph into one connected component and without cycles. Let's take an example. Let's say this is the graph and these are the edges that are connected. Now what is the spanning tree of this graph? The spanning tree of this graph can be 1 to 2, 2 to 3, 3 to 4. There can be another spanning tree 1 to 3, 3 to 2, 2 to 4, right? They are different. There can be another spanning tree 1 to 2, 2 to 3 and 3 to 4, right? So guys, there are various spanning trees possible for a given graph, and what we need to do is we need to find the minimum spanning tree of a given graph. So what is a spanning tree? It's a tree of a graph that connects a graph into one connected component without any cycles, right? I hope you got what is spanning tree. So this is a spanning tree. There can be various spanning trees of a given graph. Now let us move on to minimum spanning tree. If I give weights to these edges, let's give some weights 1, 2, 2, 2, 3 and 3. Now let's try to find out minimum spanning trees of this graph. Let us see what are the total weights of these spanning trees that I have already drawn. I have taken this edge from 1 to 2, that's of weight 1, 2 to 3 of weight 2 and 3 to 4 of weight 3. Now 1 to 3 is of weight 2, 2 to 3 is of weight 2 and 2 to 4 is of weight 3. Same for this 1, 2, 3. So if I take the total weight will be 1 plus 2 plus 3 6, 2 plus 2 plus 3 7, 1 plus 3 plus 4 1 plus 2 plus 3 6. So I can say that there are different types of spanning trees possible for a given graph. So let's find out what is minimum spanning tree. Minimum spanning tree is a subset of edges of a connected unweighted directed graph that connects all the vertices together. Let us see what is the minimum spanning tree for the graph that I have made here. Let's make this edge 1 to 2, 1 to 3 and I have to connect 4 and I connected 4 by 3. Now let's assume that 6 is the weight of the minimum weight of the spanning tree of the given graph. You can pause this video and you can try to make different spanning trees of the given graph. Or can we find out minimum spanning tree of this graph? Let's take one more case. Okay. First of all, add 1 to 2. Now let's join 2 and 3. Now I cannot take this edge 1 to 3 edge, but I can take another edge that is 1 to 4, right? So what is the total weight of the given graph, given tree? Basically this is a spanning tree, right? And its total weight is 5. So our assumption for 6, that 6 was the minimum spanning tree, was wrong. Why? Because I have already found out that there is another spanning tree that has a weight 5. Okay, pause the video and try to make other spanning trees for this graph. Basically I have got a spanning tree with a weight 5. Now let's move forward. So minimum spanning tree is a weight of 5 for this given graph, not 6. Now moving on further, let's discuss the Kruskal's algorithm for finding the minimum spanning tree. I've already taken an input and made a graph of that input. Now let's write steps for the algorithm. First step is choose the minimum weight edge. We have to repeat these steps again and again, right? So what we can do is sort all the edges according to their weights, right? So sort all the edges in the increasing order of their weight. What is a weight? It is the weight of an edge or the length of an edge, whatever you take it. Now let's write step 2. Step 2 is we'll iterate over these edges that have been sorted in increasing order. So if I add that edge in the graph, so if I try to add that edge in the graph and the resulting graph does not contain a cycle, then only I can add that edge, right? So if I add an edge and there is no cycle, that means that's a worthy edge. We can include it in our minimum spanning tree because that does not form a cycle. There will be no resultant cycle in the graph, right? If there are no cycle, I'll include it in my graph. We can easily see that it is a greedy algorithm because we are performing two greedy steps again and again without thinking of the future consequences. Now let's make this graph. Take one more example. Let's take one more example. Let's try to dry run this code on this given graph that I already made. 1 2 2 2 3 and 3. Let's make a minimum spanning tree of this graph and repeat the steps. So what was the first step? Sort all the edges according to their weights, right? So first, the smallest weight edge is edge 1 to 2, that has weight 1. Now writing all the weights for the given edge: 1 to 3 2, 1 to 4 2, 2 to 3 2, right? Now I'll have edges of weight 3, that will be 3 to 4 and 2 to 4. So these are the order of edges and this is the order of weight. Now let's iterate over these edges, right? First of all, I'll take this edge that is 1 to 2. Now let's make a resultant graph or resulting graph, right? And move according to the algorithm. Initially my resulting graph is not connected with any of the edges, okay? Now I'll take these edges and try to connect them in the resulting graph. First of all, there is an edge that has weight 1 and going from 1 to 2. So if I add this edge from 1 to 2, then this edge will not create a cycle, right? Because it is connected 1 to 2, right? Basically I have taken this edge 1 in my resulting graph. Moving on to the second edge, that edge is from 1 to 3, right? Now if I try to apply this second edge from 1 to 3, I will it will not result in a cycle and I can add this edge. Moving on to the third edge, if I am able to add this edge in my graph that is from 1 to 4 and it does not result in a cycle, I'll add it, right? So I added this edge in my resulting graph. So we can see that we have already received a minimum spanning tree of this graph. But now if I try to add the edge from 2 to 3, then this will give me a cycle from 1 to 2 and 2 to 3, right? So if an edge gives me a cycle, I will not add it in the given graph because I want a minimum spanning tree. What is the condition of the tree? That there should be no cycle, right? So I won't take this edge in my given graph. Coming on to the next edge, already we have found the minimum spanning tree of the given graph, but we have to check for all the edges. Let's check for all the edges, right? So there are 4 vertices, so there will be n minus 1, that is 3 edges, right? 4 vertices and 3 edges. My graph is a tree without cycles. Now moving on to the next edge. The next edge is 3 to 4. So I added this edge 3 to 4, and I cannot add this edge because it will give me a cycle. Now checking for the last edge, that is 2 to 4. So if I try to include this edge, again this will give me a cycle 1 2 4 1, right? So I will not add this edge in my resultant graph. So my set of all the edges is complete, right? Because there are 4 vertices and 3 edges, and every 2 node have a single path between them. So I hope you have already watched the video of cycle detection using DSU. I have used the same approach here. Now let's try to run the minimum spanning tree algorithm for the given big graph that I have made here, and let's run it for another case, okay, so that it becomes more clear to you all. Let me erase this and then we'll continue on with the big graph, okay? Or you can also pause the video and try to make the minimum spanning tree by the given steps in your pen and paper, right? So first of all, we'll sort all the edges in the increasing order and then try to find the spanning tree. So M is for minimum and spanning tree is for spanning tree, right? There should be no cycles. One, two, three, 4, 5, 6. I'm just writing the resultant graph and I haven't added any edges right now, okay? And then I'll try run that algorithm here. Let's take the minimum edge, that is 3 to 6, and I can easily add that edge because it does not give me a cycle. Now let's take on an edge that is with the second minimum weight. Is it 2? No, it's okay. The second minimum edge is not 2, it's 1, right? From 8 to 9. Oh, okay, this got erased, so it is 11, not 1, right? Because when I was erasing, it got erased. So in the input you can see that it is 9 to 8 and it's weight 11, right? Now tell me one thing, that if we have a tree, what will be the minimum spanning tree of this tree? See, total number of spanning tree possible for a given tree is 1 only, right? So if it itself is a spanning tree and there are no other spanning trees, that means it is a minimum spanning tree of itself, okay? So continuing with the above example, now the second highest edge was from 7 to 9, it was of weight 2, right? So I can easily apply this edge because it's the second highest edge and there are no cycles formed. Now we have next highest edges of weight 3 and 3. If I'll add this edge from 3 to 5, it will not result in a cycle. Now I'll take this edge from 5 to 6 and try to add this edge. This edge will give me a cycle, right? Why? Because 5 and 6 was connected from another path, that is 5, 3 and 6. So this will give me a cycle, so I will not take this edge in my minimum spanning tree algorithm, right, in the resultant graph. So there may be a doubt that we can also take this edge first, 5 to 6, right? Because both are of weight 3, any edge can come first. So if I take this edge from 5 to 6, then I cannot add my edge from 3 to 5. Why? because that will give me a cycle now. So just because of this, there are various spanning trees possible because I have choices whether take this edge or that edge, right? So just because of this, we have various types of spanning trees possible for a given graph. Now let's move further. The next weight I see is 5. No, there's no edge of weight 4. Let's add this edge of weight 5. Again, moving further, I have 6 here, and let's add this 7. So will I add this 7? No. Why? Because uh, adding this 7 will give me a cycle, right? 4, 5, 6, 8. So let it be. I will not take this 7 weight edge in my graph. Now after this I have got 8. There are 2 8s. I can add this 8 from 4 to 7, and I can add this 8 from 2 to 4, right? Because they will not give me a cycle. Now let's take this 9. I won't add this 9. Why? Because you give me a cycle 7, 4 and 8. So if I add this 9, it will give me a cycle, right? After that 9, I have got the left 9, that is from 2 to 3, the edge from 2 to 3, and I can also not add that 9, right? Now let's take this 10. I'll add this 10 because this will not give me a cycle, and I cannot add the middle 10, that is from 4 to 6, right? And then I have run this algorithm for on the given graph. Now coming to 11, I have this 11 on the right side, 8 to 9. I won't add this 11. Why? And because it will give me a cycle, and I also won't add 12, that is from 1 to 3. Why? Because again it will give me a cycle. The total weight of my edges are 10 plus 8 plus 8 plus 6 plus 5 plus 3 plus 2 plus 1. So what is the total weight? It is 10 plus 8 plus 8, 6 plus 5 plus 3 plus 2 plus 1, 43. Okay, so I got the minimum spanning tree of 841, 43. So I'll code it out in the next video, right? And then we'll check for the given input that are we getting the answer 43 or not. And then we'll also print different edges. Thank you. So guys, let's try to code this Kruskal's algorithm using disjoint set union, right? Basically I have taken a structure called disjoint set union that I have already explained in the previous videos of disjoint set union and cycle detection through disjoint set union, right? So this is the graph that I explained it to you in the previous video. Its minimum spanning tree that came of size 43, right? So basically let's input the graph first, right? And to find the minimum spanning tree of a graph, we don't need to make the whole graph, right? We just need its edges. So let's take edges. So we'll take edges in which way? So the edges will be of this type, right? It will be a tuple of 3 types. Let's take it by weight and that and there from x to y weight w. Okay, so let me input these edges int x comma y comma w. Right, so you can easily see that I have already written the input here, right hand side. Now edges I, okay, let me just resize it till n. So edges I equals to w comma x comma y, right? So now what I need to do is I need to sort the edges on the basis of their weights, that is w, right? So how will I sort this on the according to their weights? See guys, that's why I have taken the edges. The first I have taken it as w, so that if I just write a sort function, that will be edges dot begin edges dot end, right? This is an inbuilt sort function. So if I write this sort function, what will happen? It will compare these vectors, right? Basically x comma y comma w comma x comma y is a vector, right? So it will compare these vectors, and first of all a vector will be compared on the basis of their first values, that is their w. That's why I've written w as first. Okay, I can also write it as like this, na? I hope you got my point here. x comma y comma w, right? But this will mean ki the first is x, so all my edges will be sorted on the basis of their x. For this I have to apply a comparator then, right? So I am just avoiding a use of a comparator here, just taking things simple. Okay, I have sorted all these edges. Now what I need to do is I just need to take a disjoint set union, right? So basically let's take a disjoint set union G and let us initialize it by n, right? So if I initialize a disjoint set union by n, that means there are how many nodes in it? N nodes. Those n nodes are from 0 to n minus 1, right? But my input graph is of the form 1 based indexing, right? Here the nodes are from 1 to 9, not 0 to 8, right? So what I'll do is I'll just make them 0 based indexed so that I can use disjoint set union properly. Okay, now let's go through all the edges, right? Now what I need to do is it's very simple, that the algorithm I have already explained. Let's get my uh, variables back. Okay, so the x was edges I comma 1, right? So basically it's a 2D vector, right? Now edges y, what is the y here? It is 2 because I have placed it at second position, and w is at the first position, right? W, it is at first position. Okay, let me first print it for you. W x y. Okay, basically no errors, and we can see that edges are sorted on the basis of their w values, right? Because one is the smallest, then 2, then 3, then 4, then and so on, right? So okay, now I've got my values back. Now what do I need to do is I just have to check if I apply this edge in my disjoint set union, then that the edge does not result in a cycle. So I've already explained this concept in my previous video of finding cycle through disjoint set union, right? So you can see that video tutorial first. So what I need to do here is I just have to keep in which component I have x. If it does not equal to the same component of y, that means I can apply this edge. That means x and y in the different components, they are not connected through another path, right? So this will mean ki can take this edge. Okay, and let's take this as then what I need to do is g dot unite. I'll unite x comma y. So I'll unite this x comma y, and in my answer I'll include the weight w. Okay, now let's print the answer. I will just include all the edges, by which I don't find a cycle, or we can write which doesn't result in a cycle, right? So we can easily see that I have got this 43 here, right? So how did I get this 43? Let's try to print these edges, okay, so that it can be more clear. I took this from 1 to 2. Okay, first of all I took this edge that is from 2 to 5 of weight 1, right? So I took this edge from 2 to 5 of weight 1. You can easily see this. I here is written 2 to 5 because it is actually 3 to 6 that I have explained here. I just converted everything into 0 based indexing so that I can use g dot init n. Otherwise I have to initialize it by n plus 1 if I want to use 1 based indexing. I hope you are not getting confused in that, right? So I have taken this edge 1, 2, 3, 5, 6, 8, 8, 10. It's the same that I have already explained to you in the previous video here, right? Guys, thank you for watching. You can also make this graph, right? You can also make this graph. You can take a adjacency list and put x in y and put y in x, right? You can also make it as a graph. Okay, thank you guys. Hello everyone, let us begin with the minimum spanning trees algorithm, and we have already discussed what is a minimum spanning tree in detail. in the previous video, right? The Kruskal's minimum spanning tree algorithm. So in this video we'll discuss about Prim's minimum spanning tree algorithm. Right. So there is a like an advice that before going through this Prim's algorithm, you should go to Kruskal's minimum spanning tree algorithm and Dijkstra's algorithm to find single source shortest path, right? So I just want you to go through Dijkstra's because in the because afterwards you will realize that the implementation of this algorithms Prim's algorithm is similar to Dijkstra's algorithm, right? So let's start this. Okay, now there are few terms. I want you all to know about these terms. What is an active edge? I'll say active edge, MST edge, and MST vertex, right? So you must know about what these terms mean. So active edge is an edge like uh, let's say if edge is 2 points, yeah, x and y. So if this edge is an active edge, then either x or y should be a MST vertex, right? Now what is an MST vertex? MST vertex is a minimum spanning tree vertex. That means that vertex is included in my MST till now, right? So basically when I'll run this algorithm, there will be few vertices that will not be included in my MST, right? And there will be few vertices that will be included in my MST till that particular time, because we all know in the end all the vertex has to be included in the MST, right? Okay, so you are clear with the active edge. Active edge is an edge that is pointing from an MST to different other nodes which are not included in the MST, right? Basically MST edge points from MST vertex to a non-MST vertex. Okay, so these are the active edges. And now what is an MST edge? Simple, the edge that is included in my minimum spanning tree, right? Whose total sum we need. Again, repeating same thing, that Prim's algorithm is a, let me write it over here. Prim's algorithm is greedy algorithm, right? So what is a greedy algorithm? A greedy algorithm is an algorithm that says ki if we find a local optimum move, then it will result in a global optimal answer. Global optimum answer, right? So greedy algorithm simply means that if I am performing a move and I say that it is an optimum move, then this move will always lead me to the best answer, the global optimum answer, right? So that's why it's a greedy algorithm, because we'll be performing some steps repeatedly and those steps will lead me to the final answer, right? So it's very much similar to Dijkstra's algorithm, and then you'll also realize it yourself. Okay, what we'll do is let's see steps, right? And in the Prim's greedy algorithm, all the greedy algorithms can be proved by the method of like if there is a greedy algorithm and we want to say that it won't work, then we have to find a counter test case for it, right? So what we do is we try the method of contradiction and we try to find a test case, right, a counter example, and say that for this greedy algorithm this test case won't work, that's why we can prove a greedy algorithm wrong. Okay, so let us see the steps of the Prim's algorithm. First of all, we'll choose a source vertex, or let's say source vertex. Select a source vertex. Okay, now guys, when I have chosen a source vertex, we all know that in Dijkstra also we use a source vertex, right? So this vertex can be any vertex from 1 to n or any vertex in the graph, right? So let me write it, any vertex from graph. I'll give you two implementations of this Prim's algorithm. The first will be basic brute force naive approach, and the second will be a little optimized approach, and we'll try to submit it on Spoj. Okay. The second step. First is to choose a source vertex, and the second step is out of all the active edges, choose the one with the smallest weight. Right, right. So basically what I did was I chose a source vertex. I put all its edges in the active edges set, right? So we'll have a set that will say that these are the active edges, and out of all those active edges I want the smallest weight active edge, right? I'll select the smallest weight active edge, and let's say it was pointing from x to y, right? So let's say x was already included in my MST and y was not included in my MST. X was an MST vertex and y was not an MST vertex, right? That's why it can be a active edge. So if this is an active edge and it has the smallest weight, I'll pick up this edge, I'll select y in my MST vertex, right? Select y in MST vertex and this edge in MST edges, right? Minimum spanning tree edge. And then what we'll do, for all the edges of y, I'll try to push all the edges of y in the active edges set, right? Because now guys, y is included in my minimum spanning tree vertex, right? Now y is the minimum spanning tree vertex and all the edges pointing from y will be pointing towards some non-MST vertices, right? From y it will be pointing somewhere else, the edges of y. So guys, these edges have become active now, right? Because y is in my MST set. So I already told you about this, that out of all the active edges, what I'll do is I'll pick up the edge with the smallest weight, right? Just like Dijkstra's algorithm. In Dijkstra's algorithm, what we do was we pick the edge with which gives me the smallest distance, right? But in this, we'll pick the edge which gives the smallest weight. Okay. So this is the second step of the algorithm. Choose the edge with the smallest weight, right? Now let's go on with the third step of the algorithm. So guys, the third step of the algorithm is when I've chosen a smallest weight edge that is pointing from x to y, right? Let's say y was already in the MST and this was not in the MST. So what I'll do is I'll push its adjacency list. That means make all edges of y to be active edges, right? Because now all edges of y can give me an active edge. Okay, so I'll mark it as visited. That means it is included in my MST, the vertex y. Okay, and then what I'll do is I'll go in the adjacency list of y and mark all its edges to be active. Again, what I'll do is repeat these steps. Right, I'll repeat the step 2 and 3. Again, what I'll do is I'll select and choose the one with the smallest weight such that x is included and y is not included. That's why it will be active, right? Because active edge requires a condition, that the condition is at least one of, or we can say exactly one of its endpoints should be in MST, right? And the other endpoint should not be in MST. Okay, so this is an active edge, right? So in the Excel also we did the same. Out of all the active edges, we took the edge that gave us the minimum distance to a particular node and we included in our shortest path and then we move forward, right? So we'll do the same over here, right? So guys, first of all, what is the algorithm to select the shortest vertex? Out of that, what we have, out of all the active edges that we have, to pick up the smallest one and then update the adjacency list of y, right? So we'll repeat it again and again. So this is the minimum spanning tree algorithm, Prim's minimum spanning tree algorithm, right? It's a greedy algorithm because after performing just 2-3 steps, we are finding the global optimum answer. And right, so I made this let's try to run algorithm, run this spanning tree algorithm on this graph, right? You can try it yourself first. So guys, let's choose any vertex. Okay, let's choose one, and I have completed the first step of my algorithm. Now I'll repeat the second and third steps. So what I'll do is I'll actually make active edges with blue. Okay, active edges with blue, and spanning tree edges, let's say, with pink. Spanning tree means that though the edge is included in my spanning tree, right? Right, so let's make this, let's dry run over the given graph. This is the graph that I made in the previous video, right? Cruscals. So I chose one, and okay, again, one thing that I'll, whenever I'm writing a vertex over here, that means it is included in my minimum spanning tree. Okay, so whatever active edges I have this edge 10 and this edge 12, right? So these are the active edges. Okay, I have to make them in blue. Come on. Okay, this is 10 and this is 12. It will take a time. It will take a lot of time. You can try this yourself also. Okay. Now I have two active edges. Out of this 10 and 12, which is the minimum, the one with the weight 10. So I'll include that edge in my minimum spanning tree. Okay. So let me just make it with pink. Okay. And I'll include this vertex. Okay. Let's make it with pink only, the vertex also. The included vertex. 2 and this is 10, right? Now what I'll do is I'll update the adjacency list of 2, right? So what are the active edges now? This is an active edge 9 and this is an active edge 8, right? So out of these three active edges, what I'll do is I'll pick up the minimum one and include it in my minimum spanning tree. Okay, let me just pick it up. So 8 and 4 is done. Now update the adjacency list of 4, right? So what will be the edges now? This 7, this 8 and this 10, right? 7, 8 and 10 will be the edges that will be coming from 4, and yes, this 5 of course, right? So we have these edges that are coming out of 4, and now these are the active edges. So guys, out of all these active edges, 5, 8, 7, 9, 10, 12, what is the minimum? 5, right? So what I'll do is I'll include it in my minimum spanning tree, right? So let's include it. 5 and 8 is included in my minimum spanning tree. Now update the edges with the 8, right? So let's update them. 6 and 9, 11, right? So we saw that these were the edges that were coming out of 8. Now again, finding the minimum of them, 7, 8, 6, we have 6 as the minimum, right? So we'll include this edge in my minimum spanning tree, and here I'll get 6, here I'll get 6, right? Okay, now let's update all the edges with 6, right? So blue, yes. So this is 3 and the right one is updated, the upper one is already in the active set, and this is 1. So guys, out of all these, which one I need? The smallest one, and that is 1, right? Let me include this edge in my minimum spanning tree. This will give me a 3 over here and 1 over here, right? Okay, now updating all the edges with 3. See, 12, 9 and 1 were done. We only had one edge that was left, and that is this edge 3. Now out of all these active edges, which one I need? I need the smallest one. So we can take this 3 or this 3, it doesn't matter, right? Out of the equal ones, we can take any, right? So take any. Let's take this one. Okay, so what I have here is I have this, and then I'll make a 5 over here. Update all the edges with 5. So guys, we can see that all the edges of 5 were already updated, right? We don't have to update them because 7 edge, the edge 7, 3 and this 3 all are already in my active edges sets, right? Okay, so now again, finding the edge with the minimum weight among all these is this 3 edge, right? but we know that this edge is not an active edge because its both endpoints are pointing to the minimum spanning tree vertex. As I said na ki at least one edge should point in the minimum spanning tree. So I'll remove this. Now taking the minimum one among them is I guess 7, 9, 8, yeah, 7. So again I'll remove 7 because this does not include in my active edges set, because I cannot pick it up because it's not an active edge, right? Because for an active edge at least one end should be a exactly one end should be a minimum spanning tree vertex and one end should be a non minimum spanning tree vertex. Now picking up the next one, 8, right? This 8, I guess this is the next 8, right? The 9, 12, 10, 9 and 11. So 8 is a minimum. Picking it up, making 7 over here, right? So pen color 7, and I'll include it in my minimum spanning tree because it was pointing to a non-visited vertex, non-minimum spanning tree vertex. Let's include it over here, right? And let's update the edges with the 7. So I have this edge 2 that is pointing to 9. Again picking up the edge with the minimum weight. So what is the edge with the minimum weight? 2. So just mark 2 and push them in the, yeah, and update 9. Now updating all the vertices with 9, all of them are already updated. Now moving on next. See, the next we have 9, not an active edge, not an active edge, then 10, not an active edge, not an active edge, and not an active edge, right? So we can see that all the vertices, we can see that the resulting is a tree, of course, right? And we can also see that all the vertices are visited right now, so we don't have any other edges to be included because all of them are visited, right? All of them are included in my minimum spanning tree. So let's find the sum of this. It will be 10, 8, 8, and 5 and 6 and 3 to 1, right? So this is 12, 17, 17 and 16 is 33 and 10 is 43, right? So the minimum spanning tree of this graph is of weight 43. We got this from Prim's algorithm, right? Again guys, I'm repeating the same thing. Dijkstra's algorithm is similar to Prim's algorithm because this actually the Prim's algorithm was found by someone else, then Prim later republished it, and after that Dijkstra also republished it, right? After 2 years. So basically I just wanted to say was ki the Dijkstra's edge, right? The Dijkstra's algorithm is very similar to the Prim's algorithm, right? But in this we find MST, and in that we find the single shortest path, right? Instead of taking only the edges, we'll take the distance, right? We update the active edges with the distance, but in this we update the active edges with the weight, right? So guys, what's happening here is I'm picking up source node and pushing all its edges in the active edges set. Then I'm picking up the minimum one among them and pushing all these edges in the active edge set. Again I'm taking the minimum, right? So how can I achieve that in a good time limit? Of course there is a n square solution for that, right? So see, I can iterate again and again for all the active edges set, and then find the minimum one and then include them and then update the other vertex, right? Of course there's an n square solution, you all can try and code it, right? But I'm not going into the n square solution. I'll go into a better solution. So the better solution can be that, what do I always need guys? The best thing is, the main thing is that I have to choose the smallest weight edge among all the active edges, right? How to choose the smallest weight edge among all the active edges guys? How can I always maintain an edge to be the smallest edge, and I just want how can I just take out from a given set that this is the smallest edge and I have to use this edge? We can create a heap, min heap, right? Min heap. We can create a set, or we can use a priority queue, right? So in the code video that I'll be making of this, we'll take a priority queue. You can also use minimum heaps, you can also try building your own heaps, right? But I'll give you a shorter, simpler way to code it, right? And then we'll discuss its complexity in the code video, right? So to maintain the active edges, what I'll do is I'll always have the I'll push all the edges in the priority queue with their weights, and of course the top of the priority queue will give me the minimum weight of the edge, okay. And that I'll see that whether it was an active edge or not. If it was not an active edge, I'll ignore it. If it was an active edge, I'll include it in my MST and update the adjacency list of the next vertex. Okay, so see you in the next video. You can also try this question yourself, right? Minimum spanning tree using Prim's algorithm on Spotch, and then we'll code it and submit it. Okay, see you in the next video. So guys, let's try to code Prim's algorithm, the minimum spanning tree algorithm. We'll try to submit on Spotch for this question. Okay, minimum spanning tree. So according to the given input, we have 4 5, that is the edges and the number of edges, and the edges with the x to y and weight, right? I and j with weight. You can read it. We'll go in the similar fashion, right? So starting with the code, let's include some files. So the int main, and guys, I'm just putting these files, don't worry about these files. Okay, this is for input, output, and these are some fast input output files. Okay, right. So initially I have n and m. Let's input n and 8, 9 and 5. I made this graph, this one that I explained to you over here, right? And after this, what we need was, let's input the given graph and its adjacency list. Let's take a adjacency list. Okay, graph of n plus 1. Why n plus 1? Because the indexing is 1 based. So let's input all of them. Int x comma y comma w, right? So there's an edge from x to y with w. It's an undirected, and what I'll do is, now I want the adjacency list to be considering pairs. Why? Because there is an extra weight with it, right? So I'll just push them with the weights y comma w, and in the adjacency list of y I'll push it as x comma w, right? So I have made the adjacency list as a pair. Why? Because I have to push here from x, the edge is going to y, and it has a weight w. Okay, I hope this is clear till now. Now after this, what we'll do is, we'll start on with the algorithm, this one, right? So for the algorithm, what I told you, that we'll take a priority queue, right? And this priority queue should contain what? Pair, right? Because for an active edge, what I need for an active edge, that I have to select the edge with the minimum weight, so I need a weight of that edge, right? And after picking that edge, I also need where it was leading to, right? Which non MST vertex it was leading to, so that I can update all its adjacency list in the active edges, right guys? We'll take it as a pair, okay? And we want a priority queue to be all minimum heap type, right? So what I'll do is, let's make a priority queue with a minimum heap type. Okay, I'll use the comparator. So okay, and after this, what we'll do is greater pair. Just build it so that there are no mistakes. Okay, as I thought always, because I always use PBS pushback, right? I'm not defining it over here. Pushback. These are the disadvantages of using a snip. Okay, so I made a priority queue, pair, vector pair, and greater pair. Okay, so this will give me a smallest weight vertex. Let's push a vertex in the priority queue and let that node be, guys, any node. Okay, so let's start with 1. Okay, let's say the weight is 0 and I'm starting with 1. This is just for a start, right? So while not q dot empty, while the priority queue is not empty, means I have the active edges till now. What I'll do is I'll pick up the top active edge, or let's name it pair best, right? And this best will be equal to q dot top, right? And what I'll do is I'll just pop it from the queue, right? Now what I need is I need the distance, right? So let's say this is the, or let's say weight, right? So weight equals to best dot second or first, right? Because the pair is which type? Let me just write it: weight comma node. So starting with the first pair, right? And the node that it is pointing to, or let's say to, is which one? Best dot second, right guys? So what I need to do is, now to check if it is an active edge or not, what I'll do is I'll check if I have visited this 2 already. That means if the second part of the edge is already visited, then it cannot be the active edge, right? So what does visited mean over here is that it is in my MST, right? So I need to make a array, visited array, int visited and plus 1, and initially I'll mark it with 0, right? So simple. What I'll do is, if visited to, then continue, right? That means I don't need to do anything with this vertex 2, right, wherever I'm going from this, because it's not an active edge, right? So initially I marked the all the visited as 0 base. That means it is not included in my MST. Let me write over here: visited means not okay, means included in my MST. If it is already included in my ST, that means it was not an active edge, right? You can see that the last cases that we were having, that the edges were already visited, right? The vertices were already visited for those edges, and I removed those edges. I didn't include them in my MST, right? Otherwise what I'll do is I'll include it in my MST. Okay, so let's take a variable MST0, and I guess due to the constraint is n is 10 to the power 4 and the wages are 10 to the power 6. So 10 to the power 4 into 10 to the power 6 is 10 to the power 10. So basically it should be a long int type. Okay, the answer. Okay, right. So what I was doing is, if I have already visited it, that means not an active edge, right guys? Otherwise, if I didn't go in this, if I didn't continue on with the loop, what I'll do, I'll include it in my MST. Okay, so MST plus equals to weight, right? And I'll mark this node as visited, right? And after that what I'll do, you can also take a boolean array for the visited, but it's all up to you. Now what I need to do is, I'll go for the adjacency list of this vertex 2, right? And I just have to push it in the queue, right? Push all the edges in the queue such that the other part was not visited. That means if they were the active edges. So if visited x dot second, right? Why second? Because okay, we have made y comma w, x dot first, right? So if visited x dot first equals to 0, that means see guys, again explaining it, 2 vertexes visited, and this edge is going to some vertex, let's say x dot first, and it is not visited, right? X dot first is not visited. What does this mean? That currently I am on an active edge, right? Because one part of it is visited and the other is not visited. So if visited x dot first is 0, what I do is I just push that active edge in the right queue so that it will give me the minimum, right? So what will be the weight? X dot second should be the weight, and x dot first is the next vertex which it is pointing to, right guys? So after this loop ends, because this loop will end once, because all the vertices will be visited once, right? After the loop ends, what I'll do is I'll just simply print mstring. Let's check for errors. No errors, and I got 43, right? Let's try to submit it on Spot. While pushing in the priority queue, I have a pair wait comma node type, but in the adjacency list, I have the pair as y comma w, or I can even reverse it. It doesn't matter. It's running on right. So guys, we got 100. The time is 0.12 seconds. Okay. So I hope you get this algorithm, right? The Dijkstra's algorithm works similarly, right? But in that, what we do is we try to push distance plus x dot second. We try to find the node with the minimum distance, right? But in this, we are trying to find the edge with the minimum weight. Just one line difference. You can also code Dijkstra using this approach. So thank you guys.